Hi, everyone. Welcome. Welcome to the Weather and Climate live stream. I'm Jonah.
I'm Mark.
And I'm Margaret.
And we're some of the many scientists helping to organize this event.
We are so thrilled you're here to join us as we kick off this 100-hour live stream. We've got some amazing meteorologists and climate scientists who are excited to share their work with you and answer your questions. We've also got some great keynote speakers, panels, and surprise segments along the way.
Before we start, we want to take a moment to talk about why we're here. So we all know how important weather forecasts are for our lives. Whether you're planning for the weekend or you're preparing for a natural disaster like a hurricane or a wildfire, accurate weather predictions improve and even save lives. At the same time, the average weather, the climate, is changing. Climate projections can help us plan for the future too. So not just for the week to come, but for the decades ahead.
Fortunately, Americans have long been able to rely on increasingly reliable weather forecasts and climate projections. Every time you open a weather app on your phone to check if it's going to rain tomorrow, you're using 80 years of American scientific achievement, most of it a direct result of the investment the American public has made in our field through federal funding. In the 1940s and 50s, American scientists made the first computerized forecasts of the weather and climate. Since then, the United States has been an epicenter of climate and weather prediction, with scientists pushing the bounds of our physical understanding and our computational abilities. We operate one of the most expansive and comprehensive observational networks in the world, giving us critical real-time information about the state of our land, atmosphere, and ocean. These observations help keep our predictions accurate and help us better understand how these systems might work in the future.
These forecasts and projections have benefited Americans everywhere, from the countryside to the city. Whether you're a farmer, first responder, operate a business, serve in the military, or work in local government, you likely rely on weather forecasts every day. But lately, this incredible achievement of the American public is under threat. Weather stations are understaffed, research grants are being canceled, scientists are being kicked out of their offices. These cuts threaten the forecasts we all rely on, putting us all at risk. Additionally, proposed additional cuts being considered right now in Congress would make this situation worse.
Now, scientists really do not like mixing our work with politics. I've met many scientists over the years from many political backgrounds, and for all of us, our goal is to understand how the world works. We want to understand the truth, independent of any preconceived notions or things that we bring to the table. We want to know how things really work out there. And then we want to take that understanding and bring it to you. We want to help share our findings with you so that you can make informed decisions. I've been working in atmospheric science for over a decade now, and I'm amazed at how widespread and core this dedication to the truth is. I've stayed up late many times with friends getting into passionate arguments about really small little details about how some physical process works. So full disclosure, we are nerds. Sorry to all the colleagues participating, depending on how you might feel about that, but I think it's true. We're nerds and we're proud of it. And so that's really where we're most comfortable and where we most would like to be, is doing the science.
Yeah, so this is all a sign of how important this moment is, that when we went to our colleagues and asked if they would like to participate, many people said yes, and they signed up and gave us their full support. Some of our keynotes may not be household names to you, but they are like heroes and celebrities to us. So it's like starstruck when you're emailing kind of like who you grew up watching on television, or we're using their weather software or something. We've read their papers also and watched them doing the weather report, and to have them here with us is thrilling.
We're scientists who want to do our jobs on behalf of you, the American public, but we need your help. Before we get started, we should say right now that this is a nonpartisan event, and any opinions our speakers share are their own opinions. On behalf of this event, we have one message and one message only. Let's maintain funding for weather and climate science so we can keep providing the forecast that you need to live safely and thrive.
So give us a listen, whether it's just for a few minutes or for all 100 hours. I don't know if anyone, maybe take some naps in there. But come and listen and learn, and come and get your science questions answered. You can share them in the comments, and come and get a window into what meteorologists and climate scientists think about all day.
Let's get started with our first segment. We're going live to NASA Goddard Institute for Space Studies in New York, where scientists are having their final day after their lease was terminated as part of the cuts. To host this segment, we have Andrew and Syl.
Hi, everyone.
Hey, it's great to see you all.
Yeah, my name's Andrew Williams. I'm a climate scientist at Princeton. Yeah, I'm going to be one of the hosts for this segment.
And I'm Syl Foisey. I am a PhD climate scientist in training, if you will. And I am coming at you from just outside of NASA GISS. You can almost see it out my window.
Yeah, and it's amazing to be here. It's amazing to see almost 400 people on the chat. You guys are incredible. Thank you for being here. We see you got some people from Canada. We have some people from Virginia, Minnesota. Do you guys want to put some love in the chat, some hundreds?
Yeah, I was going to say, first of all, shout out to State College, Pennsylvania. I love Penn State. Oh my gosh. AccuWeather. Oh my gosh. And also, yeah, let's get some 100 emojis in the chat for 100 hours.
San Diego, Nebraska, go Big Red, Midwest represent.
This is awesome. Oh my goodness. Do we have anyone from the West Coast? Did you see San Diego? Oh, that's amazing.
Diego, Texas, Massachusetts, all over the country. You got Germany as well.
Oh my goodness.
Amazing.
Austin, Texas. Shout out to Austin. Austin's awesome. It's the best food truck scene ever. Yeah. This is sweet. Toronto, Canada. Okay, we are international. I think we've done our job, Andrew. I think our work here is done.
Yeah. France as well. It's awesome. Hey, Brett.
France, no way. All right, this is too fun.
Yeah, this is great. Yeah, so guys, we're excited to have you here for the first hour, for hour zero of this 100-hour event. Only 100 hours to go, so hang in there. We expect to see you all there right till the end. Yeah, and we're going to jump right in with our first speaker, who is David Rind. David was a NASA research scientist at NASA GISS for 30 years and is now emeritus. And David, take it away.
Hi, everybody. The comment about some of us are in institutions where we're being kicked out definitely applies to us. In fact, if you hear any noise in the background, this place is literally being torn apart with us still in it. And talking about science nerds, people are still working on their computers, even as NASA's removed their internet line from the building. However, at this point in time, the idea is to look at a retrospective of how NASA GISS became one of the leading institutes for understanding and trying to project what climate will be like in this era of increasing greenhouse gases. So we'll start with the first slide. And normally first slides are pretty straightforward. They just give the name, title of the talk, which you probably already knew. But this first slide actually has a contradiction in it. And that will be the first part of the talk. Notice the name of this place is the Goddard Institute for Space Studies. And yet we're talking about the history of climate research. How did we move from NASA's priority of looking at space to looking at climate? And that's a tale which we will now go through. So GISS, Goddard Institute for Space Studies, was established in May 1961 in New York as a branch of Goddard Space Flight Center, which is located in Greenbelt, Maryland. The idea was to have a NASA institute that interacts with the universities in the New York City area, and at the same time gets professors and people from the academic backgrounds interested in NASA programs. And the initial goal was to do theoretical research in space science, hence the name. Now, GISS has a really glorious history in space science and astrophysical research. But we won't talk about that here because here we're going to be focusing on the climate research component. And you'll see how NASA GISS made a U-turn to arrive at that destination. Essentially, initially, several of GISS scientists were involved in the Pioneer Venus project, which took place in 1978 And this was the first satellite that the US ever sent to look at the closest planet to us, Venus, to orbit around that planet. Now, Venus is pretty interesting because, yes, it's closer to the sun than the Earth, so it should get more sunlight. But Venus is so bright because it reflects a lot of that sunlight out to space. The Earth's reflection is about 30% of the sunlight. Venus is between 70 and 80%. So Venus should actually be colder than the Earth since it loses so much of that sunlight. Yet its surface temperature is much hotter. We're talking about something on the order of 700 or 800 degrees temperature at the surface compared to what we have here at the Earth. And the reason is because its atmosphere is 96.5% carbon dioxide. So the GISS scientists who were part of Pioneer Venus project started realizing the potential component capability of CO2 as a greenhouse gas to provide warming to a planet. Separately, in 1958, Dr. Charles Keeling started measuring atmospheric CO2 at the Mauna Loa Observatory in Hawaii. And when he started measuring it, the value was 315 parts per million. As time went on, people noticed it was increasing. And currently, the value is close to 430 ppm. This measurement doesn't really depend upon it being at Mauna Loa. You could make the same measurement anywhere around the globe, basically, and you get the same sort of graph. So taking that information, one of you is at Princeton. In 1967, Suki Manabe co-authored a paper talking about the importance of increased CO2 as was being measured by Keeling to the climate on the Earth. This is a very famous paper, and Dr. Manabe actually was one of the winners of the Nobel Prize in Physics in 2021, based on his early recognition of the importance of CO2, increasing CO2 to the Earth's climate. From his experience studying Venus, Dr. James Hansen fully appreciated that this was a subject of concern. He could see the extent. Now, we're not talking about getting temperatures on Venus here, but the extent to which CO2 could actually force a warmer planet. In 1981, Dr. Hansen took over as head of GISS. And with that idea in mind about how important increasing greenhouse gases would be to the Earth, he had GISS take a U-turn away from what had been a primary focus on space science and astrophysical research to focusing its resources on understanding how climate might actually vary on the Earth due to increasing CO2 and other mechanisms, the sun, volcanoes, things of that nature. GISS started by trying to estimate the Earth's sensitivity using a one-dimensional model. And this paper in Science, which has had thousands of people paying attention to it, Climate Impact Increasing Atmospheric Carbon Dioxide, was a paper based on this 1D model. And it pointed out how this could very well be quite impactful for the Earth. But as we know, climate is more than one-dimensional. So to understand how climate would change regionally and locally, and again, in a more nuanced way, needed to use a 3D model, like the models that are used for weather forecasting, but with some real differences. Again, independently, in the 1970s, Robert Jastrow, who was at that point head of GISS, imported a general circulation model from Arakawa at UCLA to do seasonal forecasting, what was called the farmer's forecast. Dr. Hansen decided to use that model as a base, but it required a lot of alterations to become a climate model. To understand things like the feedbacks on the climate system and also the impacts of climate change, there's a lot that has to be added to an atmospheric model. In addition to atmospheric physics like clouds, precipitation, radiation, and dynamics, some of which, like clouds and radiation, had not been very important as far as weather forecasting models go, but they're very important to understand the radiative balance of the planet, how much energy comes in and out. And numerics, these are numerical models, so you have to have a numerical scheme. Things that were not part of atmospheric science, like vegetation. For example, when it rains, how much of that rain enters the ground and how much of that moisture is re-evaporated or transpired back into the atmosphere by vegetation. So you need vegetation in climate models. Soils, different soils have runoff capabilities, infiltration capabilities. The Earth is 2/3 ocean, and the oceans have a very large heat capacity. So you also need ocean dynamics in the model. Sea ice, land ice, these are features that reflect radiation back to space. And in the case of land ice, as it melts, adds to sea level. Atmospheric chemistry, aerosols, which are particles in the atmosphere that reflect sunlight back, a resolved stratosphere to get, again, a proper dynamic response. And if you're actually using the model to calculate how CO2 will change, you need a whole carbon model. These are now called Earth system models. However, these are a lot of areas, and this is way more than the small civil service staff at GISS was capable of knowing. And so GISS started adding Columbia researchers, postdoctoral fellows, graduate students, and contractors. In addition, the GISS scientists had to work with specialists in other fields. I mean, if you're really working with vegetation, it helps a lot to know how the vegetation really works as opposed to something an atmospheric dynamicist might come up with. And therefore, there were a lot of interactions with Columbia University, the different departments at Columbia, also with universities in the metropolitan area, City College, NYU, Stony Brook, and with different government agencies. So while this is a NASA place, we got grants from a number of different government agencies who were more specialized or focused on other aspects than what NASA would have done naturally in terms of trying to build a more realistic model. Now, so let's say you have a model, but how well does it work? Well, in particular, we weren't interested in just how well does it work to see what things are like now. We needed to know what its sensitivity was like. If climate was going to change, we needed to know whether the model had the right sensitivity to variation and to change rather than just a static situation. So one of the ways to do that was to try to see how the surface air temperature has changed as a function of time. And Jim Hansen put together a record from ground-based observations, a lot on land, but also from ships all around the world, to try to understand how the surface air temperature has changed over time. And as you can see in this record, established back to 1880, where the gray on the charts indicate the estimated uncertainty in the temperature, global temperature. You can see that the unambiguous rise starting in the early 1900s is indicative of what is actually happening. This is one of 3 such records. NOAA also has a record, and the UK has a record, and they're pretty much like this record. So you have to ask, can your climate model reproduce this record based on what we think has happened to greenhouse gases and volcanoes and the sun over time? So this was one way to assess how well the model was doing. Another way was to look at remote sensing observations of the atmosphere as a whole. For one thing, GISS scientists, led by Bill Rossow, put together the ISCCP assessment of cloud cover around the Earth using a variety of satellites from different countries. And that was a tricky situation because scientists have satellites have different sensitivities. They have different ways of recording the data. All of that had to be combined in a uniform way to understand what cloud cover was, because cloud cover changes can really affect the climate. Other satellites like SAGE-2 measured stratospheric and even tropospheric water vapor, aerosols, ozone, things that, again, were potential perturbations of climate. So looking not only at the surface, but at the atmosphere as well. All of these were then parts of the picture to assess how good your model is in not only reproducing what we see now, but the changes that people have estimated have happened. Then also, you could look at paleoclimate time periods, the last glacial maximum, 18,000 years ago, the warm climates of the Mesozoic, millions of years ago. How well could your model reproduce the very uncertain observations for those time periods, or at least try to estimate, could we reach that degree of warmth with the magnitude of CO2 that we're putting into the model? So GISS now uses its climate research and climate model to assess how climate may change in the future, depending on the various possible scenarios of CO2 and other trace gas releases. And that obviously depends upon choices mankind makes. To model past climates dating back millions of years to gauge how sensitive the Earth's climate has been to various forcings. To model the atmospheres of other planets in our solar system, so sneaking back into planetary science. To broaden our understanding of the different ways in which these atmospheres can work, and interacting with various observations from NASA and others to better understand what's going on these planets. A relatively recent issue has been to study exoplanets that are now being observed with the concept of astrobiology, to see if one can assess which planets with which atmospheres could produce climates that are conducive to the type of life we understand. Doesn't mean there isn't other type, but this is still in an abstract way, but then one also uses the model and understanding to look at the impacts of climate change on societies and global habitability. And GISS has had a very active climate impacts group for a number of decades, working on cities, agriculture, general ecosystems. In addition, being in New York City, GISS has coordinated with New York in its preparation for climate change following what happened with hurricanes and various other things, and even things like flooding due to heavy rains in the subway. And GISS has set up for many years now programs to train high school and undergraduates from various schools throughout the city, some with disadvantaged backgrounds, to understand what it's like to be a scientist, to learn about climate, and to learn about the potential problems that increasing greenhouse gases are causing. So in conclusion, over 4 decades, and so starting in 1981 with Jim's paper, GISS scientists have built the expertise to explore the climate system on Earth and other planets with state-of-the-art numerical models and observations from both satellites and ground-based measurements. GISS personnel have worked with various academic institutions in New York, especially with Columbia, in both research and educational activities. GISS scientists have contributed to numerous US government reports, such as the State of the Climate System in the US, also on regional and urban impacts of climate change, and also intergovernment reports like the Intergovernmental Panel on Climate Change has had numerous GISS scientists over the years. In recognizing the problems early, helped with the perspective of Venus and focusing on what was needed to advance our understanding, building a model, adding the different components to the model, getting necessary observations to see how well it was working. GISS became one of the leading centers for climate research. And it's fair to say it's influenced the discussion of climate change and its potential impact in the US and around the globe. Now, as was said, we are being kicked out of our place because it turned out that the lease, which an independent panel said was very economical, was not economical enough for the new administration. And we were told that in the next few months, they will try to find a home for us. It's possible they won't, at which point this retrospective will be a complete story. Hopefully that's not the case, but we'll see what happens. Okay, thank you.
Thank you so much, David. That was amazing, and it's just incredible to see how GISS has been at the forefront of climate science and climate modeling really since the inception. This is incredible.
That's remarkable. We had a quick question in the chat about the temperatures being used for a lot of the graphs, whether or not it was Celsius, Fahrenheit, or Kelvin.
Those are Celsius temperatures.
Sweet. Thank you.
Yeah, and we've got time now for a few questions. So if anyone wants to put questions in the chat for David, we've got a question from David Gordon, I can put this up on the screen. So it says, who owns the model and the data? Is it possible for this to be destroyed by the federal government?
Well, actually, the model and the data are the property of the people of the United States, because this was funded with government money. We have been trying to back up the model and back up the data in case there are nefarious elements that would like to destroy it. But it is the property of the people of the United States.
Sweet. Are there any other comments in the chat? Andrew, do you see any? Let's see.
Don't see anything right now, but I mean, another question just more generally is like, so we have these models which can be used to predict climate change. So do we know like how much it'll warm in the future? Do we know how fast it's going to warm?
Well, I think the current feeling, I mean, obviously this depends upon what the trace gas emissions are in the future, and that depends upon what people decide to do now in terms of minimizing trace gas releases from energy and transportation, things of that nature. But I'd say looking at the path that we're on right now in terms of the energy usage, I would say 3-degree warming by the year 2100 is certainly not out of the question. If you remember, most people said, and this included biologists, that once you get above 1.5 degrees centigrade warming, it's disaster for wide areas of the globe in terms of habitability for plants and animals. In addition, you're starting to increase the likelihood of melting ice off land, the big land glaciers, which are happening already. 3 degrees centigrade would be some quite different planet. My personal feeling is that sea level rise has been underestimated. You may have seen recent discussion about the Thwaites Glacier in Antarctica and how it's looking dangerously unstable. To put it in perspective, during the 20th century, the sea level, due to the warming that occurred, was about 10 inches higher than it had been previously. If the Thwaites Glacier by itself melted and went into the ocean, that would raise sea level by 2 feet. And as people have pointed out, the Thwaites Glacier and the associated ice shelf regions help buttress West Antarctic ice sheet, which people have found in the previous interglacial, a lot of that had gone into the sea. If the West Antarctic ice sheet went into the ocean, that's 12 feet of sea level. And people have actually produced maps of what would be left. I mean, Ireland, forget it, no more future people from Ireland. Even the 2 feet rise would be tremendously destabilizing for good portions of the coastal US. So if the path we're on now for a 3 degrees centigrade rise by 2100, that will be a very, very different world than what we have now.
Thanks for sharing that. And we have another question from Henri Drake, who asks, so the GISS model made predictions back in the 80s. Were they accurate?
The GISS model back in the 80s had a climate sensitivity to increasing CO2 of 4 degrees centigrade. Right now, the best guess is that the proper value is around 3 degrees centigrade. So the value at that time, I think, probably overestimated the sensitivity of the system. Even the 3 degrees centigrade value is not really known. In the last IPCC report, several of the models, including the Hadley Center model and NCAR, very respected models, had sensitivities close to 5 degrees C. I think all of the evidence suggests 3 degrees C. One of the comments about what was predicted in that 1981 paper and also an 88 paper for what would happen, there were 3 scenarios chosen. The high scenario was a business as usual, which people thought that's not going to happen, because as soon as people understand the threat that this would cause to habitability and even economies, people will try to minimize greenhouse gas emissions. And then there were 2 others. Well, it's turned out that the business as usual scenario is a slight underestimate of what has actually happened. So our ability to predict what man does is even worse than our ability to predict what the physical system will be doing.
That is pretty sobering. Yeah. I think maybe we have time for just like one more quick question before we move on to the next speaker, because there are a few comments that are echoing the same theme here, and which are, will GISS continue to operate in the interim while it seeks a new home? Will the climate work of GISS continue even in the absence of a building?
Yes. So NASA has allowed the civil servants and the contractors, and Columbia has been, GISS is composed of a mixture of all these diverse elements. Columbia has allowed, in a way, people to work remotely to some degree. So people will be working remotely. They have places at different portions of Columbia where they either have a desk or can have a meeting, or they work from home like was done during the pandemic. As long as we have access to the computers at Goddard Space Flight Center, the climate model can be run, the science can be done. It's better to have personal interaction so that you can sort of delve into things. But it happened during the pandemic and things went all right. This procedure will stay up until the end of September, by which point they, air quotes, hope to have a new place for us. But if they don't, then there's nothing guaranteed as to what will happen after that. And so I guess we'll see. So the answer to the question is, in the interim, to the end of September, I think the science, to whatever extent, can still be done.
That's good news to hear, but troubling. Thank you so much, David. I think we're going to move on to our next speaker. So for those who just joined the stream, just a brief introduction from me and Andrew. I just want to say hello to everybody. Thank you for joining us in hour 0.5 of the Weather and Climate live stream. Only 99.5 hours to go. So we're making good progress.
No, we're almost there, right?
Yeah. My name is Sil. I'm a first-year PhD student studying at NASA GISS, and I am your co-host.
And I'm Andrew Williams. I'm a climate scientist at Princeton, and I'm also your co-host. We have another great few hours of weather and climate science coming up for you now. But before we dive into that, we just want to remind people again about why we're here on your screens.
Yeah, so we all know how important weather and climate forecasts are to us as individuals and everyone else in this country. And luckily, the United States has long been a world leader in weather and climate prediction.
Yeah, that's right. We developed the first weatherized climate forecasts in weather forecasts in the US. And that's to help you know what the weather is going to be in the coming weeks. and also to understand how carbon pollution is going to impact the Earth over the coming decades.
And to make these forecasts work, the United States has in its history created an unparalleled network of observations, kind of as David was mentioning, using everything from weather stations to satellites to planes, balloons, boats, floats, you name it. And the resulting forecasting and observation system is a true scientific miracle when you really look at it from a big picture. And we're really excited to share some of that miracle here today on this stream and over the next few days.
Yeah, this miracle is like what we've managed to achieve as a community has really pushed the bounds of what we thought possible. And this miracle was made possible by decades of investment by the American public, by you guys. But as we heard in recent weeks, funding cuts have put this miracle at risk. There are weather stations out there which are so short-staffed that we're losing this observational coverage that we need to keep our models grounded in reality, and these are already hurting our forecasts. There are laboratories out there like NASA GISS, there are others like them who are focused on understanding the future of our planet, of Earth, who are all having their funding threatened and are being closed or shrunk.
Exactly. And, it doesn't really have to be this way. I think if you like what you see here, then you can use the link on the screen to contact your representatives and voice your concern about American forecasting, and really help keep the light on weather and climate science and keep the momentum going in the United States and keep this miracle alive of forecasting. And either way, we hope that you learn something today and over the next few days. I got to start saying a few days. Hopefully you learn something over the next few days about weather and climate. And please feel free to ask questions about science. We're going to do our absolute best to get those to the speakers. Speaking of speakers, we have a new speaker, Marcus, who will be joining us. And Marcus is a Columbia and NASA GISS scientist. And the talk today that Marcus is going to give is titled Using Observation to Improve Climate Predictions. So I guess give it up for Marcus wherever you are.
Yeah, thanks. And thanks for having me. And sorry that the title here is slightly different, but it's basically the same meaning. Basically, I want to talk a little bit about, the impact and value of observations and basically putting a number on that, being able to give some sort of guidance into what the value of a potential new satellite might be, specifically as it relates to the societal impact of the sort of predictions that we do. So this is the title slide. You can see all these little logos and stuff. This is kind of equivalent of like in NASCAR where you got your BF Goodwrench and frame auto filters. Anyways, moving on. So what is the value or impact of an observation? So NASA, NOAA, other agencies send satellites into outer space to look at the Earth. And what's the value or impact of that observation? Well, we can maybe break this down in a few different ways. So maybe there's 3 different ways we can talk about what that means. And the first might be sort of a basic information, like how hard is it raining? So there are satellites that are measuring rain rate, or they might measure aspects of the clouds or temperature or humidity and so forth all over the globe. Okay, another one might be for numerical weather prediction. So the sort of models that go into your forecast that you get like every single day. Is it going to rain? What's the temperature going to be? Is it going to be windy? These models, these numerical weather prediction models, depend on a constant stream of information that's assimilated into them in a process called data assimilation. And there, the main uncertainty is basically how are we starting up the model? So the model has to kind of get booted with a certain value of the atmosphere. And that's sort of a critical element and the main component of uncertainty in making these sort of weather forecasts. All right, now if we move on to larger timescales, so years, decades, centuries, we want to know what the Earth is doing on these climatological timescales. We really have to hang our hat on our knowledge of the physics. We have to say, well, based on our knowledge of the physics, what's going to happen on these timescales? Also, sort of beyond the timescale of a decade or two, another thing that matters is what sort of emissions are we going to put into the atmosphere, right? What's the forcing going to be? So in other words, if we put in a lot of dust into the air, maybe that will reflect light in a certain way. Maybe some brown carbon will absorb light in a certain way. maybe carbon dioxide will go into the atmosphere, and that carbon dioxide will have its own radiative effect, greenhouse effect, which will affect how the whole Earth system behaves. So there's sort of those uncertainties at the Earth system model scale. I really want to talk mostly about this physics uncertainty. So that's sort of my area of expertise or concern. How do we use observations to improve our understanding of that physics uncertainty? So this is basically just a little plot that shows with on the x-axis is sort of time scale of prediction, and then these different colors show what's the contributing source of uncertainty for a prediction. So at the short time scales, it's sort of this internal variability, this initial condition uncertainty. At medium time scales, and actually really at all time scales, that model physics error in blue is a huge contributing factor. And as we get to really long time scales, what are our missions going to be is something that becomes sort of a dominant source of error. Okay, so putting a number on value. So when we're thinking about value, what is the value overall of making these predictions? Well, I'm not sure I'm qualified to do that, but there are papers on this. There's research on this by economists who have pegged the number as high as $10 trillion. So that's a huge number, right? That's sort of the aggregated value of being able to have a prediction of what the climate's going to do, how the climate is going to respond to humans' activities, and so forth. Looking a little bit more granularly, a researcher here at NASA GISS, Alex Rind, has come up with a number of metrics called climatic impact drivers. So these are various metrics, things such as heat waves and droughts that are societally relevant, and they are things that we can predict with our models. And so there's a whole sort of flow chart on how to derive these climatic impact drivers or choose them. I won't go into it. It's a little bit complicated, but the main point is that there's a number of these metrics that we can relate to our models and that we can predict with our models. So this is another thing that is highly valuable, right? These are things that we can go to a farmer and say, hey, like this is what droughts might do in the next 30 years. Or we can go to investment agencies or insurance companies who might like to have this sort of long-term planning information. Okay, so one example, all right, agriculture needs water. I'm picking California, that's where I grew up. I grew up in an agricultural area of California, and here's an example of all the agriculture that happens in California, right? Produces 90% of the world's almonds. I was actually kind of shocked about that. 90% of US grown avocados, almost all US broccoli, so on and so forth. And they need these sort of predictions to make choices on their water management, right? Do we let water out of our dams? How do we manage all of the supplies that go into irrigation? Okay, to give another example, maybe make this bipartisan and pick a red state. Here's Texas. So here's a plan for water for Texas from 2022. And this one page in it, this is all available online, freely available. Uncertainty of our future water supply. So this really caught my eye. I'm really into uncertainty. It's a big part of what I do, quantifying uncertainty. So this page really caught my eye. And specifically, I zoomed in on this little section here that says there isn't much agreement among climate models or scientists about the nature of long-term changes to water resources in Texas, and no forecasting tools capable of providing quantitative certainty about future water resources in Texas at the resolution needed for water planning. However, efforts to improve technical capabilities and address uncertainty are in progress. So I think this is a really provocative statement for me, and is really something that motivates a lot of the work that we do. So we are exactly trying to produce these capabilities and try to make these capabilities much stronger. So I'll get into that a little bit here. Okay, so until recently, we have not had a methodology to quantify Earth system model physics uncertainty. When I say Earth system model, I mean these global models of the Earth system that are able to make predictions on the scale of decades and centuries and so forth. Okay, what are the causes of these uncertainties? Well, if you look at what these models are doing, they're basically predicting things in the atmosphere, things in the ocean, on the land surface, and so on, vegetation, chemistry. And if we just look at something like a cloud, right? Here's a picture of a cloud and a weather model, a numerical weather model that provides your forecasts day in and day out. Might have a grid scale that can resolve some, but not all of these features. A Earth system model, a climate model, might have a grid scale that cannot actually even resolve the cloud itself. So in the size of its grid box, multiple clouds might exist. What this means is that we basically have to represent the population of clouds statistically. That statistical representation of clouds requires a lot of analysis of what clouds look like and might require some approximations, and there might be uncertainty in that. There might be some uncertainty in what the numbers that we use, the parameters that we use to characterize that statistical distribution to make sure that it matches, works well across the globe, right? The clouds, the population of clouds in the Amazon is going to be different than what it looks like in Oklahoma. So that takes a lot of work and contributes uncertainty. All right, even inside of clouds, we have other uncertainties, right? So even if we could get a picture, we could resolve a cloud that we see with our models. Clouds are made up of populations of droplets, and some of these droplets are large, some of them are small, right? We might have a large raindrop, a small cloud droplet, we might have a drizzle droplet somewhere in between. And this is another thing that we have to represent statistically. So I'll just sort of skip over this last image here. And well, how do we get at this? A recent solution that we've been looking at, that I've been working with, is parameter estimation. So this is basically trying to get a better quantitative estimate of some of these numbers that go into representing these processes in our Earth system models. And we use ensembles, that means running the model many hundreds or thousands of times. Emulators, I'll talk a little bit about that, and statistical sampling. So basically what we want to do is use Bayesian statistics, which is sort of the gold standard of how we address uncertainty with statistics, to estimate not only the value of the parameters, but also the uncertainty in them. So this is producing a probability density over the range of parameters. We don't just have a single number, we have some uncertainty there, some ranges. And I should say, this is constrained by observations, right? This isn't just in a vacuum. This is informed by all the observations that we have. So we've come up with a process to do this. Basically, this is really hard because these statistical methods for estimating parameters, you have to usually run your model thousands or even millions of times. Climate models are extremely expensive, and by expensive, I mean they take a long time to run on really big computers. So we need to speed up this process somehow, and we use machine learning. So we train a model surrogate that fits into this process, by which we constrain the model, we estimate our parameters using available observations. And these observations are things like satellites, NASA satellites or NOAA satellites in outer space. Okay, we have a paper on this. If you're interested, you can grab this QR code and look at it online. And basically, what's the value of this? The value of this is that without constraining with observations, if we just look at our uncertainty, we have a wide range of uncertainty in various values that our model might predict. So this value is basically how much light the Earth is absorbing from the sun. And we know a lot of these values are not in agreement with our knowledge. Our knowledge is sort of this bounds right here in this blue box. After we apply our constraint, we're sort of within this box. And the important thing here is that this isn't a single model. This isn't a single number that we're getting out. We're getting a number of them. So we still have an estimate of uncertainty in our model. What just happened? I hit the wrong key, I think. Oops. Oh, thank you so much. Okay, I will just skip over this, except to say that, yeah, I'm just going to skip over this in the interest of time. We also do this in high resolution models, I'll say. So we want to connect sort of the knowledge that we have on the globe to higher resolution. And I'll skip over this as well in the interest of time. Hunt me down and ask me about this, and I'll talk your ear off. I would love to do that. Okay, so how do we talk about reducing uncertainty of our Earth system models, and how do we talk about the value of a new observation? Well, one way is in the sort of way that I've been talking about in terms of parameters. So this is just a schematic. This isn't actual data. We might consider like, that we get this estimate of our parameter values, right? It's like a little histogram that tells us, well, this is the most likely value, and maybe these are less likely values, and so on. And then we can imagine we get a new observation, right? A new NASA satellite is sent out into outer space. And then we can quantify basically how much we've reduced our uncertainty. Now, this is great, but it's only really of relevance to climate nerds like me, right? Who know what these parameters are. Similarly, we can look at what the outputs of these models are. Things like how much water is in the atmosphere and how much radiation is the Earth absorbing. And right, we can move from these black dots, which is sort of our prior knowledge, to our constrained values, which are these green dots. And that's great. Again, this is probably mostly relevant to climate nerds. Now, here's where we would like to move to. We'd like to move to basically putting this in terms of things that matter to people, things that matter to farmers, things that matter to investment agencies. So things like, so equilibrium climate sensitivity, that's probably still of relevance to climate nerds, but that's how much warming we'll get if we double CO2. But also things like the prevalence of heat waves. How often are we likely to see heat waves around the globe? Or late frost. And we want to see basically when we add a new observation, how is it constraining these values? How are we getting less uncertainty in these estimates? So we've done this. We've basically played around with this. We've tested out a simulation of a satellite. We pretended that NASA put a new satellite in outer space that can measure these things. And we're able to quantify basically how much our uncertainty has reduced in a lot of these variables. I won't go into the details there. And this is basically the framework that we want to do. We want to be able to translate that reduction in uncertainty to be able to say, if you put a satellite into outer space, this is how much better I'm going to be able to tell you about heat waves or frost and so forth. And yeah, we've submitted a manuscript on this. Hopefully it'll end up in press soon. And we've tested this out. These are, again, climate scientist nerdy numbers. We can just maybe skip over this, except to say that we constrain uncertainty in very climate important things like equilibrium climate sensitivity. Okay, and this fits into sort of overall NASA effort of Earth Science to Action, where we want to connect basically guidance for NASA missions, so new satellites and so forth, to a lot of the basic science of how the Earth works. To these sort of climate impact decisions. And I'll say that basically in closing, that government-funded science is open, collaborative, and innovative. And really, we need government support to do this sort of innovative science and to do this sort of collaborative science. We need to be able to connect satellite observation experts to Earth system model experts, and then in the middle, also be able to fit in mathematicians, statisticians, and machine learning experts. So that's really important. And really, all of this work is in service to the US people. It's in service to industry, to business, to agriculture. If every farmer or investment company or insurance company had to hire their own climate scientists, it'd be a massive waste of money. The government provides this as a service to increase productivity and to save lives, really. And so I'll finish with that. Here's a bunch of nerdy conclusions. And yeah, thank you.
Thank you so much, Marcus. That was amazing. That was incredible. We do have some questions in the chat if you have a second. We have one question from Hannah Liddy, who asks, GISS research continues to push the boundaries of climate science. What frontiers do you envision emerging in the coming decades?
Well, I'll just talk about what I'm really excited by. I'm really excited about stitching together insights from different scales. So there's a lot of research that goes into flying airplanes into clouds. I know a guy who sends balloons into ice clouds and captures ice crystals and looks at them through an electron microscope. His name is Nate McGee. And being able to connect that sort of stuff to weather models that predict, thunderstorms, and then connect that to climate models and basically have that knowledge linked through is incredibly exciting. And there is like a statistical formalism for this. And so, yeah, we're just really excited about doing that sort of thing. At least I am.
That's awesome. We all have our like things that we just zone in on. That's what makes us good scientists, We have a question from Jeff, which I think is related to some of the work that you talked about. So basically, how will clouds change in a warming world?
Right. Yeah. So there's been a lot of research on this, and I think one of my slides had a cloud feedback, and so basically that is this this aspect of will we have what's sort of the feedback effect as we warm? Will we get more clouds or less clouds? It can be very complicated, and it can sort of fit into the circulation of the Earth. If you have subsiding air in the Earth, so if you get big circulations and those circulations change, subsiding air can warm and dry an atmospheric layer that can produce fewer clouds. And so there's been a lot of work, especially on, if you've ever been to California, to San Francisco in the summertime and experienced those horrible foggy clouds, that's like one of my main topics of research. But those things are incredibly important for clouds, and those are one of the things that really factor into how clouds change with the warming climate. And they also factor into a lot of these large-scale circulations. So the full answer is pretty complicated, but basically you have to look at the full Earth system. The answer isn't always obvious. There's a lot of subtle feedbacks and sort of connections between different parts of the Earth system.
Amazing. Marcus, I had a quick question. What's your favorite type of cloud?
You know, I work with that sort of boring marine stratocumulus so much right now. I really should pick that, but I have to say cumulonimbus, absolutely. Like I just absolutely love a good cumulonimbus. I used to live in Florida, and I had an apartment that faced the interior where thunderstorms would build every day in the summer, and it was heaven. I loved it.
I love it. I agree with that. All right. Thank you so much, Marcus. I think we're going to try to move on. Is that right, Andrew?
Yeah.
That was incredible. Andrew, do we have another call we want to go through, a call sign?
Yeah, let's go through it one more time. Just keep everyone, remind everyone why we're here. So yeah, just the number of participants that we have, like the number of people watching the live stream, I just see it ticking up and up. This is incredible. You guys just share it. Like if you're watching it, like start a watch party, get a room of people together, get some popcorn, or share it with your friends. This is incredible energy. Thank you so much.
Absolutely remarkable. I'm inspired. I'm getting chills like every 5 seconds.
We could just quickly remind people why we're here though. So, the reason that we're here is because we want to try and remind you of how important the weather and climate forecasts we have are, and to show you what climate scientists are actually doing. And these weather and climate forecasts are important to everyone in the country. And the United States has really been at the forefront of weather and climate research ever since its inception.
Yeah, that's right. And, the United States was the first to develop computerized weather forecasts, which is something I didn't know until recently. And, these forecasts, as we all experience, help us know what type of rain is going to fall later in the day, or what kind of nice weather is going to happen later in the week. And also the US made the first computer models for climate impacts and carbon pollution. Forecasts we don't interact with as much in our everyday life, but equally have important impacts to the American family. So farmers, as we've heard, can know what types of crops to plant to prepare, and a plethora of other important impacts.
100%. We like these forecasts that we've made, we need to put data into them. We need to feed them real world information. And like David said in a couple of talks ago, we have this information from various different sources. We have floats in the ocean, which are going up and down, measuring temperature. We have satellites going around the Earth, which are looking at these beautiful clouds that Marcus and others study. And this observational system and the forecasts that we create are a real miracle of science. It's incredible how we as a community have managed to push forward the boundary of this knowledge. And that's really one of the reasons why we're doing this live stream, is to share some of this miracle with you guys, give you an insight into what we've managed to do.
Exactly. And it's not possible. None of this is possible without support from the American public and investment by the United States government, which also we need to acknowledge that, in recent months, there have been a lot of funding cuts that put the future of the United States leading this effort globally at risk. And so, weather stations are short-staffed, so we're losing some observational coverage and forecasting coverage, and laboratories dedicated to understanding climate future are being, reduced in size or kicked out of their buildings, such as the case now actually at NASA GISS, which for those who are joining now, we're actually streaming these talks from NASA GISS, which is a very famous climate forecasting institution in the United States. And we're streaming them there while GISS has its final few hours. So at the end of working hours today, GISS will be permanently closed as a building for its research purposes, and all of the employees there working on creating climate models will be a climate model will be full-time remote indefinitely. So that also is something we want to keep in mind here.
100%. And yeah, these cuts and the threats to science, it doesn't have to be this way. We're hoping that if you guys like what you see, you can see the value in what we do and what the people at GISS and other institutions do. We'd love for you to contact your representatives and tell them to save our forecasts. So if you go to wclivestream.com/act, you can contact and call your representatives. And we really want to keep this miracle alive. We want to keep the lights on for weather and climate science. And if that doesn't resonate with you, we still hope that you learned something. We still hope you got an insight into what we as climate scientists do. And yeah, keep the questions coming. We got loads of questions in the chat, almost 700 people here. And I think we just ticked over hour 1.
Let's go. 99 to go. This is pretty good.
Exactly.
We need like some confetti sound effects. I don't know if we have.
Yeah,
I don't know how to do that.
Yeah,
we can imagine it.
Director person, we need this.
Yeah. So we are 1 hour done. Just to clarify for all the viewers, 1 hour done. 99 straight hours to go. So that means if tomorrow night you are waking up at 3 a.m. and you're like, don't know what to do, you can turn on this exact same stream and there will be scientists communicating their research.
Yep. They will be a lot more tired than we are now, a lot more, more caffeinated, but we'll be here.
Yeah. This is the easy shift. This is awesome.
Easy shift.
Andrew, do you want to introduce our next speaker?
Yeah, so our next speaker is Casey Ivanovich. She's a postdoctoral fellow at NASA GISS, and she's going to be talking about separating the role of temperature and humidity in driving extreme heat stress conditions. So thank you, Casey. The floor is yours.
Wonderful. Yeah, thanks so much, Andrew and Sil, for keeping up the good energy. I'm really excited to be a part of today's event. I think it's a great way to kind of celebrate all of the work that's been done, funded by the federal government, and its importance to society, and of course, in this first kind of stretch, to honor the work that's been done at NASA GISS over the past 60 years or so. And so also thank you to David for earlier in the day doing that overview of the history and really kicking us off. So my name's Casey Ivanovich. I'm a postdoctoral fellow at the NASA Goddard Institute for Space Studies, or NASA GISS. And as a postdoctoral fellow, I'm fully funded by the federal government through a fellowship grant that I won last year. And in the proposal for that grant, I wrote that I was going to study when and why extreme humid heat events occur in order to better prepare for their human health and sort of cascading socioeconomic impacts. So this is the work that I'm currently working through. It's an extension directly of my dissertation research, which I completed last July. And in those 5 years as well, I was fully funded by the federal government. So really emphasizing how far-reaching these types of grants are and supporting this type of science. So today I'm excited to talk through some of the focus of my previous and current work. So when you hear the phrase climate extremes, what typically comes to mind? I think a lot of times people think of these very epic and dramatic events, things that are very fast-paced. They're wiping out everything in sight with tons of destruction. So you might think of a tornado, you might think of a hurricane, massive flooding, these things that you can see. But in reality, in the United States, the climate extreme with the greatest mortality impact is extreme heat. And so this is something that's inherently sort of silent but deadly. You can't see it, but you can definitely feel it. And mortality is certainly sort of the most important and the most jarring impact of extreme heat, but there's countless other aspects of society that are affected by this hazard. So there's other human health outcomes, such as maternal health and inducing preterm labor. Productivity in outdoor work is going to be limited in industries like agriculture and construction work, as the hours during which it's safe to perform outdoor labor is going to be limited during extreme heat. And this, of course, is also going to directly impact crop yields, as people are going to be limited in the times during which they're able to work in agricultural settings, but also there are direct impacts on crop health itself. And so these ecosystems and direct plant health are also threatened. There's also increased energy demand during heat waves associated with the increased use of artificial cooling and air conditioning. And even farther reaching impacts like disruptions to transportation, things like roads buckling and airplanes not being able to get enough lift in the runway length when the temperatures are very high. So this is just a very small sample of the wide array of ways that extreme heat can impact us as humans and sort of society at large. But of course, the biggest impact is directly on human health. And when we think about the human health impacts, we really need to focus on both the temperature and the humidity. And so the reason for this is that the primary way we cool our bodies down is through the evaporation of sweat off the surface of our skin. So you can look at this diagram on the right, which is showing that sweat comes out of your sweat glands onto the surface of your skin. It's that liquid water that is evaporated, and that has a net cooling effect on the air and on our skin temperature. And so it turns out that this is responsible for about 75% of the way that we cool our bodies down. And you can see this in the schematic on the left, showing the different interchange of heat with our environment. So when the temperature and the humidity rise, this means that this evaporation process becomes less efficient. And at certain thresholds of humid heat, our bodies can no longer shed heat at all. We start to have our internal core temperatures rise, and we experience heat stress. And so we've known sort of physiologically how these systems work for decades. And there have been some recent advancements in physiology that are able to take that kind of theoretical understanding and show in a lab setting that it does indeed have these kinds of effects. So physiologists do these sort of heat chamber studies, which they take a person, they put them in this kind of sealed box, they crank up the temperature, they fluctuate the humidity, and they see how bodies react. And it's through these types of analyses that we're able to really identify that humidity does matter. So at a given temperature, when we increase the humidity, a body experiences heat stress faster and experiences the impacts at a much higher rate. And so understanding from a climate perspective when and why these types of events occurs is becoming increasingly important. And this is because we know that conditions that are quite rare in today's climate are going to become much more frequent in the future. So this figure is showing a metric called heat index, which might be familiar to lots of people online. And it's a joint metric of temperature and humidity. And so this is a feels like temperature, which tells us, when you check the weather for the day and it says, oh, it's 80 degrees outside, but it feels like 90 degrees, that could be heat index. That's an example of these types of feels like metrics. So taking that joint heat stress metric and looking at sort of the frequency of extreme events that are only happening once per year in our present climate. By year 2080, under a high emission scenario, these events are going to become much more frequent. So this is showing how many times in a month or how many months are surpassing that threshold. And so we see that the highest increases are happening around the tropics and subtropics, places which already experience very high levels of extreme heat and very frequent dangerous thresholds. And so there's plenty of urgency in terms of understanding why these events occur. And from a sort of climate perspective, differentiating between dry and humid heat specifically is very important because where these events occur, when they occur, and through what mechanisms can all be different for dry and humid heat. So this figure is showing us the 95th percentile of dry heat on the top and humid heat on the bottom, essentially just showing us how hot is it in an extreme event at each individual location. And so what we can see is that there are some similarities, but there are quite a few differences. So extreme dry heat occurs mostly in desert regions and in low latitudes, while humid heat is much more widespread throughout the tropics and subtropics and even over ocean. Some deserts actually have pretty low humid heat events because they're so dry. And there are also some regions that experience very high thresholds of both types of heat extremes. And so this could be South Asia or Western Mexico, for example. So I think these figures give us kind of a snapshot of the major extreme heat hotspots, but we also have to think about how the exposure to extreme heat can vary across space and time. So these variations have really large impacts, not only for exposure to extreme heat, but also for the impacts on human health. And a couple examples of this, one is in temporal compounding. This is essentially to say we can imagine that we have 7 days of extreme heat in a given month. If those extreme heat days, so days that cross this kind of temperature threshold shown in the figure on the left, by this horizontal line, then if all of those events are happening in quick succession, if they're kind of squeezed together without many breaks in between, that's much worse for human health impacts because a body can't really recover in between and get any rest from those stress conditions. And that's in comparison to if these dates were kind of spread equally over the month. And so, unfortunately, as our climate continues to warm, hitting these really dangerous thresholds of extreme heat is going to be a little bit easier. And so this means that the frequency of these types of temporally compounded extremes will increase in the future. And we've also seen how sort of spatial variation can drive differences in sort of regional exposure to extreme heat on the previous slides, but this is also true on a really localized level. So one example of this is through what we call the urban heat island effect. And so this is describing a phenomenon where we have in a relatively small sort of region having higher temperatures at the surface in urban areas in comparison to the surrounding rural areas. And so there's a couple of reasons for why we think this occurs. The first is that in sort of urban regions, we have, much more dark color materials, things like asphalt and steel. And these are absorbing a lot more sunlight, which is then going to heat things up and increase the local temperatures. At the same time, in rural areas, we have much more vegetation, and this vegetation, sort of trees and grasses, are going through a process called evapotranspiration, which is releasing water vapor into the atmosphere. And so this, in a similar way to how we cool our bodies down through sweating, is going to cool down the surface of the planet. This vegetation also is increasing shading, which is going to reduce temperatures. It's also holding on to more water in the soil, and all of these are going to have a net cooling effect. So together, this kind of differentiates the heat experienced in sort of cities versus surrounding rural areas. But something you might have noticed as I'm talking through some of these mechanisms is that many of the things that are cooling down the surface are also increasing the humidity. So as evapotranspiration is taking place, or as the soils are holding on to more moisture and having evaporation take place, that is going to reduce the local temperatures, but it's also going to increase the local specific humidity. And so a new sort of concept that's coming about is comparing this sort of urban heat island with when we take into account the effect of humidity. And so this is a recent paper that came out in 2022, which is showing the difference in this urban heat island effect on the left when you're just using the surface temperatures. This is something measured directly by a satellite, for example, directly looking at what the temperature is of the ground. And we can see that there is, the red is indicating that the urban locations are hotter on average than the surrounding rural areas. And so this is what we kind of expect when we're just using a temperature-based metric. But when we use heat index, so that joint temperature and humidity metric from before, we're now factoring in the effect of humidity, and we see that there's a huge sort of reduction in the urban heat island effect. And even in some of these locations, we're having a reversal where there's more heat stress experienced in the rural areas because of that additional humidity. So I hope that this example really shows how these trade-offs between temperature and moisture at the surface kind of complicate our understanding of how we can characterize heat stress. And this is especially important when we want to compare how these sort of contributions of temperature and humidity vary across space and time. There's a variety of different factors that can influence temperature and moisture jointly, and this can have different net effects on the humid heat experience at the surface. And so this is something that we really didn't have a good way of describing using traditional metrics. And so we thought, okay, let's make one. So for the rest of the presentation, I'm going to go through a recent project that I did on this topic, trying to get towards this. So extreme humid heat really inherently is this compound climate extreme. It requires some kind of elevation of both temperature and humidity. And because of that, a given threshold of humid heat, let's say a wet bulb temperature of 100 degrees Fahrenheit. This is another joint heat stress metric that is combining both temperature and humidity. So in this situation, we can have very high temperatures in the presence of just a little bit of specific humidity, something we would call a temperature-dependent extreme. Or we can have more moderate temperatures in the presence of plenty of specific humidity, what we would call a humidity-dependent extreme. And so differentiating between these two sort of flavors of heat stress are really important because the impacts and the drivers can be very distinct. And so we didn't have a good way of really quantifying that and describing it in sort of technical terms. But we realized that there exists kind of an analog in oceanography. So oceanographic spice is a metric with a kind of somewhat silly name, which describes the individual contributions of temperature and salinity towards a given seawater density. And so I like this schematic coming from Woods Hole, which is showing the Bay of Bengal, where the seawater density is roughly equal throughout the bay. But on the western side, we have much warmer and saltier water, what we call spicy. And then on the eastern part of the bay, it's much cooler and fresher, what we call minty. So again, these are kind of silly naming conventions, but they're really allowing us to describe, parcel tracing, seeing how movement of water is occurring in a basin with a very similar seawater density, as well as column stability, so kind of vertical movement. And so we were really interested in using this as a kind of framework to understand the temperature and humidity contributions towards a given value of humid heat. So kind of doing this, but in the atmosphere. So in this paper, what we do is we derive this new, what we think of as being comprehensive metric called stickiness. So we're kind of having our, similar cheeky nod to the somewhat silly naming conventions in oceanography. So what we're doing here is deriving an equation for stickiness, which is most sensitive to changes in temperature and specific humidity, but least sensitive to changes in humid heat. And so this might sound a little vague, but really what this is doing is setting up a very strict mathematical equation that we solve for stickiness in terms of temperature and specific humidity. This figure is showing us the result of that derivation, essentially mapping out the values of stickiness at a variety of combinations of temperature and specific humidity. So just to show us what's going on here, on the x-axis or the horizontal axis, we have temperature in degrees Celsius, and on the vertical axis, we have specific humidity in grams per kilogram. These dashed lines are showing us the lines of constant wet bulb temperature, again, this humid heat stress metric. And then the solid lines are showing us the lines of constant stickiness. So essentially, we want this variable to measure the trade-offs in temperature and specific humidity at a given humid heat threshold. So let's just make sure that it works. So I'm going to pick out this 24 degrees Celsius wet bulb temperature threshold, so this line of constant humid heat. And let's say we start at 0 degrees Celsius stickiness. Okay, so remember that point. If we were to increase the specific humidity, but we want to stay on that line of constant wet bulb, this is going to require us to decrease the temperature. And this reflects a net increase in the stickiness. In contrast, if we start at that same 0 mark and we increase the temperature, this requires a decrease in the humidity, and that reflects a net decrease in the stickiness. So I hope that this is somewhat intuitive, that the stickier the air parcel, the more humidity dependent those conditions are. And the less sticky the air, the more temperature dependent. And so the real benefit of having this metric, again, is that we can compare how these kinds of trade-offs occur in space and time. And so here we're going to plot the mean or the average stickiness conditions during all days in the historical record. This is particularly for the June through August season, during just extreme humid heat days, and then the difference between these two, so panel B minus panel A. And there's a couple patterns that immediately emerge. So we see that we have the highest stickiness happening in coastal areas, in monsoon regions, as well as in places that have very high thresholds of humid heat being exceeded rather rapidly. So this is shown by the red contours on each plot. We see the lowest stickiness happening in sort of desert areas, so places like the US Southwest and the Sahara. And I think the most striking is really that third map showing the difference between these two types of days. And so what we can see is that the entire map basically is purple. So this is indicating that conditions during extreme humid heat days tend to be stickier. And this is our first indication that extreme humid heat events on average tend to be humidity-driven events. So they're requiring some kind of influx of humidity in order to occur. And so this is a really helpful tool now that we have in order to understand these kind of universal drivers of extreme humid heat around the globe. So as I continue with my work in my postdoc, I'm really hoping to focus in on some of these physical mechanisms contributing to these types of extremes and exploring how land surface influences the trade-offs between temperature and humidity to affect both dry and humid heat extremes. So I've included this schematic, which is showing just a variety of different mechanisms that are influencing both of these types of heat extremes, things like precipitation and solar insolation, cloudiness, advection, but also things like irrigation, evapotranspiration from that vegetation, land use change, urbanization, et cetera, et cetera. So I'm really interested to consider sort of how this is linked to seasonality. This has a particular impact when we think about extreme events that are happening outside of the heat season, whether that's very early in the spring or very late in the fall, when people might not be acclimated to extreme heat yet or might not be ready to employ sort of management techniques. And I also want to think a lot about how humans are altering these balances. So as we apply more irrigation, how are these different types of heat events affected? Are they becoming more frequent? Are they becoming less frequent? Are they intensified? And how does urbanization sort of balance or shift the balance between our more dry events happening or our more humid events happening? So these are, questions that are directly relevant to extreme heat adaptation and mitigation strategy and have really strong societal influence. And should my funding remain stable, I'm excited to tackle them, but really hoping that this type of work can continue in this capacity, given its direct applications to societal impacts. So I'm really grateful to be here today and to participate in this week's live stream, and I'm happy to take any questions in the meantime.
Thank you so much, Casey. That was a great talk. Thank you. And it's it's pretty hot and humid here in New York today as well, at least for me.
Yeah, I think so. I got my window open. Maybe I'll go close it. That was incredible. Oh my gosh. And learning about all the terms, I had no idea that, I love a fun name.
We have
do we have questions? Did you see that?
We have a really good question from Neil here. I'll put on the screen, which is, are you or your colleagues working with communities or university campuses on building resilience to these extreme heat events?
Yeah, that's a great question. So that's something that we are kind of in early stages of connecting with community members and community groups to really make sure the science that's being produced is as applicable, is as actionable as physically possible. One of the greatest challenges of studying extreme heat as a physical scientist is that you can't necessarily capture all of those behavioral aspects of dealing with these really challenging extreme events. And so it's essential to have people in the room who have experience with the challenges that are happening on the ground, who are working to put adaptation measures into place, and in order to, really ensure that science-based decision-making is happening. So I have a little bit of experience working in the past with different community groups, with different industry members. I've worked a bit with professional sports leagues. I've worked a bit with summer camp administrators, talking about how to make those spaces more resilient, what kind of adaptation measures work better or worse, and especially how to think about these trade-offs between temperature and moisture. But those conversations are so essential to making sure that the results that are being presented from our work are really usable, that the questions we're asking are the right questions. And I look forward to, continuing those kind of collaborations in the future.
Wow. We also have another question in the chat from Henry. It asks, the opposite of spicy is minty. What is the opposite of sticky? And also I should note there's a little bit of a debate in the comments right now. We have some options being thrown out. So what do you think?
Oh, I would love, I can't see those right now, but
I can read them out. We have gluey, we have slippery, we have Teflon-y.
Okay.
Teflon, I think that's it. Yeah.
Loving
so
it.
What do you think?
That's awesome. I think the best recommendation I got was parchy. So if it's really sticky and it's really humid versus it's really parched or crispy. I think there's some good options out there. So definitely keep leaving me suggestions and I'll be sure to work that into the next paper. I appreciate it.
That is awesome. I love it. Are there any more questions or shall we thank Casey?
I think people like crispy. Yeah.
Oh, crispy.
Awesome.
Crispy weather.
Okay. I'll keep that in mind. Thanks.
I love it.
It's radish time. Loves crispy weather.
Yeah, that would definitely be my pick.
Shout out to It's Radish Time. I agree. I love crispy weather as well.
Yeah.
We do have another quick question if there's some time from Haley asking about potential heat adaptations that folks listening here should advocate for.
Yeah, thanks, Haley. That's a great question. So there's a range of different strategies that we can employ. The challenge with humid heat is that because of that interplay between our bodies and the environment, really the only way that we can cool things down is the use of artificial cooling or air conditioning. So that's already a major challenge. So we've talked a lot about sort of future climate change and how we can prepare for that, but access to air conditioning is already so inequitable. It's already like people who have it in their houses might not be able to turn it on when they need it the most. And so I think that is a huge challenge in terms of expanding the use of air conditioning and making sure that people can access it when it's needed the most. So one component of that is, of course, in-home, but also the use of cooling centers. So places that people can go in large groups in order to utilize these kind of public spaces, which would essentially help, provide greater access to this type of adaptation. But there are also that can't really just be our only method, because we can imagine a situation in which, everyone turns on their air conditioning at the same time. That puts way too much stress on our energy grid, and this might lead to sort of blackouts. We could have an extreme, a tropical cyclone, and then maybe that wipes out the power in a given region. And if we have an extreme heat event that follows up, we don't have access to that. And so other adaptation measures we need to employ are sort of relying on changing sort of the surface conditions. So we can use more reflective paints on roofs to help lower the temperatures. We can implement more of that planting vegetation and using green roofs, a variety of different sort of city level, I would say, adaptation measures as well, to make sure that people are as protected under all of these variety of stresses as possible.
That's amazing. Thank you, Casey. I just heard, and I think that we should probably say this on the stream, is that someone from Goddard is at the GISS building and is not letting our one of our organizers back into GISS right now.
Oh my gosh.
Yeah. So
this is breaking news. This is live from New York right here.
Yeah, Miriam is being blocked from coming back into the building.
Are you serious? Okay.
Yeah. So this is really happening right now. It's incredible.
Oh my gosh.
What are we hearing? Let me just.
Oof.
Yeah, I mean, so let's give it a second. So I mean, yeah, we have so many people on this chat who are giving us good vibes now when this is happening. Yeah, this is crazy.
Yeah. Oof. And I guess for viewers that are new, just to update on the situation, is that where we've been streaming and where Casey just presented from is actually from inside NASA Goddard Institute for Space Studies, which is in the Upper West Side in New York, in Manhattan, right above Tom's Restaurant, which you may have seen from Seinfeld. But it's been home to climate research in the U.S. for the past 60 plus years. And recently there was an executive order to shut down the building for climate research, and all the researchers are starting a remote agreement today. And we just got word of the first person who works there who is no longer being allowed in the building. So this is history in the making right here on live.
Yeah, we have people who are now trying to get some more details, and we're going to let you guys know. We're going to see if we can get a picture, like get some video from outside of GISS now, if we can. We'll put that on. Yeah. But I mean, yeah, Sil, you're a PhD student at GISS. What has it been like? What has the vibe been over the past, what is it? It was only a month ago that they found out they were going to get kicked out of the building. This has been so fast. This is insane.
Yeah, it's been a very fast pace. And for me personally, it's been a fascinating first year for a PhD, because right before finals week, so for more context, I'm affiliated with Columbia University's Department of Earth and Environmental Sciences, and my two advisors are at GISS. And so for finals week, we had this meeting at GISS where the news was broke to all the scientists from higher ups at NASA about the building no longer going to be leased by NASA. for this purpose. And, it's quite a time to take final exams after hearing that news. You hear so much of everything on the news, and when it finally hits you, it's pretty heavy. And I will say, my own personal method of dealing with that, I actually went on a 60-mile walk, 60, in one day, starting 6 a.m. and ending midnight around Manhattan. And I actually walked to a different research center and back, just because I was trying to process things. So that was kind of my process. Maybe not the most
not the most healthy, man. Like, see,
maybe not the most. I mean, I enjoy walking. I love walking. I enjoyed it. I've done stuff like that before. But, the point being is that it's difficult to do science in this situation for sure. And Andrew, working at GFDL in Princeton, how has that been for you? And how has the situation evolved for you this past spring?
Yeah, so I mean, for people who are joining, so I'm a scientist at Princeton. I also work at a different government lab called the Geophysical Fluid Dynamics Lab, which is in Princeton, New Jersey. That's a NOAA. So we were live from a NASA lab. GISS, the place I work, is a NOAA lab, but we do very similar stuff. And like GISS and the lab I work at, we both these places build climate models. So people are writing millions of lines of code, taking like all of the equations of physics and stuff we know about the sun and clouds and humidity. We're putting it into a computer, and that's really hard work. Like that takes like a lot of people really focusing on that mission full time, and it's been really hard for people to do that when there's been all this uncertainty around. So people are still turning up to work, people are still trying to do their best, but whether you're taking finals and you're trying to revise for that and study for that, or whether you're trying to write code, like really hard code, then it's difficult. It's people are trying though, and that's the thing. Like we're climate scientists, we're weather people who you're going to see on the stream as well. These are people who study the weather. We're doing this because we love it and we think it's important. So this is what we want to do. We don't we don't want to be getting involved in like these, in unnecessary like politics or anything. We want to do this. We want to do this science and share. And today, that's why we're sharing it with you. Just to say from Henri, like this is a nonpartisan event. Like we're here to up the science and just tell you guys like what we've been doing and try to convince you of the value of it. Right? You just saw Casey's talking about how like this dangerous extreme heat that can happen, like when you get really high temperatures and it's really humid, and understanding that together, and maybe like will climate change will make that worse in some regions, for example. This is what we need to understand. So we hope you guys are convinced of like the value of this.
Yeah, just to reiterate that too, anyone who's speaking, including NASA civil servants or contractors, they're all speaking on their personal behalf right here. They're not through their affiliations, just to reiterate that. And we also have a quick update is that currently people are trying to find a new location for the stream. We have a few more GISS scientists to hear from. However, it will no longer be in the building, I believe. So we will keep you all posted on that. We are getting input. It might be around 30 minutes, but we will keep you posted. It is an updating situation. And let's see what else we have here. So out of curiosity, just we have a minute here. Andrew, you just finished your PhD in 2023? 2023?
Yeah.
What made you interested in science? Why do you love climate science? I mean, how did you find out about this field?
It's a great question. So like I didn't really know you could do climate science as a career, or like, so I really liked science and like science classes when I was young. And so I went to university and I just studied physics. I majored in physics and, went deep into like all of this like really nerdy stuff that we love, quantum mechanics and things like that. And it was only towards the end of my degree that I realized that you could apply all of this stuff I was learning in my undergrad to weather forecasting or to understanding Earth's climate, So like the reason that CO2 causes global warming is because of like quantum mechanics, basically. And so as a physicist, I was like really excited about taking all that stuff I was learning, but applying it to a problem which is just like super relevant and has a lot of societal need behind it. I also did my PhD during COVID. I was a COVID PhD. Pretty wild. But I guess, was your undergrad during COVID? So
yeah, my first year was, especially during the height of it, 2020. Yeah, it was an experience, you know. And
that's why we're so good on camera though, you know.
Yeah, I mean, I didn't know what Zoom was or anything before that. I mean, I don't think most people did. But yeah, it was an experience up in Northwestern Massachusetts, Williams College. They decided to allow people to come to school, but a lot of tests. So like it was like bi-weekly or twice a week tests. So it was quite an experience. And I think by the end of it, you know, it's interesting now. This is maybe a topic viewers can relate with, and one that I cannot believe. But, you know, Zoom is used now for like if it's a snow day or something, you know, if it's a big snowstorm out and then it's like we're going to have Zoom classes. I'm like, I do not like that. If it's a snow day, I want the full day off. You know, I'm an advocate for that. So
that's not fair now.
Yeah.
we have a lot of questions actually from people asking about this, the stream and the details and stuff. So like people asking what part of the live stream is being shut down, just the GISS part. Yes. So just, so we are going to keep going. We're going to be here for another 98 and a half hours, not just us, but 200-300 other people. We will be here. As Henri said, just the live from GISS part is being shut down.
That's right.
We have some information. So there was a decision that what was happening there, the live from GISS was considered advocacy, and that's why they're trying to shut it down. And there's currently like they're trying to work it out right now. So the director of GISS, the current director of GISS, is trying to get them to let everyone back in, basically, and to keep this going.
That's right. We just had that, and we also, just as another reminder for discussions in the chat, just to keep it focused on the science, the scientific community, and not necessarily or not at all about politics. This is purely just about, you know, climate and weather as it affects us all as we walk around and experience it. So just to reiterate that. So let's see, do we have, I guess we'll keep you updated on that. In the meantime, I guess I was going to say a little bit more about my research and what makes me really drawn to this field and why I want to stay working in it. It's just a complete fascination with the sky. You know, when I grew up, like, are you kidding me? If it's a big snowstorm, I am like, this is incredible. You know, there's photos of me just like running outside barefoot, just looking up and like catching snowflakes. And that like never really left me. And I did a research project at Penn State actually in my junior year, so a year or two ago, about aerosols, which are suspended liquid and solid in the air. And in particular, how like I had no idea that there were little things suspended in the air. I had like some intuition because like I see, you know, a stream of light come through and you see the dust and everything lit up. There are so many things like way smaller than that. And that just blew my mind, especially hearing about the sources of all them, you know, sea salt from the ocean getting blown up by winds and traveling throughout the entire world in the sky, and bacteria from the oceans, the top of the oceans getting swept up, fires releasing smoke that gets transported all around the world, dust from the Saharan desert in Africa, all these things. And actually one that shocked me is like organic aerosol from plants and vegetation. So like I always smell a flower, you smell those chemicals that are beautiful and have that scent, but I didn't realize that they go on, react with all sorts of stuff in the air and become like liquid and solid bits that are a significant portion of aerosols in the whole world. That just blew my mind. And so that's what I've been studying for my PhD, is how these aerosols are evolving throughout the past couple years. And it has just been a fascination, especially aerosol cloud interactions, because at the center of a snowflake or a raindrop, you need a liquid and solid bit of something to start that process of condensation or freezing or deposition to make a snowflake. So you look at the center of a snowflake, there could be a piece of dust from a desert in Saharan Africa in that snowflake falling over you in northeast US, or a bacteria in the ocean that got swept up at the center of that snowflake from across the world. And that really keeps me going, is just the fascination with that.
That's amazing. It was also a really good explanation as well. That was cool.
Thank you so much.
It's crazy to think center of like every raindrop or every snowflake, there's some dirt. It's just like,
yeah.
We have an update. So we've been so this is Chris, who is a scientist at NASA GISS, who's just letting us know what's happening there. He says, we've been asked by folks from the Goddard HQ to stop streaming on government property and look to relocate. So I think that'll take a little bit of time. But in the meantime, you guys have been loving Henri in the chat, right? Can we get some love for Henri, everyone's favorite moderator, right?
Let's go.
Yeah. Boy.
Woo!
Hey everyone. Thanks for tuning in.
And now you see him in the flesh. This is amazing.
Hi.
Hey.
Yes.
Henri. Oh yeah.
Yeah, great to be here. Wasn't expecting to speak this morning, but I dug up some slides, so I will.
Yeah. Do you want to just introduce yourself briefly? So yeah.
Yeah, sure. So I'm Henri Drake. I'm a early career climate scientist. Got my PhD about 3 years ago and did a postdoc at the NOAA GFDL lab where Andrew is now in Princeton, New Jersey, working on climate modeling. Continuing to work on climate modeling now, mostly focused on the ocean. So I'm a physical oceanographer and study the physics of the ocean.
That's awesome. Do you want to share your talk, or I think?
Yeah. Oh, sorry. I thought I already was. All right. Should we get?
Yeah, I think we can bring you up to stage now. Yeah.
Okay. Yeah. So this is some slides that I'm reusing from an Earth Day seminar I gave. But I've been really fascinated by the history of climate modeling. So it was really nice to hear from someone who was part of that history in Dr. Rind earlier today. And I'll talk about some of that work, but from the perspective of someone who wasn't born when they were writing those papers. So maybe a different take. So I'm going to talk about the past and then also the present of climate modeling. So what I'm showing right now on this slide is what's been called the weather forecast factory. So this is a concept that was first created in 1920 by Richardson. And it was this idea that even 100 years ago, they thought that it might be possible to make accurate weather forecasts. And so the idea they had at the time was basically what we still do, which is you take the Earth and you chunk it up into a bunch of little boxes, the atmosphere, and you basically write equations for how the atmosphere should change in each one of those boxes. And at the time, they thought, okay, well, if that's a lot of boxes, that's going to be a lot of calculations. And so we're going to need a lot of humans to carry out those calculations. So they had these human computers that they imagined would live in these offices surrounding a globe. And each human would be in charge of calculating the future temperature and winds in like that one box. What they didn't know is that 30 years later, we would have actual like analog computers to do this, digital computers to do this for us. And so they basically had the right idea, but the technology wouldn't come for decades. And the concept is the exact same. It's just now we have like actual CPU processing units on computers doing each one of these little calculations. Okay, so just an overview of the climate change problem. We're, as humans, putting stuff in the atmosphere, like carbon pollution, that is leading to Earth system changes at global and regional scales. And that has all kinds of impacts. We've already heard about the stickiness problem, where when it's hot and humid, that can be really severe impacts. But there's all kinds of other things. In our group, we study warming oceans and rising oceans as well. And then, of course, we know what the problem is. And so we also know the ways to solve it. So you can either stop the climate change from happening by reducing the emissions that cause it, or you can try to adapt to whatever climate impacts are left over. Okay, in any case, we're in the business of making these predictions better so we can act in a more informed way. Okay, so if you're just tuning in and you heard that we were trying to have a bunch of little computers predict what the weather is going to be like, you might be thinking that's foolish. So this is just a picture, satellite composite of what the Earth looks like from space. And it would be pretty foolish to try and say that we can predict what this is going to look like exactly one day in the future, let alone 100 years in the future. So what gives? So I'm going to frame this as first telling you why it's so hard, and then kind of walk it back and explain why it's actually not as hard as it sounds. Okay, so this is just an incomplete list of all the things that make predicting the future difficult. So the first problem is that we don't even know what the equations that govern everything on Earth are. So there's already some error just in like the physics that we know about. The second thing is, even if we knew what those equations, basically like F equals ma, the laws of nature were, we don't know how to exactly solve them. And so we have to use computers, and computers sometimes make errors. And so that's a problem. And then even if we had perfect physical laws and perfect computers and algorithms, we still would need to start those from some point. So we would need to be able to observe exactly what the atmosphere and ocean look like today, so that we have a good starting point for the future predictions. And we don't have that. Okay, and then the final problem is that even if we had almost perfect observations, there's the butterfly effect. And so any tiny little error, such as a butterfly flapping their wings somewhere in Kansas, could create a tornado somewhere else across the world. And this is known as the butterfly effect. And actually, this is where the concept of chaos theory comes from. It came from Ed Lorenz trying to predict the weather and realizing that it was chaotic. So just to give you a sense of what that looks like, here I'm showing 3 different weather systems created by a forecast. And they started with almost the exact same initial conditions. So they started with the same weather on day 1, but then they had slightly little butterflies in different places. And so they ended up in a totally different place 6 days later. Also, Andrew and Sil, I know that we might be getting the NASA GISS people on soon, so feel free to just cut me off whenever I can find a good stopping point.
We will drag you off the stage when GISS comes back.
All right, sounds good. Okay, so the final thing, which is not really our problem, but problem of other people, is that humans are uncertain. So we're in the business of climate modeling, not trying to model humans. But because humans are impacting weather and the climate, there is also some uncertainty there. If we don't know, how much carbon humans are going to put in the atmosphere, we're not going to be able to predict the climate in 50 years. Okay, so I've explained why predicting the future is so hard, but this event is all about saving US weather and climate forecasts. So clearly it's not too hard because we can actually do something useful with it. For example, you probably now check the weather forecast pretty frequently. This is a pretty new thing in the last few decades because 50 years ago, people were making forecasts, but they weren't really that reliable. So people wouldn't check them. But these days, forecasts are pretty reliable a few days into the future, and so people use them frequently. Okay, so the first point is that I mentioned there's all these sources of errors, but the first 3, we've actually done a lot of work over the last few decades to reduce these. And so these are not really the main sources of error anymore. These are more stubborn and are hard to get rid of, but it turns out that the chaotic effect doesn't really show up until a few days into the future, like maybe a week or 2. And so we can get away with making weather forecasts up to 5 or 6 days in the future. And then humans affect the climate, but they don't really affect weather systems that much. So we don't really need to include what humans are doing in our weather forecasts. Okay, so just to kind of make this more concrete, weather models can deliver pretty reliable forecasts up to 7 days out now. Here's an example of how our skill, or actually our error in our forecast, has changed over time for the specific problem of hurricane prediction. So what you're seeing here is on the y-axis is the forecast error. So in the 70s, when we started making these forecasts of hurricanes, there was pretty large errors, and we were only making, so there's only up to blue colors here. So we were only even trying to forecast hurricanes 3 days out. And there's pretty big errors. The forecast error here is in terms of the error in where the hurricane landfalls in the US. So, on average, we were like 500 nautical miles off in our forecast. But over time, that has come down. So our 3-day forecasts have gone from being 400 or 500 miles off to now less than 100 miles off. So they've gotten like 5 or 6 times better. In addition to that, we've also been able to make forecasts 4 or 6 days out. So not only are our forecasts for a given lead time getting better, but because of that, we're also able to make reliable forecasts further out. And that's essential for preparedness.
Henri, I think we might have to cut you off there. This is great, though.
Okay.
It's kind of cool. We got like an extra 50. We're doing 50 miles better every decade or something.
Yeah,
right.
Exactly. All right, thanks. And happy to fill the time later and share the rest of the slides.
Yeah. Thank you, Henri.
Thanks, everyone.
Thank you so much. Give it for Henri at home, wherever you are. I had a quick question, Andrew. Is my mic better this way or this way?
The way it is now.
This way.
Yeah.
Okay, awesome.
The way it was a bit kind of muted. Yeah.
Okay, awesome.
No worries.
All right. So we have an update. So are we going to go live again near GISS?
Yeah, we're going to go live from a non-GISS building. So the GISS people have moved now to a non-government building, and they've moved all the equipment. They've set up again. And we're going to go to that now. And I think we have Chris, actually. Chris, I'm going to bring you on. Here you are.
Hello, you can hear me?
Yeah, we can hear you.
Yeah.
Yeah, so I'm actually going to abbreviate my talk a little bit just because of our disruption. We were asked to stop our stream, and now we've relocated to non-government space. So hopefully this will please the folks who made that decision. But I am going to be talking a little bit about a different use of the NASA model, which I'm calling, I'm not calling, it's called Rocky 3D, which is the planetary extension of the GISS model that is used for Earth simulations. And my advancing is not working.
Chris, can you resize your resize the window a little bit?
Hold on, I'm getting this.
Okay. Yeah, that's better. Thank
Okay,
you.
I see. All right, so as others have talked about, we use these models that are, we split up the planet into actually millions of boxes, essentially, in latitude, longitude, height, depth, and these exchange mass, moisture, energy, and we can model different aspects of the Earth with that. But what I want to do is talk about some recent advances in making our Earth climate model that has a long history at GISS more flexible for other planetary atmospheres. This is, and there's a few things that need to go into that, including making the radiative transfer flexible for other stars and other atmospheres that are very different from Earth. Treating the orbit of other planets, for example, planets that have a very different length of day or a different seasonal cycle, developing a calendar system that's robust to these exotic situations, allowing for for things like geothermal heat flux, which is a non-stellar source of heating. We have support for thin atmospheres such as Mars. I know there's a lot of interest in Mars nowadays, and so we want to be able to support science that allows us to understand that planet more, as well as deep oceans that are kind of a much larger fraction of a planet, such as on icy moons. And And here I have a plot of actually just the Martian seasonal cycle in atmospheric mass or pressure. On Earth, water is a very negligible part of the entire atmospheric mass. It still matters for climate because it affects the radiation. It affects the latent heat the latent heat coefficient is very high, and so it affects the thermodynamics. But in terms of the actual mass of the atmosphere, it's very dilute. Whereas on a thing like Mars, the thing that condenses, the thing that forms clouds, is actually most of the atmosphere, and so we have to redevelop the ways in which the model treats such situations. These are just a few examples of some of the science that has been done with Rocky 3D. In the left panel, I just have an example of an Earth and a synchronously rotating planet. So Earth. So on the very left here, you'll see temperature and ozone, and this is what Earth kind of looks like. You have a hot tropics, you have a cold poles. When you these data are averaged over months or years, and so when you do that, the sun moves so rapidly that you don't have any east-west variation in sunlight, right? But on a planet such as on the right here, a synchronously rotating planet, this actually means that the length of day is 365 days, the same as the orbital period, and so the same side of the planet faces the star at all times. There's a permanent day side and a permanent night side, and in this case, the permanent day side is located over the Pacific Ocean, and so we want to model. This is actually a very favored orbital situation for a lot of planets, especially around low mass stars, in which their rotation has been slowed by tides. So we're modeling the climates, and then on the top right here is the climate of such a synchronously rotating planet, except with an 11-day orbital period. So a planet with a very compact orbit around a low mass star. Actually, when you include ocean dynamics, you end up with something that does not look like a substellar point. It looks like this has been called a lobster pattern in the literature. It looks more like a stealth fighter to me, but that's what ocean dynamics end up doing in terms of spreading the heat from the day side to the night side. So even though there's a permanent night side, it's actually it's relatively temperate and habitable. And then we've done some ancient Venus work. There's a lot of such situations. One application of this is looking at the habitability of alternative Earth. So what I've done is I've just run almost 100 simulations here with an Earth-like planet and Earth atmosphere. But we're varying things about the orbit. We're varying the tilt of the axis, which controls the seasonality. We're controlling how oval-shaped the orbit is. And we're slowing the rotation down gradually as you move down the plot. So here I have like a 1-day rotation rate, which is Earth, and then I'm going down to 2 days. And as I advance the slides, we're going to start getting into very hyper slow rotating cases. And these all have very different obliquities. In some cases, you'll see for very high obliquities, such as this planet, the poles are actually warmer than the equator, just because actually in the long term, in the yearly average, the poles get more sunlight than the equator does. But as I advance down the slides, we start to see kind of once we get into these slow 20, 30-day rotation periods, we start to see mostly an ocean-land contrast. And this is now we're getting into the 30 to 100-day rotation period. And now we're getting into the area where the distinction between seasons and day and night don't really matter anymore, because if you're at any given point, say over South America or Africa, the sun is only going to be overhead for a very small fraction of the year, and it's going to slowly move east-west throughout the entire year. Okay, and then these planets actually get pretty cold, and what we see is because most of the time the land is not being heated by the sun, it's very cold when you average over the year, and we mostly see a land-ocean contrast when you average over an entire orbit. And actually, you can't really by eye anymore see the distinction between a high or low obliquity planet. And so, you know, we're thinking about the habitability of such planets. This is just, if I could just like draw attention to maybe this plot, this is just showing the habitable fraction, which is just a metric, you know, we make up based on some temperature threshold or precipitation threshold at each point. And then we ask what area of the land has that threshold. And we see that because the land is so cold most of the year, actually the habitable fraction of land goes down pretty rapidly with rotation rate. Okay, so slow rotators are not very favorable places to live on land for most of the year. We see this is just how the sun moves east and west on a slowly rotating. This is a 294-day rotation. We still have a 365-day year, but the day now is 390 or 294 modern Earth days, and so the sun moves very slowly east-west. And in some cases, it actually reverses slightly. So you know, you'd have very romantic double sunrises or double sunsets at certain points of the year. That has to do with when the orbital velocity is faster than the rotation rate. There are certain points in the orbit on an eccentric orbit in which that can happen. Here's another case where the sun moves east-west on a high obliquity planet. So there's an east-west and a north-south component. So you can imagine sort of monsoon, you know, a different sort of sense of the monsoons as the range moves with the substellar point. And then I'm going to cut off my talk in a few minutes just to make room since we were cut off. But one thing we're trying to do with all this is move from just climate modeling to also making contact with observables that the astrophysics community is interested in. Because, you know, we now have very expensive telescopes in space. It's just the James Webb Telescope that is actually taking observations of the transmission or the emission of planets. And so basically where the science is just in this cartoon, we see a planet from, you know, very far away as it transits in front of a star. This is what we can see. And as the planet moves in front of the star, you actually get a small dip in the amount of energy that we can see here from Earth, and so that's how you detect planets is you see periodic dips in the amount of light that you see. But you can resolve this as well by wavelength, and so if there's light passing through an atmosphere into your sensor, into your platform like James Webb, you can break this up by wavelength. So the planet will actually appear larger or smaller depending on the wavelength that you're looking at, and so you can generate transmission spectra based on and say something about the composition of this upper part of the atmosphere, maybe the top 100 millibars or so, which is for Earth that would be 10% of the way through the mass of the atmosphere. And so we can say something about the presence of oxygen or CO2. And what we're actually doing now is using this tool called PSG, the Planetary Spectrum Generator, to actually create images. This is not work I've been on, but we are now working with these with a few people who developed PSG to apply this to all of the alternative Earths that I just showed. And so we can actually create images, simulated images. This top row is a simulated image of Earth, and then the bottom row is actual observations of Earth. And so, and we can create spectra, we can create transmission spectra, or the actual reflection spectra, what would be reflected into a sensor. So this is simulating not just the climate, but the viewing geometry and the point in the orbit in which the planet is. So we can now make contact. We can use our climate simulations to make contact with the things that the astrophysics community is interested in, which we have multi-billion-dollar instruments in space that are getting this great data. So I had a whole nother half to my talk, but I'm actually going to stop now because of our disruption. I'd like to make way for the next speaker. But just jumping to, I will jump to my closing slide, which is, and you can actually use this Rocky 3D model, to probe your favorite questions about planetary climate. And this is very relevant for the public in terms of understanding planetary habitability. There's a lot of interest in Mars, future exploration, and inform existing or near future NASA missions. And at our sort of last day at GISS, it's unfortunate that, at GISS, there's been a long history of the science being a little bit disrupted somehow. For example, during the Bush-Cheney administration, when people were asked not to report about the then record warm temperatures in 2005, which is no longer near even in the top 10 of the warmest years. But this is our last day, and we hope that we can continue to talk about our science in a more transparent way. And even though we're losing our building, we still have our personnel, and we're going to keep fighting for our science and talking about the importance to the public and communicate with honesty what we know about the planet and about the universe. And so I'll stop there and take questions.
Thank you so much, Chris. That was a great talk, but also it's touching to hear that stuff at the end. I think we have time. We have one question which came up in the discussion, which or while you were talking, which I might just put up here, which is Carolyn Barthel, who was just asking, so if Earth rotated more slowly, would the land get colder? Is that something that you can say from these simulations that you have?
Right. So so a lot of what I showed, and I'll just advance the slides really quickly, but a lot of the work on Earth rotating slower has been I would say the intermediate rotation rates, where it's like 1 day, 2 days, 3 days. A lot of that work, the history of a lot of that work has to do with studying the general circulation of the atmosphere, thinking about, for example, the Hadley circulation in the tropics that transports energy from the equator to the poles. It actually gets wider as you have a slower rotation planet. Venus, for example, rotates very slowly. Its year is actually shorter than its day, and it has almost a global Hadley cell. But for these hyper slow rotating cases, where again the distinction between a season and a day and a night sort of loses meaning, and because at any point in the year the sun is not overhead; it's only overhead for a small fraction of the year, and so when you average over a year, the land gets pretty cold, and the ocean has a lot of heat capacity, so it's like a swimming pool that's being heated and cooled slowly, and it doesn't end up getting too cold actually in these runs, but the land does. Yeah.
That is fascinating, like absolutely fascinating. I did not know that. Thank you for sharing. All right, so Andrew, are we about at that time to switch to the next talk, do you think?
Yeah, I think we should
Okay.
we should move on. Do you want to introduce our next speaker?
I would love to, and I first of all thank you to Chris, and also just to remind all the viewers here about. Oh, I think there's a little. Okay,
Right.
sorry about that.
While they sort that out.
Let's see if that's better. Close. Anyways, we'll see if this works, but I think we should also take a minute to remind all the viewers of why we're here and the mission of this live stream. So hello to all of our new viewers. Thank you for joining us at hour 3. We are into hour 3, believe it or not. Time is flying. So hour 3 of 100, I should specify, of the weather and climate live stream. So we only have 98-ish hours to go. My name is Sil. I'm a first-year PhD student at NASA GISS, and I am your co-host. And this is Andrew.
Yeah, I'm a climate scientist at Princeton. I'm also co-hosting this segment. And yeah, we've been going presenting live from NASA GISS for the first 2 hours. That live stream from the Goddard Institute of Space Studies, that government building, was shut down. They've now moved to another place. But we've got another great hour of weather and climate science for you. But I think it'd be good just to take a little minute, right, to explain to people why we're here. Why are we doing this live stream? Why are we on your screens?
Absolutely. Yeah. Why are we here? It's a question I ask myself. It's a good question. Like, why am I doing anything? You know, you got to always think about that thing. Well, I can answer why we're all here right now, and that is because weather and climate forecasts are something that affect all of us. And it's something that the United States has led in and been a world leader in for the past century.
Yeah, we made some of the first climate models in the whole world. Some of the first weather forecasts were done here in the U.S. and some of the first. And we now have built these weather models which are able to predict the weather days or weeks in advance. And also, government labs like NASA GISS have built climate models which can help us understand how CO2 and other things that humans are doing to the planet will affect climate in decades to come.
Exactly. And one of the big questions is, how do these forecasts work? And that's what we're here today, learning from these scientists about how they study and understand the processes that are happening on our Earth. The United States has created an unparalleled network of observations using everything from weather stations, satellites, planes, balloons, boats, floats, you name it. And the result is an incredible network of forecasting observations, or rather observations that can be used for forecasting. And it, as we've mentioned a few times, maybe to the viewers who have been here since hour zero, it's really a miracle. It's unbelievable. It's a scientific miracle. So we are here to celebrate that for the United States.
100%. And yeah, this, if you like what you see, we'll put up a banner in a minute that tells you how to call your reps to support this type of science, support NASA GISS, support other people like that. We need to keep this miracle alive. We need to keep the lights on for weather and climate science in this country, and we need your support to help do that. But I think we should hear from our next speaker now, from Dorothy.
Absolutely. Yeah. Welcome, Dorothy. A little introduction is that Dorothy is a research scientist at NASA GISS and an adjunct professor at Columbia University. And the talk that Dorothy will be giving is about the Hudson River, and in particular, unlocking secrets, blue carbon in New York, in the New York Estuary. I love it. Let's learn. Thank you so much.
Yeah, hi. I'm glad to see everyone, glad you're doing this. And I'm excited to tell you about the work that we're doing around New York City and the marshes. They're actually our wonderful archives for past climate. And as climate changes, we can also see shifts in them. And the work that I'm going to show is really, it's only because of a lot of people's hard work. So if you can, let's see, how do I forward this? Maybe this, or, oh, where is it?
I'm going to ask them to do it for you.
Can you, can I change the slides, or, okay, that's fine.
We can change it. If you just tell us, we can change it for you.
Okay. So why do we care about wetlands? Wetlands are incredibly important. We didn't used to know that. We're still losing a lot of wetlands, but they're sponges. They soak up water for the aquifer for New York City. They're nurseries. They're at the boundary of ocean and land. They protect our shorelines. We found out that in Sandy, actually on Staten Island, whole communities were protected. But for us, they hold a lot of secrets that we've really learned that I want to tell you about. And they're very high sedimentation rate. They accumulate carbon. So they store a lot of that CO2 because the plants make their leaves and store, and then the marsh grows upwards in the water and really stores carbon over time. So the next slide, any coastal marshes are called blue carbon, and that's because they're connected to the coastal waters. So it includes grasses, salt marshes, tidal marshes, mangroves, seagrasses. But it's a lot of the carbon that is buried in the ocean comes from these coastal marshes, even though the strip line of the coast is small. It's because they're deep. And the Hudson River, we've discovered, has marshes as deep as 17 meters, so over 50 feet deep. They bury carbon at a tremendous rate. You don't hear people talking about go plant a marsh, like they say plant a tree, but actually they store carbon at a much higher rate than trees do. And the other problem is that so many have been lost and continue to be lost that we really need to save them. And I want to convince you about that here. Because our marshes are at risk. In the next slide, the things we're discovering in the next, if you can advance it, next slide. Here's a picture in Jamaica Bay, and Jamaica Bay is a national park in New York City. And you can see the erosion that sea level rise is having on the marshes. So we set out to ask a bunch of questions: how the marshes have changed, what's the human impact, how fast are they accreting, how does that change with human impact, and can we finally figure out ways to save them? In the next slide. So we look at it two ways. There are two parts to what is in a sediment core, and that's a core on your left, that 1 meter side opening auger. And the organic part is the part that was alive, so plants and animals, which gives us chronology. It tells us about the carbon history. We can learn about climate, paleoclimate from that. The inorganic part is the sand, silt, and clay. And I'll show you, as well as heavy metals that we've discovered. The next slide. So here's an aerial view, and I want to talk about Joko primarily, but you can see also in our data that the other marshes basically show the same story. In the next slide, a lot of these marshes in Jamaica Bay are gone because they've been, you basically have land fill on top of them. So one of the first things we do is to burn the samples. And the graph on the left shows you that the upper part of the marsh has more organic matter than the lower. It looks like when you burn it. But if you separate it out in the graph on the right from the organic and the inorganic, what you see is that the percent looks higher only because the inorganic part, the blue part there, has declined over time. So the organic part hasn't changed that much. But turns out Jamaica Bay marshes are starved of the sediment that used to be brought in by streams. In the next slide. So we did a lot of analysis on these marshes. And if you start at the top right, I'll just walk you across. It turns out using X-ray fluorescence, we can tell that those sand, silt, and clay is made of titanium and potassium, which declines over time because those streams have been hardened. The whole shoreline has been hardened. And so now the marshes are basically falling apart because they don't have that mineral sediment to hold them together. You also, in this record, see the coal burning signature in the early 1800s that we can track all the way back to Pennsylvania and the aerial burning of coal. And then you see in the upper part, the lead and the zinc, that we have big declines in the 20th century due to the Clean Water and the Clean Air Act. And so we have seen human impact that actually really helps the marshes and helps our air because of those laws that were passed during the Nixon era. Then you come over to the left and you see the high charcoal. That was during the industrial age. And then ambrosia, which is ragweed, and that increased right when you had farmers settling the area. And then it declines again in the 20th century. And finally, you see the record of trees on the left, which parallels the whole industrial signature of everything else. In the next slide. So to sum up, we see large declines since the 1800s that again is due to the hardening of the shoreline. We see the accretion rate increasing, even though we have this huge loss of sand, silt, and clay. And we think that that might be due to higher nitrogen fertilization. The next slide. So to summarize, we have this chronology that we can understand from just taking a sediment core in the marsh. We see the whole human history. And what we're really worried about as the marshes erode are these heavy metals that are continuing to leach out into the bay. And if we can keep the marshes alive by adding sediment, which is happening now in Jamaica Bay, we can keep them growing upwards and keep them viable as a protection for us as well. The next slide. This is just an example of some of the NASA work that's being funded for calculating how much carbon has been lost through time. We do that by looking at old maps and going out and examining the marsh itself, doing the loss on ignition and calculating the carbon. And you see this red used to be the entire marsh in Pelham Bay, and the blue is what's left. And there's a dramatic picture out in the water that we found of a remnant eroding marsh. The next slide. Then I want to jump upriver a little bit to Piermont Marsh, which is right next to Lamont, where a lot of our work is done, part of Columbia University. The next slide. Here we see native grasses being encroached by Phragmites, an invasive weed. In the next slide. And again, this marsh, which is over 17 meters deep, we count pollen and we can see climate change. And that those two orange circles are pollen evidence of a drought that happened during the medieval warm time. And that big increase on the right is charcoal. We see that this area was terribly dry during that interval of 850 to 1250 AD. And then in the upper part, you see European impact again with ragweed rising above the yellow arrow. As trees are cut down, you see the tree pollen over on the left, the hickory and pine declining, and you get cattails, ragweed, and other invasive species. And then the next slide. Again, in the top, you see heavy metals. You see the ragweed there, and you see changes in inorganic. In this case, the inorganic is increasing when you cut down trees because there's more erosion into the Hudson Estuary. And finally, on the right, we have nitrogen isotopes, and they're complicated, but the percent nitrogen continues to increase as there's more population in the area, while the nitrogen isotopes shift due to a lot of different factors. The next slide. The carbon we can calculate. We go through the medieval warm period with very low carbon accumulation because it burned off. The Little Ice Age, we know that the season was very short. Actually, we had frosts in August in Piermont, diaries show. The next slide. And they also did haying on the marsh and took off a lot of the carbon, which is not preserved. So thankfully, that's not happening anymore. The next slide. So finally, we see that the sedimentation ranges, basically it averages 2 millimeters a year, and we need to add sediment to keep these carbon stocks from declining and going back to CO2 up in the air. We also see that we have changes in carbon storage with climate change, and that's important to know for the future. And we know that increased nitrogen, which is from poop and pee in the estuary, can make the grasses look better on top, but below ground, they're actually falling apart. In the next slide. I have a student who just graduated who's looking at accretion rates in marshes and has found that coring is a much better way to calculate the carbon accretion than the current method, which is a different modern using only the very top centimeters, because the long-term averages out what's happening over quite a number of years. And finally, I think the next slide. Yeah, a student I have looks at salinity change as you go upriver, along with the next slide, heavy metals. And you can see that here we have lead profiles, and you see this big hot spot in New York City, but also up at Kingston, where we had all this coal delivered during the industrial era, and canals and barges bringing coal. And I think the next slide, again, this is our small accretion rate versus our projected accretion, our projected sea level rise. And finally, the last slide, we know that we're going to have more drought with higher temperatures. We know there's going to be more storms with greater frequency and intensity and sea level rise. So we have some suggestions. Basically, we need to help clean up our waters. We need to add sediment, and we need to conserve possible future places for more marshes. Thanks.
Thank you so much, Dorothy. That was amazing.
Sure.
I personally am curious about why wetlands are so important overall, and how do we preserve them?
Well, they're important for so many reasons. I mean, you think about New York City protecting the watershed, right? Because that's drinking water. But also for habitat, for birds, you know, wildlife is always greater around any kind of water. But New York City is really known for its tremendous bird life in Jamaica Bay National Park. But coastal protection too, you know, hurricanes are getting to be a bigger deal now. So they're lost because people didn't know they were so important, and they built on them and they've destroyed them for so many reasons. And we just have to learn to protect them by adding sediment, basically, to help them keep growing up. Yeah.
Thank you. Andrew, are there any questions in the chat?
I don't see any specific questions, but there are so many people who are asking or who are saying that they just really love that you're highlighting the role of wetlands, telling us about the natural world. I think people really appreciate this. And I didn't realize that you could look at these sediment cores and see such like fine detail. Like it's telling you about the history, right?
Right.
You see the evolution, everything. That's incredible.
Yeah, it's amazing what they can tell us.
Yeah, and it does actually look like we have one question that popped in from Anthony Perry. And the question is, do we have any similar models specific to the quicksilver impacts in the Sierra Nevada mountains and tributaries?
I'm not familiar with the quicksilver impacts. Can you elaborate?
We will keep posted if we get a response. Dorothy, maybe if we move on, we might be able to answer that later.
Yeah. Okay.
Thank you so much.
Sure.
Everyone at home, big round of applause.
Love Dorothy. And yeah, next we have Kate.
I'll be Dorothy. It's fine.
Yeah, sorry. Kate Marvel. Yeah, next we have Kate Marvel, who is a climate scientist at NASA GISS. And for those of you who may not be aware, Kate is an author and is a little bit of a celebrity in the at least amongst climate scientists. You're one of the cooler ones of us, I think. So if this is a good point to take the YouTube link, share it with your friends, because you want to hear Kate speak. So where do we have your slides? That's a good question.
Also, just a note. 100 emojis are always welcome in the chat.
Yeah.
Just going to put that out there.
Just going to themes or something. Okay. Sorry, everybody. Yeah. Can you hear me?
We can hear you.
Awesome. Perfect. Great.
Do we have slides somewhere?
We do. We're having some drama with the slides.
Oh, it's okay. What was it like? Were you in the building when you guys got moved out, or?
I am on vacation, and nothing I say will represent a specific federal agency whatsoever. But because I am on vacation and speaking in my personal capacity, I can say whatever I want. So hi, everybody. Hi from non-federal property and on this relaxing vacation. So I kind of wanted to take a step back and talk about like the overall context for why we do what we do as climate scientists and why it's important. So newsflash to everybody, the world is warming. We are about 1.4 degrees Celsius, which is way more than 2 degrees Fahrenheit, warmer than we were before the Industrial Revolution. And you know, we can measure this, right? We have several different data sets that show that the world is indeed warming and has been warming, you know, basically more or less with some wiggles for over a century. And I think it's really, really, really important to stress that we know exactly why this is. We understand why. Because some people like to tell us that, oh, climate has always changed. And we're like, yeah, we know, we told you that. And it's totally true that climate has been very, very different in the past. 21,000 years ago, where I'm sitting right now in New York City would have been covered with a thick sheet of ice. That's what we call the last glacial maximum. And it was 21,000 years ago. And we know from paleoclimate evidence that it was between 5 and 6 degrees colder. So really a very different world than we are now. And we know why that is. The Earth is not an only child in the solar system. We go around the sun, other planets go around the sun, and they pull on us with their own kind of weak gravity. And the impact of that is that the orbit of the Earth wobbles very slightly over thousands of years. It goes from an ellipse to the perfect circle, more or less, that it is now, and back. It changes its axial tilt, and it precesses on its axis like a spinning top. And we have really good reason to believe that it is these orbital shifts that led to the last ice age and the ice ages before. So we can ask the question, is it the orbit? Is that what's causing climate change today? Because we know that wobbles in the Earth's orbit can indeed lead to very, very big shifts in the climate. So I am very fortunate in the place that I work, that unknown government space agency from which I am currently on leave. We have a climate model. And what a climate model is it is very literally a world building machine. It lets us simulate hypothetical worlds, future worlds, current worlds, and past worlds. And so we can take a climate model and we can feed into it the observed changes in Earth's orbit over the past 150 years or so. And we can do that counterfactual, where we can look at the impact of the orbital changes that have occurred over the last century or two on global temperatures. And you can see that there is basically no effect whatsoever. So no, it's not the orbit. Now, there is a very, very obvious culprit for climate change, right? Almost all of our energy on Earth, with a very, very, very tiny exception of nuclear reactions on the Earth's surface, comes from that big glowing star in the sky, our sun. And so it is very reasonable to suspect that, okay, well, maybe if the climate is changing, it must be some sort of variance in the sun's output. But let me tell you, if the sun was getting warmer, somebody at NASA or one of the other government space agencies would have noticed. So we can take the model and we can run it with everything fixed except the observed changes in the sun. So can variance in the sun's luminosity explain the temperature changes that we have seen so far? No, it's not the sun. So we know that there are other natural things that can have really, really big climate changes. We know that when certain types of volcanoes go off, they spray so much gas and dust in the stratosphere that they actually block the sun and they lead to major climate consequences. So the most recent really large volcanic eruption was Mount Pinatubo in 1991 that lowered the average temperature by about 0.5 degrees. And we know that there have been other really consequential volcanic eruptions in Earth's history. So the eruption of Krakatoa in the late 1880s really, really cooled the planet and spread so much ash and gas and dust all over the atmosphere that it led to really, really spectacular sunsets that year and freaked out a lot of people in, for example, Norway. So it's reasonable to ask, is it volcanoes? So we can take one of our climate models and we can run it with only the effect of volcanoes. And what we see is that the model captures these localized brief cooling spikes that happen whenever a volcano goes off. You can see at the beginning of the record, there's Krakatoa, and then Agung, El Chichon in Mexico, and finally Mount Pinatubo. But what you don't see is any sustained warming trend due to volcanoes. So no, the warming that we have experienced so far cannot be due to volcanic eruptions. Now, we've kind of exhausted the things that nature can do that will change the climate. So let's look at things that human beings can do. We know that as humans live on the Earth's surface, they change the Earth's surface. We change forests into urban areas, into pasture, into croplands. And when we do that, we alter the surface of the Earth. We actually make it shinier when we cut down these dark absorbent forests and replace them with something that's less absorbent. So it's reasonable to ask, is it deforestation? And the answer is deforestation does slightly change the Earth's surface. The albedo effect, which is the fancy science word for the change in shininess, actually has a very, very slight cooling effect on the planet as human beings cut down trees and replace them with things that are shinier and reflect more sunlight. But you can see that deforestation, or at least the albedo or shininess effect alone, is not enough to explain the warming that we've seen so far. But deforestation does something else that's really important. Deforestation emits greenhouse gases. It takes something that used to be a carbon sink. Trees are very good at taking carbon out of the atmosphere to make more trees, and turns it into a source in the atmosphere. So deforestation is a major contributor to greenhouse gases. So are industrial processes like the manufacturing of steel and plastics and cement. And finally, the burning of fossil fuels like coal, oil, and natural gas emits greenhouse gases. And so if we look at the sources of greenhouse gas emissions, not just carbon dioxide, but also methane and nitrous oxide and other greenhouse gases, we see that about 2/3 of those anthropogenic greenhouse gases, human-caused greenhouse gases, come from fossil fuels, with 22% from agriculture and land use, and the rest from industry and waste. And we know that greenhouse gases, because of their molecular structure, are really good at trapping heat that comes from the planet's surface. So greenhouse gases, we expect from basic physics, will have a warming effect on the world. And this is what we see in a climate model. So if we run a climate model using only greenhouse gases, what we can see is a really sustained warming trend that looks kind of like the warming trend that we've actually observed. But if you look closely at this, you can see that the model run only with greenhouse gases is actually warming more than the observations. So what's going on here? Is our model too sensitive to greenhouse gases? And the answer is no, because there's one other thing that humans do that we are leaving out of this. Human beings, in the process of burning fossil fuels and doing other activities, also emit what we generally think of as pollution. Pollution we can see. You can see this haze over India and Bangladesh. You can see ship tracks over the Northern Pacific, smoke over California. These things are what scientists like to call aerosols. And aerosols, as you can see in these pictures, are really good at blocking sunlight. And so the net effect of aerosols, both from directly blocking sunlight and from seeding clouds, which block sunlight, is a cooling effect. So while greenhouse gases warm the world, aerosols cool the world. And so if we put together all of these different factors, the way that humans change the land surface by making it shinier because they've cut down forests, the way that humans emit greenhouse gases and human emitted aerosols, when we take all of these things, all of their effects, and we add them up, what we see is something that matches the observed temperature pretty well. So that warming, the warming that we are able to very confidently attribute to human activities, has consequences. That's the most frequently asked question that I get about climate change, actually, is, all right, well, the world's 1.4, 1.5, 1.6 degrees Celsius warmer. who cares? That doesn't really seem like a big deal. But we know that climate change changes aspects of the climate system, and we experience those. If you turned in for Casey's talk, you know that climate change is affecting heat waves. We expect that when it gets hotter, we will see more heat waves. And there's kind of a couple reasons for that. First is just we expect the distribution to shift over. When you change the center of the distribution of that bell curve, you're also going to get much more, you're going to get more extremes. We also expect to see changes in the circulation, the large scale motion of air throughout the atmosphere. And turns out that evaporation is a really efficient way to cool the surface. Your body will prove this to you when it gets hot, because your body will cover you in liquid, hoping that that would be evaporated away from your skin to keep you cool. The land surface of the Earth also sweats in the heat. That's one of the most efficient ways it has to cool itself. But when it gets really hot and really dry, you're going to deplete the moisture in the soil. You're going to have no other way to cool yourself off. And therefore, you're going to become hotter and hotter and hotter. So that's something that we call the soil moisture feedback. And that directly leads to the next consequence of climate change. We know that climate change changes drought risk, and in some places makes the chance of droughts that are more severe, more likely, more widespread. It really increases that risk. And that is because climate change is changing the water cycle. We know that hot air is thirstier air, so climate change is sucking moisture away from the surface. But we also know that something else is happening in the atmosphere. At the same time that climate change is causing more droughts, climate change is also leading to more downpours, heavier precipitation. And that is because warm air holds more water vapor. For every degree Fahrenheit increase, we see about 4% more water vapor that's allowed to just hang out in the atmosphere. And what that means is that when it rains, it pours. We expect that with climate change, we will see heavier downpours and more heightened flood risk. Climate change also means sea level rise. We see this right now. The seas are rising, and sea level rise is in fact accelerating. And there's two reasons for this. First is there is a lot of ice right now that's parked on land in the form of glaciers and ice sheets. When it gets hot, ice melts. Great scientific thought right there. And the ice runs into the ocean, and there's more water in the ocean. But that's not the only thing that's happening. Warm things expand. Warm water expands. So we also expect to see expanding seas as they get warmer, and that is also a contributor to sea level rise. Climate change doesn't necessarily mean there will be more hurricanes, but climate change means stronger and more damaging hurricanes. And that's because warm water is hurricane food. We know that the sea surface temperatures are warming. We also know that because that air is warmer, it will hold more water vapor, and that's going to lead to more severe downpours like we saw in 2017 in Hurricane Harvey in Houston. We also know that as the seas rise, those storm surges caused by hurricanes will push farther inland, become stronger, and get more damaging. Now, we don't necessarily know that climate change will lead to more fires per se, because fires are affected by a lot of different human decisions, where people live, what they're doing, what fuel availability looks like, what fire suppression policies might look like. But we are very confident that climate change means more fire weather, more of those hot, dry conditions that are really conducive to starting fires. So we know a lot. We know it's warming, we know why, and we know what that means. We know that we expect a robust link between rising temperatures and heat extremes. We expect more downpours and more droughts. We expect sea level rise. We expect changes in hurricanes. But here's the thing. Right now, I still have a job. And the reason I still have a job is that we're not finished with science. There are a lot of things that we still don't know. We don't know how hot it will get. And people are really surprised to hear this, right? They're like, scientists, you had one job. Why can't you tell us how hot it will get? Well, one of the reasons we can't tell you how hot it's going to get is we don't know what the future is going to look like exactly. We have a set of scenarios that we use that span warming between of slightly less than 2 degrees Celsius to all the way up to about 5 degrees Celsius. And just a reminder, 5 degrees Celsius is roughly the difference between now and the last ice age. So we're really talking about the difference between bad and completely catastrophic here. Now, there's several reasons we don't know this. We don't know how hot it will get because we don't know how the carbon cycle responds. So right now, human beings are emitting greenhouse gases from multiple sectors, burning fossil fuels for electricity, transportation, industry, and changing the land surface. And right now, the biosphere, stuff that photosynthesizes on land and on the ocean, is pretty good at taking carbon dioxide out of the atmosphere. In fact, the land is removing about 50% of the carbon dioxide, excess carbon dioxide. Land and ocean, is removing about 50% of the excess carbon dioxide that human beings are putting into the system. But there is no guarantee that that's going to last forever. We don't really understand now how climate change is going to affect phytoplankton that lives in the ocean. We don't really understand how it's going to affect permafrost in the Arctic. And it's really hard to take carbon dioxide out of the atmosphere when you're on fire. And because climate change does mean more droughts and possibly more wildfires and definitely more fire weather, we don't exactly know how those changes are going to affect the ability of the Earth's biosphere to take carbon dioxide out of the atmosphere. We also don't know how hot it will get because we have never done this experiment before. We've never kicked the Earth system this hard. We don't know how the Earth responds to really elevated levels of carbon dioxide. We know that when the temperature changes, aspects of the Earth system change, and those climate changes can themselves feed back onto the temperature change, making it warmer or colder. So I think the most easy to understand of these climate feedback processes is the albedo effect. Ice is really shiny and really reflective, just like those windscreens that you put on a car on a hot day. It cools the Earth down because it's reflecting sunlight. Now, when it gets warmer, the ice melts, and that exposes the darker ground or ocean underneath, and it removes that reflective effect. So this is an example of what scientists call a positive feedback, which is terrible terminology. We should call it a destabilizing feedback that has the effect of making the Earth warmer. But we understand what happens to ice. There's a pretty robust scientific consensus that when it gets warm, ice melts. One of the things that we don't understand is what is going to happen to cloud cover as the climate changes. And that's because clouds are really difficult to understand. There's low clouds, there's high clouds, there's wispy clouds, there's thick clouds, there's puffy clouds. There's different kinds of clouds at different heights in the atmosphere and at different places. And it is really, really difficult to understand exactly how those clouds are going to reorganize themselves to either speed up or slow down the warming. So clouds are really the wild card here. And when we take all of those, everything that we know, and we try to calculate how sensitive the climate is to elevated levels of carbon dioxide, what we find in recent research is that very, very, very high sensitivities to carbon dioxide are relatively unlikely. But low sensitivities are also completely ruled out. And so this kind of leads to a way that a lot of people tend to think about uncertainty. So you think, okay, climate change could be bad, but it could be great, and it'll probably be fine. And I want to be really clear that how we should think about uncertainty in the climate context is it could be really bad. It will likely be bad, and we've completely ruled out fine. So this, I think, has led to a lot of what I would call doomerism, right? There was this article in 2019 in the New Yorker by Jonathan Franzen titled, "What if we stopped pretending?" Basically arguing climate change is inevitable, terrible things are going to happen, we cannot prevent it, so let's just step back and let the climate apocalypse come. And I thought it was really important to respond to this. And so this is probably the thing that I've written that I'm the most proud of, this headline in Scientific American. Very, very important to make that statement. But what I do want to stress is that, and I've heard this at several points in the live stream, the number one thing that is hard to predict about the future is human behavior. Water droplets and ice crystals and bits of dirt and carbon dioxide molecules, those things follow the laws of physics. They will always react in the same way under every circumstances. People are really, really difficult to predict. That's why I'm a physicist, not a social scientist. Physics is way, way, way easier. And this is the #1 source of uncertainty in future climate. We don't know how hot it will get because we don't know what humans will do. So remember that plot that I showed of possible global surface temperature changes ranging from pretty bad to completely apocalyptically terrible? These mysterious labels here that begin with SSPs correspond to different future scenarios, different stories about what human beings will do in the future. And that, I think, is one of the most powerful things about climate models, is that they are machines that run on stories. You take a story, you translate it to emissions, and you feed it to a climate model, and the climate model will spit out the reality. And so what these correspond to is different scenarios about future human behavior, ranging from, in the blue down here, sustainable development, very strong climate policy, to in the red, really heavy fossil fuel use, no climate policy, and very, very high emissions. And the thing that I really want to stress is that that story is very much still in human hands. I, as a scientist, as a physicist, cannot give any opinion on policy, cannot argue for the right policies, because I don't know what I'm talking about. I'm not a policymaker. But what I can tell you is that what the physics says is that we very much still have a choice. And it is the research that we do at NASA GISS, at NOAA GFDL, at universities all throughout the country, that's really helping people understand what the choices are and what the futures could look like, depending on the choices that we make. So thank you very much. Happy to take questions.
Amazing, Kate. Thank you so much. There was so much love for that talk in the chat. The Captain Marvel we need. Amen. Amen.
Yeah, that was unbelievable. My mind is blown, and like I am like a student taking classes, and my mind was blown by that talk. Yeah.
And I think the biggest compliment you've had so far is I had planned to have a Star Wars evening, but here I am. This is amazing.
Yeah, that was incredible. Speaking of which, we have a lot of really good questions. It's going to be hard to choose ones to highlight. But Andrew, are there any that stand out to you?
I think there was one about aerosols. You mentioned aerosols. We'll bring that up here. So will new regulations on ship soot emissions have a significant effect on global temperature?
Yeah, that's a great question. And actually, it's a great question because it's something that scientists are fighting about right now. So in 2020, there was a significant change in ship fuel regulations. So I showed you a slide of these beautiful ship tracks crisscrossing the Pacific Ocean. With the change to different kinds of ship fuels, we no longer see basically ship trails that are that thick, that are blocking that much sun. Now, the emerging scientific consensus seems to be that that had a slight warming effect on the climate, those sort of thinner, less opaque contrails, but it was not a big one. Wasn't really likely to have a major effect on the climate.
Nice. We have so many questions. Let's just put another one up. So this is someone who really knows what they're talking about. This is a question for Kate. Models do a good job of reproducing warming in the last few decades, but models seem to underestimate warming during 1910 to 1940. Why is that?
Great question. I think, I'm going to step back and answer not that question exactly, but a related question, and then hopefully circle back to not ignoring that question. So it's really kind of important to me to understand what climate models are capable of doing, what they're for. So we don't expect a climate model to capture every variation in the Earth's day-to-day or even year-to-year climate. We don't expect a climate model to have, for example, an El Nino event in 1998, even though in the real world there was an El Nino event in 1998. That's not what climate models are for. We expect a climate model to simulate some El Nino years, and we expect the distribution of where those El Nino years were and what they look like to roughly match the distribution in reality. So we don't expect a climate model to be able to exactly match every wiggle. We expect that there will be a lot of what we call internal variability, essentially noise in the climate system, and we understand where that noise comes from. Now, there are concerns when climate models don't match sort of long-term trends or long-term behavior. One of the things that really started to happen in 1940 was this really large uptick in the global use of fossil fuels, global industrialization, especially in North America and Western Europe. And so we start to see a lot of, a big spike in aerosol emissions then. Aerosols are really difficult to get right in a climate model. They're really difficult to measure. And so we can start to see some divergences, some more uncertainty entering in the aerosol era. Before the aerosol era, we do see climate warming. Whether or not the models are supposed to match exactly, whether or not we should be concerned about that divergence, I don't really know. But we do know that there was sustained warming during that period, and we have been able to attribute it to human influences. Gabi Hagerl, who is a colleague of ours at University of Edinburgh, has done some really interesting work where she's arguing that massive heat events, like for example, the Dust Bowl heat wave in the 1930s in the Central Plains of the US, probably would not have been so bad were it not for that greenhouse gas forced climate change that was already occurring.
Thank you so much for that explanation. We have a lot of comments that are along the similar line, I want to highlight Bob Jones's. It's, what would be your thoughts around how to get this information to those who don't understand or refuse to understand?
I mean, my life got much easier when I realized that I don't have to do this on my own, right? There are so many people who have organized this live stream, who are participating in this live stream. There are a lot of us, and there are a lot of really amazing communicators, especially among early career scientists. It just makes me so excited and warms my heart whenever I see something like that. But knowing that no one person can do it all. No one person can be the messenger that every single community needs. And so people who won't listen to me, maybe they'll listen to you. Maybe they'll listen to somebody else. Maybe they'll listen to somebody who went before or after on this live stream. So I think the really important aspect of climate communication is that we need all hands on deck, really. We need everybody doing this. And we can have everybody doing this. And I think that's just the thing that I remember, is that it doesn't have to be any one of us. It's all of us.
That's inspiring. That's amazing. And speaking of all of us, we are almost at 1,000 people watching right now. This is amazing. Woo! 994, 993. Oh dear. Oh dear.
Almost.
We said 1,000 before we have.
Almost 3 hours too. This is awesome. Couple of milestones
coming up. Till we've ticked off 3 hours. So.
Yeah. Kate, I wanted to highlight one more comment. Oh, there we go. A lot of people are asking when your book is going to come out.
Oh yeah, I guess I'm on vacation. I'm not wearing my NASA hat, so I can say this. The book is released June 17th. If you are in the New York City area, please come to the free launch at the New York Public Library on June 16th. And I'll be in a bunch of East Coast cities, basically up and down the Amtrak corridor, talking to folks about it in June. So yeah, I'm really excited to meet people.
And what's the too long didn't read?
So the book is called Human Nature: 9 Ways to Feel About the Climate, Our Changing Planet. And it is basically climate science, but told through the prism of 9 different emotions. So we've got wonder, anger. That was the most fun chapter to write, actually, the rage chapter. But then ending up with surprise and pride and hope and love is the last chapter.
That is awesome. Oh my gosh. Everyone check out Kate's book. gonna
Right.
be-
Thank you.
Yeah.
Thank you so much for organizing this, and thank you everybody for being here.
Yeah. Thank you to you and all the GISS folk for doing this. It's amazing.
Seriously.
Bye.
So this concludes our segment with GISS folk, and we are going to be moving on to a terminated NOAA panel. And I believe this is our time to transfer hosts. So it has been a pleasure hosting this. Thank you all for joining. This has been a privilege. I am honored to be here with all these amazing people. And Andrew, it was so fun. I had a blast.
Sil, thank you so much. This was good energy. There have been a lot of comments that we might be long lost brothers.
Yes.
So thank you all for reuniting us.
I love
Let's keep the energy up. Thank you everyone in the chat who's commented and shared good energy. Love you all. Thank you.
Thank you so much. See y'all.
All right, so we're going to continue on with our streaming, our live stream, our 100-hour live stream event. Up next, we're going to move to a panel of fired NOAA scientists. But first, I would like to just say thank you to Andrew and Sil for doing an amazing job hosting the last 3 hours through the NASA GISS event, especially dealing with the fallout of the NASA GISS scientists being kicked out of their lab. Again, this is a nonpartisan event. We are just here to share our science and remind the American public the value of climate research, prediction, and weather forecasting. Okay, so as we know, the cuts are also affecting NOAA staff right now. And joining us today, we have 5 folks who were fired from NOAA, who are all scientists. And if we could actually add them on screen right now, that would be amazing. And I'll just do brief introductions. Here they are, the 5 joining us. We'll start with Tom DiLiberto. He is a fired NOAA climate scientist and public affairs specialist. We have Sabrina Valenti. She was a budget analyst with NOAA's Office of Habitat Conservation. She's originally from the Florida Gulf Coast and attended LSU in Baton Rouge. And she was very excited to manage the budget for a major coastal wetland restoration program in southern Louisiana. We also have Dr. Caleb Bissong, and also interrupt me if I'm pronouncing your name incorrectly, who is a fired duty scientist at the Pacific Tsunami Warning Center in Honolulu, Hawaii, where she participated in 24/7 watch monitoring and issuing alerts for tsunamis. So it doesn't sound great that you were laid off, Kayla. She holds a PhD in atmospheric science from the University of Miami and a Bachelor of Science in Environmental Engineering from SUNY ESF, which is located in Syracuse, New York, where I'm streaming from, also the best city out there. Moving on to Dr. John Cortinas. He's a retired from NOAA's Office of Atmospheric Research as the Deputy Assistant Administrator for Science. He was the previous director of the Atlantic Oceanographic and Meteorological Laboratory. And he was also a former director of NOAA Research's cooperative research programs. So a nice peer under the hood of what's going on in the NOAA research side of things. And finally, we have Anna Vaz, who is a former fish biologist at NOAA Fisheries, is an oceanographer who worked to integrate environmental variability, including ocean forecasts and climate production models, into climate-enhanced fisheries applications. Her work supported sustainable fisheries management and community resilience. She's also known to get overexcited about open science and local engagement with her community. And she also mentioned that we should ask her about chickens at our own risk. So we'll hopefully get a question in the chat about that. So just really quickly, the structure of this panel, we have some pre-made questions for our panelists on here. We'll just go through and they'll answer those questions very briefly. But this will be open to the audience, and we're going to hear what you guys, what questions you guys have for our panelists. Again, these are all laid off NOAA scientists. So let's start. First on my screen, we have Anna right next to me. What did you do at NOAA, and how did your work impact the lives of your local and nationwide communities?
So, good afternoon. Thank you so much for this opportunity. I was a fish biologist, and my research was to understand how environmental variability affects marine ecosystems and fisheries. Often I used traditional knowledge or knowledge shared by our communities to incorporate in my research, seeking sustainable fisheries management alternatives. So I made science accessible and actionable for people who depend on the ocean every day.
Amazing. Thank you, Anna. And Kayla.
Hi, and thank you for having me and for everyone who put this on. So I was a duty scientist or a physical scientist at the Pacific Tsunami Warning Center. And so I was a part of a 24/7 hour watch, basically looking out for tsunamis. And how we did that is if a tsunami is generated, we basically carry around these little pagers, sort of like ER doctors. And if there's a large enough displacement in Earth's crust or water, we get paged and we have to run into the ops floor and determine if a tsunami has been generated. If so, we kick off our tsunami forecast models as well as alert all the people that need to know about it. This includes the public, local officials and National Weather Service offices, emergency managers, and even the military.
Amazing. Thank you, Kayla. Tom?
Yeah, thanks for having all of us, and thanks for the beginning of this really, really long and extremely cool next 100 hours. So I'm Tom DiLiberto. I started as a meteorologist and a climate scientist at NOAA at the Climate Prediction Center, and then I moved into the world of communications. And when I was fired, I was a public affairs specialist at NOAA headquarters. I've done a lot of work in climate communications. I was on the ENSO team at NOAA. So if you like El Nino, La Nina, and you're wondering why it's happening, we are the ones who forecasted that. I was also one of the writers for the ENSO blog, as well as a climate scientist for climate.gov. And I somehow convinced NOAA to let me also make a cartoon called Teak and Tom Explore Planet Earth, which is aimed at kids. And, you know, the work I do is a lot about communicating what NOAA does in the climate space and also working with communities to develop solutions for building climate resilience.
Thank you, Tom. John?
I, and like others, I really appreciate the opportunity and really love what's going to happen just now as well, and in the very near future, the 100 hours, etc. So very excited to be here among other very proud former NOAA employees. I think that's one thing we find so much across our agency is the pride that all of the employees, whether current or previous employees, had. A lot of the jobs that we do aren't always, we don't do it for the money, we do it for the passion, we do it for the dedication. And so I think that's going to come out from hearing everyone's stories and the things that we do. As you mentioned, I retired a little earlier than I expected at the end of February after a long 20-year career, with almost 30-year career actually, with NOAA in one way or another within NOAA's research line office. And in my position, I oversaw our 10 national laboratories as well as our cooperative institutes that work very closely from universities and other research institutions. And in that line office covers all aspects of what NOAA does, whether it's marine ecosystems and understanding the changes, climate change impacts on habitats, et cetera, or fish evolution, whether it's understanding severe weather tornadoes and hurricanes, flying into hurricanes, collecting observations around tornadoes, and being storm chasers to understand and improve the weather forecast tools that our forecasters in the National Weather Service are relying quite heavily. We're also heavily engaged in understanding climate change, collecting observations, not only within the US, but around the world at other very remote locations, as in Antarctica and the far reaches of Alaska and in the middle of the Pacific Ocean as well. So we collect a lot of observations both on the ocean as well as the atmosphere. And so collectively, our laboratories conduct the research and provide information and improve our understanding of processes across NOAA to help us perform better for the American public and society. And the impacts of research are far-reaching across the agency. And so very proud to be here, and certainly proud to be a former NOAA employee as well. Thanks.
Thank you, John. And finally, Sabrina.
Just want to echo what everyone else has already said. Thank you for the opportunity to be here. I'm the lone budget analyst on a panel of brilliant scientists. I think any of the scientists would agree you can't do science without spending money. So it was my job to responsibly spend all the taxpayer money that flows to NOAA. I did the budget for a big coastal wetland restoration program that focuses on South Louisiana. And like you said, Mark, when you were introducing me, I went to Louisiana State University. I used to work for the state of Louisiana, so it was really amazing to get to spend money for Louisiana at NOAA. This program impacts people across South Louisiana by reinforcing the coastline that protects them from hurricanes, from run-of-the-mill summer storms. It builds back up the places where the hurricane evacuation routes are built, and all of that work also benefits migratory birds and Louisiana's fishery industry. I don't know if y'all have ever had Gulf shrimp. If you haven't, you should definitely try it, and that is reason enough alone to protect Louisiana's coastline.
Awesome. Thanks so much, Sabrina. And yeah, no, thank you guys for coming on. We know that, it can be hard to be fired from these positions, especially, as John was mentioning, we're all very passionate about what we do. We don't really do it for the money. We love the atmosphere and also, the fish biologists and all this other stuff. Okay, so our next question is, what is your biggest fear from these cuts? We'll start with Anna again.
So my biggest fear is my work was really related to NOAA had a big project to really incorporate all these amazing data and oceanographic models that John described very well are being developed on the OER side of NOAA. We had not only downscale climate projections looking at 50 to 100-year oceanographic conditions, we had also ocean forecasts for the next year to the next decade being developed. And we were going to use these models and incorporate these into management. And my fear is that the needs of the communities for this type of information is not disappearing. We are just disappearing with the resources that could help them plan their businesses, their livelihoods. For example, one of the projects I was leading look at that there is a complex of snapper and groupers in the South Atlantic region of the US that are showing a decline in recruitment in the last decades. And we were explaining by what environmental drivers are driving these declines. And then we were going to input this information to our stock assessment model using these very cutting edges forecasts that NOAA is producing, and we would be able to do better fisheries projections. So the fishermen would be able to actually catch more fish, and the consuls would be able to do a better job in setting the quotas and the fishing rates for the sustainable fishing industry. So my fear is that our communities are less safe, they are less prepared, and they are more vulnerable to all the impacts of climate change. And that's cutting both their livelihoods and long-term traditions in all the US, that all the communities that depend on the fishing industry to survive.
Thank you, Anna. Kayla.
Yeah, so I have two main concerns, and the first one is something you'll hear from most people who work in operations, and that's burnout. And so specifically in my unit, we only had 12, now 11 people covering a 24/7 hour watch, usually with 2 people on at all times. And also within an 80-hour period, we are also expected, we kind of have something worked out where we're definitely working more than 80 hours in a pay period with a 24-hour standby watch, right? So we have a very demanding schedule to begin with. We're already worried about a team that is stretched too thin. And so when you lose anybody, it's pretty disheartening. The second one, specifically in my unit as well, is this generational transfer of knowledge. 7 out of our 12, or now 11, are actually over the age of 50. And so they were really excited to have some young folks coming in, eager to learn the systems and understand what's going on. We have a pretty niche set of systems. It's all built in-house at the Tsunami Warning Center. It's not some other magical, Google or Microsoft program. It's all built in-house. And so there's this huge generational transfer of knowledge going on. And it's just pretty concerning, because if you don't do that, you're going to lose how to work these systems, right? So those are my two.
Great. Thank you, Kayla, for sharing that. Tom?
Yeah, it's safety. Safety is my biggest concern. Now, I wanted to work at NOAA since I was like 8, mainly because I love clouds, but also because, and this is not alone, it's a mission to keep people safe and to make sure people are safe. And the cuts that we're seeing, not only on the operational side and the Weather Service, but you're looking at cuts across in the Marine Fisheries, National Ocean Service, into the research wing of NOAA, OAR. These are all going to lead to there being less information, less knowledge going forward, less people making the forecast for you. And the biggest fear is obviously that people are going to get hurt. People are going to get hurt now, but we're not going to be able to plan for the future. We're not going to be able to plan necessarily the best way we can for changing climate extremes and how they're going to hurt the communities that we live in, the people that we love across the entire country. And, you know, when it comes down to it, like this idea of mission and mission focused, the people at NOAA are incredibly mission focused. And the idea of this, like going back to the burnout, is it's got to be incredibly difficult to really care about protecting people and having to do that now with less resources and less people. It's just a horrible thing to be going through, even if you're working there now, and considering the rest of us who are fired.
Yeah. John, I'm sure you have similar concerns to Tom.
Absolutely, as well as with Kayla and Anna so far, and probably with Sabrina, I'm sure. You know, I have a couple of concerns. One, Kayla touched on it, is the brain drain. We are losing, you know, hundreds of years of expertise, scientific expertise that's world renowned. You know, NOAA is very well known around the world for its expertise. People come to NOAA because of its world-class understanding, expertise, research, etc. And so we've lost so many people that took that expertise with them, as Kayla said, without the ability to maintain a younger, early career workforce. There are real concerns about how we'll be able to maintain that superiority, if you will, in terms of all of our operations, whether it's coastal operations, whether it's fisheries operations, our satellite service, our National Weather Service, the research. The other thing that I'm really worried about is not so much, although it's extremely important, on how it may impact the population tomorrow, but what's going to be the loss to the population in the next 5 to 10 years. Within research, NOAA research is one of the only places really anywhere in which, because of a sustained commitment to resources and research projects that are extremely large, that it's hard to imagine anyone else being able to take over that kind of global scale type research. And some of the innovations that have come out of research, you know, Kayla's a good example in terms of tsunami forecasting. The buoys that are deployed around the world to detect tsunamis originated at our laboratory in Seattle, Washington, from a research laboratory and the scientists that want to deploy the understanding and how do we measure these things. That took decades of investments in research and testing and deployment, and then the whole modeling side, the development of how we forecast tsunamis, etc. Those are not things that happen overnight. Those are not things that happen from a lone university professor or faculty member with a postdoc churning out a project. This requires sustained commitments of research and resources that we found have extremely high payoff to the public. With a minimal investment, we get a significant return on that investment in terms of life saved, property saved, etc. So I'm worried about what's going to happen in the future now that we've made all these cuts, without really thinking about, if we have to make cuts, how can we strategically make cuts instead of making large cuts across the board? I'm really concerned about the future.
Yeah, that makes sense. Sabrina.
Again, I have to echo everything that everyone has already said. I agree with all of you. I would say that my top concern with these cuts to NOAA is loss of life. You know, with the region that my work impacted, South Louisiana, they're no stranger hurricanes. For the younger viewers who might not remember Hurricane Katrina, I'm sure everyone else who's on this call does. We're talking about thousands of preventable deaths because of insufficient preparations for hurricanes. When you build up barrier islands in coastal Louisiana in general, you are creating an insurance policy for everybody who lives further inland, because you've added some land to just put brakes on the storm, to slow it down, make sure it's not as forceful when it hits you. And so to tie that back to my work as a budget analyst, there are still scientists on my program who are employed. There are still thousands of scientists at NOAA, but it's no good having the scientists on staff if you can't fund their work. And what we're still seeing from people who are inside at NOAA is that any activity over $100,000 is having to be authorized by the Secretary of Commerce himself. It's like if you're married, imagine if you went to the grocery store shopping for your household and you had to call your spouse every time you wanted to buy something that cost more than $1. It's creating a massive slowdown on all of these activities, including this coastal restoration work. And every hurricane season that passes without building those barrier islands, without replanting those coastal marsh grasses, without reinforcing the levees and the rock dikes and everything else that keeps Louisiana safe, it only takes one storm for people to be impacted. And again, as a person who is from that region of the country, I know that there's often a lot of derision directed towards the Southeast, a lot of this idea of you get what you voted for. And I think the reality is that me and everybody else I worked with at NOAA really cares about every single one of the hundreds of millions of people in this country. We don't care what your personal opinions are. We want you to be safe. We want you to be healthy. We want you to be able to enjoy an unburdened life and to enjoy the outdoors. And when you lose staff at NOAA like us who really care about that, every American suffers.
Mm-hmm. Yeah, thank you, Sabrina. And also, just going back to mentioning Hurricane Katrina, of course, this is the 20-year anniversary of the storm making landfall in Florida, and then, of course, in Louisiana. And something that I've been mentioning to people, of course, is that last year when Hurricanes Milton and Helene, formed in the Gulf of Mexico and the Caribbean Sea, the forecasts for those storms were incredibly accurate. They were both predicted to undergo rapid intensification well in advance of when they actually did. Hurricane Milton's first advisory predicted it would make landfall in Florida only 12 miles away of where it actually made landfall. And the reason that happened is because we've been investing, like John mentioned, in these research laboratories that develop the hurricane and weather forecasting models to predict these storms. Also, we invest in the cooperative research institutes that help hurricane hunters fly into these storms to take those very critical observations. So NOAA, it's a whole infrastructure, and that's why it's so amazing we have this very diverse panel, very diverse perspective of how each of you contributed to saving American lives. So that was really great to hear. So our final prepared question, and then we'll start taking questions from the chat. So for those of you watching, if you have a question you want to ask the scientists here as a whole, or if you want to ask just one in particular, go ahead and post it in the chat, and we have someone in the background kind of flagging those questions, and we'll be able to read those during the second part of this panel. So the third question is, and we'll start with Sabrina this time so we can go in a different order. What would you do if you controlled the purse strings of NOAA's budget? And going off of that, instead of cuts, what could we do to make NOAA better?
You can't solve every problem with money, but you can solve a lot of problems with money. And some of the things that NOAA has experienced internally over the last several years when we were all still employed is, for instance, transitioning to a new in-house financial system. This really delayed some of our program activities. And if I was in charge, I would spend a lot more money to make sure that doesn't happen. I would spend more money to get grants out the door to help states build projects in their own backyards, the same way that my project did with our coastal wetland restoration program. I would keep spending money to recruit brilliant meteorologists like Tom or fish biologists like Anna to make sure that people have career stability. I think one of the things that has given NOAA its edge for decades is that people around the world know that NOAA is where you go to do amazing science. So the more that we can fund people's stable careers, the more that we can have there be, stable federal employment and not just contract employment. We can prove that we want to back up scientists, that we want to fund research, even if we're not sure it's going to go anywhere, because some of these most revolutionary discoveries happen when a scientist is kind of afraid that they're going down a dead end and things turn up differently. There's so many different things that NOAA does, the coastal restoration, of course, the fishery maintenance, the research, the tsunami watching, hundreds of other functions that people not represented on this panel did and still do every single day. But NOAA needs more funding to do the thing that it's good at. And through all of that research and proactive planning and preparation, we can improve American lives, keep Americans safer, and have really healthy fisheries that produce things like Gulf shrimp for us all to enjoy.
Thank you, Sabrina. John, do you have a follow-up as well?
Well, thank you for starting with Sabrina, because I think she probably covered a lot of it for all of us. Ditto. But certainly the funding, I think, is an important aspect of if you look at NOAA as an agency, and as I said, you look at the return of investment, this is one of the best investments that the country can make in terms of just a little bit of resource, just a small amount of resources has a huge payoff for our society in terms of the economics of our businesses and our population, and not only for the United States, but for the entire world, for sure. And so we're essentially a $6 billion agency that could do at least with $20 billion in order to keep doing what we're doing and do even more of it and help expand our partnerships. Our university partnerships are extremely important. That requires additional funding for grants, et cetera, for them to work with us. We work a lot with nonprofit organizations in terms of building out communication to help share all the information we have with with society so that people can make better decisions. And I think helping us to continue to stay non-political, if you will, about what we do. We don't really get involved so much with policy as it is with the science and delivering information to people so that they can make their own decisions. But you have to make sure that you have all the information in order to make those informed decisions. And so we'd like to stay, not become political in any of this and not get so much into policies, but more resources to develop the best information and data and observations that people in the public can have to make their own choices and let the policymakers develop the policy. But at least they'll be well informed when they do those things.
Thank you, John. Tom.
Such great things already mentioned so far. If I had I would fully make sure it was all the National Weather Service people would be fully staffed. I mean, it's short staffed now, but it's always been short staffed. It's always been problems with making sure that we have enough people in the right place to be able to make the forecasts. I would make sure that the radars are funded and we're getting next generation of them. We fill those radar gaps across the country that we do so desperately need. I'll make sure that we have a full observation network. Let's get as much data as we can. That could include public-private partnerships like that we already signed, that NOAA already signed last year with folks like United, putting on instruments on the planes. I make sure that we can fully sustain our observation network, whether that's buoys, satellites, it could be related to greenhouse gas monitoring. I would also make sure that one thing that NOAA does a lot of, besides the weather forecasting, which is incredibly important, and fisheries, seafood monitoring, make sure that our seafood's safe and abundant, but we work with communities a lot to help build climate resilience. One group is within the Climate Program Office, which is the Climate Adaptation Partnerships Program, which work on the ground with communities to build from the ground up solutions to extremes, whether that's extreme heat, drought, flooding, you name it. Same thing with coastal, making sure we have enough money funding our National Ocean Service to make sure that we can protect the coasts and the ecosystems that exist in those areas. There's just so much if you had more money to be able to do. The question at NOAA has never been, what to do with this extra money. I don't think I've ever heard anybody ever at NOAA say, what should we do with this extra money? Like, it's always been, okay, we have this pot of money. How can we try and maximize the impact? And that just brings a question, man, what could we do if we fully funded the work at NOAA, and how much good could come from that?
That's so true, Tom. That is so true. Kayla.
Yeah, so obviously I don't think the answer is to rush into downsizing or drastic cuts, right? So NOAA's mission is simply just too important to risk with hasty decisions like those that have been made. Instead, I'd kind of advocate for more of a careful data-driven review, like kind of where inefficiencies and redundancies truly exist, because as much as I hate to admit it, they are out there, right? And I think potentially one of these places is kind of at the senior executive level and maybe the GS-15 level, right? And so I think maybe some of the people at the top need to kind of engage with us more directly with those of us doing the science. We're kind of in the best position to point out what's getting in the way of effective work, right? So too often unnecessary meetings, irrelevant trainings, and a lot of like bureaucratic red tape slow down progress and distract from NOAA's core mission. One of the best examples I have of this is my entire team had to spend days doing this training for something that had to do nothing with tsunamis, right? And so we're spending hours and hours doing something that doesn't actually pertain to us. And all of us just want to get back to our projects, right? I just want to get back to my code and finish my coding project, right? So by listening to the people on the ground and streamlining only where it truly matters, we can really modernize NOAA for the 21st century and put those funds where they count, making it more effective without undermining the essential services that protect lives and property.
Amazing. Thank you, Kayla. Yes, I agree, especially with the what is happening now, the cuts. It's very chainsaw approach. There's no thought. It's more of a let's slash now and see what happens type of thing. Whereas, yeah, there's definitely opportunity to figure out where there are inefficiencies. Anna.
Thank you. Everybody made my job very easy. So I totally agree. Like as John said, as my colleague said, like NOAA is one of the best investments we can make for our future. I would say I would invest in our resilience of the agency and of our communities. I would be growing NOAA, not shrinking NOAA. But I have 2 points that I think are very dear to my heart that I think are being highly affected now, and that's going to have an impact on NOAA and our communities and in science, not just for the US, but globally. One is go back to increase investment into open science. We have a great effort to drive open science within NOAA in the last years, and it's highly successful, and that can drive a lot of innovation and create exactly this type of efficiencies and savings we're looking at. It can drive a lot of fast development of models of use of our data. So have our data all available for our academic partners, our international and national collaborators, and to businesses. That so many businesses use NOAA data and they drive innovation and they make a lot of money by creating products based on our data that then we can learn from what they're doing and improve our processes. So that's one point. And the other is our international partnerships. Like I see here, all of us, the science we do is not bounded by borders. Our ocean is moving, our fisheries are moving, the tsunami is moving, the climate is affecting everywhere. And if we stop having data here, we're not gonna have good models. If we have a blank data, or if we have not access to data from our partners, be it for natural resources or physical data, we also not going to be able to do a good job. We really need just exchange and flow of information, and we need exchange and flow of people and ideas. We need to be able to travel and attend conference. We need to be able to receive students, to train them and learn what other countries are doing. We really need to have this exchange preserved. So that's one thing. If I could control the budget, I'll make sure it's happening. I'm also an immigrant, so that's kind of course, near to my heart, but I think it's very important for advancing our mission.
Yeah, thank you. And I'm really glad you talked about the observational infrastructure of NOAA. I mean, climate agencies, weather forecasting agencies around the world use that data. NOAA has built the most important observational infrastructure of our planet. And if that data suddenly is not shared, it would really affect not just our ability to predict the weather and climate, but the rest of the world, which is very important to mention. So I'm glad you brought that up. Those were all excellent questions or excellent answers. I'm so glad you guys all have very different perspectives on NOAA. Okay, so we're now going to take a look at questions in the chat. So again, if you guys watching the live stream on YouTube, if you have questions, you can go ahead and type them. Again, just general questions or directed at one of our speakers. The very first question is from Lauren. Please tell us about the chickens. I think that is directed at Anna.
Sorry, what is the question?
Please tell us about the chickens.
Yes, I have 8 chickens, 4 standard size breed, 4 silkies, and they're really cute. And one of my silk has been broody for a whole month. So if someone has any tips, please.
All right, we'll look out for tips in the chat then for that. Okay, going to our next question. My 8th grade students just learned about the NOAA Tsunami Monitoring Program in our Natural Hazards Unit at the end of this year, and they were really fascinated by that. So maybe more of a comment. Kayla, I don't know if you want to respond to that quickly or...
Yeah, first off, I think that it's amazing that you're teaching 8th graders about tsunami hazards and using all of the amazing resources that NOAA has put together. I know there are tons of them. I've used them in my own talks. So just mainly an applause for, getting the information out there and helping to make people aware. I think I caught someone at the end of the previous talk say none of us are alone in combating climate change and making everyone more aware of the hazards in our own yard.
Nice. Thank you, Kayla. Our next question from the audience: how many lives are collectively impacted by your monitoring and rapid response work? Shall we start? Should we start with John maybe, and we'll go through some other folks?
I don't have any exact numbers, but I would probably start by saying the entire population of the United States in one way or another. I think the work that NOAA does is so expansive. I don't think the average person fully understands. I think people even at NOAA don't even fully understand the expansiveness of what NOAA does in all aspects of the environment, particularly on the atmospheric side, and in the oceans and our Great Lakes and our coastal region. All of those areas really fall under the main domain under NOAA's mission. And so NOAA is the agency that's responsible for collecting information and transmitting it to the public in near real time in many instances. And so the infrastructure, the number of people that are required to even be able to support an infrastructure like that is expansive. And so when we lose people, we lose our ability to communicate effectively and quickly with the general public, as well as the broader community. So I think one way or another, every single person in the United States is impacted by what we do, what NOAA does in terms of the information it collects and it shares on a minute by minute basis sometimes.
Yeah, John, that's so true. And again, every time the live streamers, every time we open our phones to check the weather, right? All of that data is possible because of NOAA, its forecasting models, its observational network. That's not just coming from your phone or the phone company, that's coming from NOAA, really. So thank you, Trixie Ann, for that question. Does anyone want to add something, Sabrina or Tom?
Yeah, I wanted to add, so I started my career at NOAA in the Office of Response and Restoration. Response right there in the name. They house what's called the Emergency Response Division, and this is an office that sends top scientists out anytime there's an oil spill or a chemical spill in any of America's waterways. So again, the older folks on the panel or in the chat might remember Exxon Valdez in 1989. Younger, those of us probably still remember Deepwater Horizon back in 2010. That was a massive, 72-day long oil spill in the Gulf of Mexico. And it was scientists from NOAA's Emergency Response Division who went out there and who were assessing the situation. They were trying to figure out, where's the oil going in the water column? How is it affecting fish and marine mammals? How is it affecting phytoplankton? The critters that are so small you can't even see them with the naked eye. And they respond to dozens and dozens of spills in every region of the country every single year. There's still Deepwater Horizon response work that's going on right now. And it's been 15 years and a month since Deepwater. So if you like swimming in water that's not coated in oil, you can thank NOAA for that. As I've heard Tom say before, if you've gone outside, you can appreciate what NOAA does. So I think that we can all, whether you're in the driest part of the country or the wettest one, we can all appreciate what NOAA does for every American.
That's so true. Tom, Kayla, Anna, anyone want to add something? Tom?
Yeah, I'll just say, in order to forecast the weather, understand what's going on our planet, no matter where you live on this planet, you need to have information from literally every country everywhere. So impacts at NOAA are inevitably going to be felt everywhere. right? What goes into weather models that are run by other places across the world, right? You can't necessarily like, oh, well, these cuts are hitting the United States. Those cuts will impact how any model works. I mean, we all know a model is only as good as the information you put into it. So NOAA runs, right, 2 geostationary satellites that cover roughly half the planet. That information easily goes into models used by, run by countries around the world and institutions around the world. So these cuts at NOAA obviously are directly going to impact Americans. They're already impacting Americans every single day, but they're going to impact everybody on this planet in one shape or form.
True.
Can I add a quick?
Yes, Anna, of course.
There's recent studies showing that the improved of the model forecast for hurricane have saved $5 billion per event. So
Wow.
just that, you see how impactful the work done at NOAA is. And what Sabrina said remind me too that we also have a fisheries resource disaster assistance. So every time there is a hurricane or any other type of big event like the collapse of the crab fisheries in Alaska, NOAA fisheries researchers are going to go and talk to the community to provide assistance, emergency assistance to the communities that are affected too. So we really work from all fronts together to help our communities to remain safe and resilient.
Very true. Kayla, do you have anything to add before?
Sure. So I would agree with kind of Tom's sentiment that it does extend globally. NOAA's impacts are reaching people all over the planet. It is called Earth science, right? And it is Earth system sciences. And I think it was Sabrina who also mentioned that, storms know no borders. Tsunamis know no borders. And in fact, the tsunami monitoring program, we have a lot of international collaborations where we're talking to people in Japan, Chile, Australia, New Zealand, and we're all communicating and sharing data about a propagating tsunami. We also are the tsunami mission for someone like the military, right? And so all of our data and all of our information also has things like geopolitical ramifications. So it's much bigger than the United States.
That's so true. Thank you all for your responses. Let's move on right to the next question. And so we only have 20 minutes left in the panel, so we'll probably do maybe 2 or 3 responses per question, starting with, let's actually go to this question. This is from VCW Loves. They say, I'm located in Southwest Texas and it's getting hotter every year. There's also decreasing water sources. How will people who rely on your weather forecast, especially related to heat, be affected? Anyone wanna jump in?
I can talk a little bit. So obviously, the National Weather Service is still going to be forecasting. I always joke like if the National Weather Service has some of the world's best meteorologists. Like NOAA has some of the best oceanographers, the best marine biologists, the best satellite experts. Like you just run it across the board. So those folks are still going to be doing their best to use the information that they have to make the best forecasts for you, because that is their mission, that is their goal, that is their life. That's what they want to do. That's all they've wanted to do. The things that could especially be impacted kind of fall on the outside of that. What happens? How do we prepare for extreme heat? How do we work in the off season, the non-hot time of the year, to prepare communities for extreme heat? At NOAA is run the National Institute, the National Integrated Heat Health Information System, or NIHIS, or the folks who run heat.gov. And they basically work with communities on, off, all the time to help build resilience to extreme heat, so that when the forecasts come for the National Weather Service, people know what to do. They know where to go for help. There are people to check folks, let's say, who are inside their houses or apartments heat is a silent killer, right? So NOAA does all of that work. And we know that grants have been cut to start for centers of excellence with NIHIS, or efforts specifically to help folks deal with heat in communities across the country. And the one thing I say about NOAA is that at no point does anyone at NOAA ever say, who did this county vote for before giving potentially life-saving information to? That never comes up, ever. All that folks at NOAA want to do is help people and provide this best help. But now you can see with these cuts, they're inevitably going to be felt and impact, but not necessarily now, let's say this heat season, but the next season and the next and the next and a decade from now, because we know the efforts to help drive change and build resilience can't happen overnight. It takes consistent investment to help build that resilience so we can eventually save people and help people survive some of these extreme heat events.
That's so true, Tom. Does anyone else want to jump in on these reliable weather forecasts?
I just want to add that it's not necessarily that the forecasts will get more unreliable, but they won't keep consistently getting better and better and better. If we go back again to Hurricane Katrina, you look at the forecasting models that were used in 2005, and they were dozens of miles off. That's why New Orleans wasn't prepared for the storm that hit them. If you use the modern day models and the information that was available when Katrina was barreling towards the Gulf Coast, you combine those two things, you get a way more accurate forecast than we had 20 years ago. And so I think the question to be asking is, what amazing advancements could these meteorologists at the National Weather Service be making if they still had all the resources they need? Instead, we might be stuck with 2024 tools for the next 5 or 10 years. Mm-hmm. And so the big loss to me is the lack of advancement that will be occurring because of these cuts.
Well said, Sabrina. Thank you for that. Okay, we have some actually direct questions. So we'll start with one directed towards John from Alpharia. Issues regarding Hurricane Hunter flights have been an issue for a while. Will the potential lack of additional funding of flights cause even more problems in forecasting?
Well, again, without specific information about any specific cuts, generally speaking, with less resources, NOAA will not be able to do everything that it's doing today. We've got very committed and dedicated workforce who go to extremes to be able to make sure that everyone gets the best information as possible. But with fewer people, the observations that come from the hurricane flights require manual engagement. In other words, it's not just an instrument that we sit out there and let just kind of go and take measurements. It actually takes people to operate, as you know, that fly into the hurricanes themselves. Right now, there are two ways that NOAA gets information from hurricanes that involve flights. One is with the Air Force. So the Air Force maintains a consistent, what they call a reconnaissance flight, where they go out, they sample with some traditional instruments that they have, dropsondes, for example, those instruments they drop from the plane, and they provide that information to NOAA. NOAA also has its own fleet of aircraft, and that fleet is specialized so that it takes unique types of observations within the hurricanes that the Air Force reconnaissance cannot take. Those planes don't have those kinds of instruments. For one, there's a radar like we see on TV every night in the tail of the NOAA aircraft. And so that specific information NOAA has found through its research contributes to a more accurate forecast. And so without that information, there's no guarantee that NOAA will be able to deliver the most accurate forecast possible. So yes, there are concerns that if there's cutbacks and that we are not able to make those flights on a regular, consistent basis or be able to collect the information with the people that need to collect the information, there could be a degradation in the forecast.
Nice. Thank you, John, for your response. Okay, so we're going to do a question for Anna and then a question for Kayla. Starting with Anna, a question from Aster. I grew up in a fishing town in Alaska, heavily reliant on fish and aware of fish populations. How quickly, dramatically do you expect fishing towns and their fish populations to be affected?
That's a great question. Well, we're trying to answer that question with our big initiative of understanding the linkages between climate change and the fisheries in the country. Alaska has been heavily hit. So we have the example of the snow crab collapse that hit suddenly, and all the fishermen just didn't have that resource on that year unexpectedly to fish. So one thing with the climate change is usually this region, especially the Northeast and the Northwest and Alaska, is very seasonal, very predictable changes, and we could account for these changes in our population models. But with climate change, we have just more extreme events, and we have rapid cooling or warming, and the system goes from a linear change to a non-linear change. We really cannot use the old models we use to now see how the population is going to respond. We need to find new ways to account for these changes. And that was why we had a big project to try to account for this very extreme variability of the climate right now into our resources. So we will expect expect more of these changes. There are some species already shifting their distribution. So some species are getting out of some areas into new areas. Some are just expanding their ranges. So they're not leaving their old areas, they're just getting into new. And that's going to cause competition between species that didn't exist before in the region. There's lots of unintended consequences too. For example, you have a fishery of shrimp now. You can have shrimp up to New York, we've been told by fishermen. And there is no turtle excluding devices legislation past Virginia. So if you have a fishery of shrimp in an area where sea turtles, they go to feed, and you don't have turtle excluding devices, this is a big problem for protected species. So you're going to have all these sort of unintended effects that we need to still sort out. So we expected the fisheries town going to be affected. There's also direct effects, right, of storms in the southeast, of all the hurricanes affecting our portuary infrastructure and the boats itself, days at sea, how far you can go, how much you can get out with just changing patterns. So there are changes happening in our towns, and many are starting to talk and trying to prepare for that.
Thanks, Anna. It was very interesting to hear about how you guys may have been able to prepare for these extreme weather changes, but that you might not be able to do this anymore. That directly affects everyone. It's crazy. Okay, we'll do one question directed to Kayla, and then we'll go back to an all participants question. Kayla, can you talk about what the consequences of burnout and loss of generational knowledge might be for the 24/7 tsunami watch? How could that affect tsunami forecasting and warnings?
Yeah, so I think I mentioned that out of the 11 left, there are 7 that are over the age of 50. Within that group of 7, they pretty much developed the warning system at PTWC. And so these are like very unique Linux systems. And so the transfer of that knowledge is very important. On top of it, we're actually trying to kind of merge with the Alaska Center, because right now, one of us even runs on Linux, one of us runs on Windows, right? And so we're also trying to come together and create a more continuous operational effect, because we do back each other up. And that's why we do need 2 centers, because if one goes down, we need a continuous watch of tsunamis for our coastlines and globally, right? And so that's a big concern. And then burnout is always a concern, especially you're only having 11 people for a 24-hour watch, 2 people on at a time. We're working more than 80 hours in a pay period. There was already burnout, right? And so when there's burnout, mistakes can happen, right? And that's the main concern for that.
Right. Yeah. No, thank you, Kayla, for that. And here's, okay, so we have about 10 minutes left. We have another question for all of the participants. Kind of asking about how you were let go. Did your manager explain why you were let go, and have your former coworkers described how they're coping since you left, going off of kind of that burnout question, Kayla?
Yeah, I can go first. My team is incredible. A lot of them have reached out to me. I don't want to start crying, but everything's been really emotional. They lost one of their own. We're a very tight-knit team, so everyone's pretty disappointed. And they've all reached out to me to make sure I'm okay at multiple weeks at different times. I'm also close with some of the folks in the Tsunami Center in Alaska. Like, we all check in on each other. My manager didn't even know that I got fired. I had to inform him. I had to inform him more than once, because I got fired and then rehired and then fired again. So no, they don't know. And we still actually don't have a reason why we were fired. It was technically for performance, but even though I have positive performance reviews, and so do many folks that have gotten fired, there's no direct link to what those performance measures that we did not meet were. So there really is no explanation other than we're just easy to target.
Yeah. Thank you, Kayla, and thank you for being open here on this panel. I think that's very important to our viewers to know that we are people as well as scientists, and we are being affected by this. Okay, let's go. Anna, do you have a comment?
Yeah, so building up on Kayla, for those that don't know why not today here, what happened is we all received kind of a mass spam email We all received the same email. Some of us, it was populated our name and position. Some of us, not even that was correct in this email. And it said it was not more in the public, our skills, knowledge, and our abilities were not needed by the agency. My supervisor had provided just a week earlier a justification of why my knowledge, abilities were needed by the agency, because I have a rare skill set. I was fulfilling NOAA mandates under the MSA for sustainable fisheries. So congressional bipartisan laws that direct the work I was doing, and most of my colleagues here too. So it's very complicated. I needed to tell my supervisor too that I was fired, and she couldn't even process that had happened, because she's a director of she also took the early retirement. She was the director of the Sustainable Fisheries Division, and she was not aware. The director of our center was not aware. And on that day, he lost 17 of his employees. So in one day, about 10% of his workforce was let go, and he was not afford any input on if that would help or not the center. And a lot of us were brought to actually update how we did research, how we did our management advice. We were doing a lot of cutting edge and increasing efficiencies, making everything more accessible and more efficient. So we still puzzled and trying to understand what happened there. And I think my other friends and my colleagues are overburdened. We were already overburdened before these firings. We all did the role of 3 or 4 other workers. We all work it a lot. We work way more than our 40 hours a week, and we wear multiple hats. As John said in the beginning, we all do that because we love it, and we believe in the mission, and we really, they are now really trying to see what needs to be done, what is essential, and a lot of essential things are getting cut because there's just not funding or people to do other work that needs to be done.
Yeah, thank you, Anna. Tom?
Yeah, I'll just say my manager got fired first, and then he had to get in a call and fire me. So we were both probationary employees, and that's one thing that's consistent. So I had worked at NOAA starting in 2010, and I had been a contractor for about 13 years before I finally became a federal employee. And they fired me 13 days before my probation period ended. And my boss was hired a little bit after I was. So he had to get the first news from his supervisor, who then we had to jump on a call, and he had to fire me. So in terms of NOAA comms, I always say, what good is the work NOAA does if we can't communicate it to the people? And the communications part of NOAA has been decimated across the board. So it's just a lot less people trying to maintain the level of work that we've always put out at NOAA, and having a difficult time being able to keep up with all of the stuff that we usually do at NOAA.
Yeah. No, Tom, that's awful. Yeah, the communications department just being decimated, that's exactly where we need you guys the most, especially with climate change. And Sabrina.
I'll make it quick since I know we're coming up on the end of our time. My manager found out I got fired from me because I actually didn't get a firing email. I just got locked out of my email the same at night that everybody else had been terminated. So I heard through word of mouth I had been on the firing list. She told me, my supervisor told me not to come in the next day. And when I did finally get a printed out paper copy of my termination email that, again, I had never received, it said that my job was fish biologist. So whatever resource they were using to track down all of us probationary employees and fire us couldn't even figure out what job I was supposedly not good enough to perform.
Wow.
Since I've been terminated, I've stayed in touch with former colleagues, and it's depressing. They tell me every day the things that aren't able to get done, again, because of that $100,000 rule that I explained earlier on. They're all afraid for their own jobs. It's just a really dark time to be working in what should be a really uplifting, powerful, mission-driven agency that's full of people who just want to make this country better.
Yeah, no, that's so true. Yeah, no, it's going back to that recurring theme among the panelists. We're all very passionate about what we do. We're scientists over here, right? I mean, I always tell people, like, I literally sit behind a computer and just code all day, and that's what I do. Like, we're not the enemy here. We're just very passionate about the atmosphere and the ocean and understanding it and trying to protect lives. So it's really great to hear that, Sabrina. Okay, so we have about 3 minutes left. So I think we'll just go through, and if anyone has like maybe a closing statement, closing thought, what you're looking forward to next. Hopefully you have something you're looking forward to. We would love to hear. And maybe let's start with Kayla.
Yeah, so even though this has really stunk and has been really hard, and it's a traumatic thing to go through, at the end of the day, I'm still a scientist. I'm going to continue to do science in any way that I can and support climate and weather science on any front, especially as it's under attack. I do support a North American multi-model ensemble project where I do publish real-time NMME forecasts at the beginning of every month. You can actually find them on the Rosenstiel University of Miami page, a little plug there. So that's something that I'm going to continue to pursue, because if they start removing plots from anywhere, we're going to try to put them back up. And then also continuing science communication. I'm part of the Season Chaos blog, which is an upcoming thing as well. And we continue to communicate science to the public on every level, to scientists and non-scientists alike. So I'm going to continue to do what I can.
Great. Thank you, Kayla. John.
Well, I'm retired, but my passion continues well into retirement. You never just kind of drop it off. So in any way that I can help support, build and spread the good news about NOAA. And I think all of us, and even in this panel, I think try to serve as a voice for our NOAA colleagues who can't speak. And they can't speak because they're still federal employees that are under the responsibility of the executive office. And so we can speak for our colleagues and try to communicate to the public and others who will listen the important things that are happening at NOAA and the real challenges that the people that are still within NOAA are going through, but yet maintain their dedication and show that they still are some of the best federal employees that exist.
Yeah, that's true. Anna.
So let me turning a lot to like local action and community building. I'm part of my town sustainability commission, and we finished a climate ready plan for our town. So we're looking to put that into place with partnerships with other non-governmental organizations and businesses. And I'm also helping climate youth group to keep on going, and those things kind of bring me joy and some hope that we can continue the work in some other fashion.
Yeah, that makes sense. And we'll hear quickly from Sabrina and then Tom.
Yeah, two final things I wanted to say. One, I hear from a lot of folks like, well, we should make government more efficient. Why can't we do that? And I just want to remind everyone watching who doesn't already know, government has to make this trade-off between transparency and efficiency. Our mission is to serve 100% of Americans, not to, select a demographic that we want to cater to and only serve them. And so when we work for all of you, that means everyone, the edge cases, the complicated cases, that can get a little expensive. And we also want to make sure that we track every single step that we take, every single decision that we make, not only to comply with federal transparency laws, but so that average citizens can just trust that we're doing the right thing. So it does make things go a little slower. It does make things a little more expensive than maybe the private sector would do it. But we're also doing tasks that would never happen in the private sector. So that's one thing I wanted to address. The other thing really builds on what Anna said, which is that we have to stay hopeful. I know that all five of us are talking about the dire impacts that we're facing, and I don't want to downplay that. It's absolutely a crisis moment for American science, but it's not over. There are states funding these things. There are private entities. There are nonprofits. There are still grants from elsewhere. There are philanthropists. There are community groups that are all working together to make sure that not everything is lost. So if you find yourself feeling sad and dark and hopeless and depressed, remember that acting is the best thing that you can do to feel better, and that we are all going to work together to make it through this together.
That's true. Thank you, Sabrina, for that. Tom.
And I'll be quick. Sometimes it feels like we're a hamster or a gerbil on a spinning wheel, not being able to go anywhere. But that's not the case. Look at this. This is what gives me hope. This whole thing, the people in the comments section talking about it, just the sheer amount of people speaking up for why these things are so damaging, who understand the impacts of these cuts. So again, thanks for having us. I think it's incredible, this thing. I cannot wait to, I may not be on here for all 100 hours straight, but I'm going to be on for plenty. And thanks to everybody for asking these really great questions.
Awesome. Yeah. No, you can see the director behind the scenes is throwing up some of the comments. Really we really appreciate you guys and what you do and what you continue to fight for. And really to be on the panel today fighting for NOAA and its mission is amazing. So thank you again for coming. All 5 of you did an amazing job, answered all the questions, and hopefully we will keep in touch. But yeah, in the chat, let's give some love to our speakers, definitely. And we will move on to the next segment of our live stream. Thank you. All right, so next on our agenda, we're bringing up 2 former National Weather Service directors. We have Dr. Joe Friday and Dr. Louis Uccellini. I'm going to start really quickly with 2 introductions, but really before that, I will just say the panel structure will be, first I'll do introductions, and then we will ask some pre-made questions to Joe and Louis, and then we will open up to the chats. So hopefully the chat, you guys keep typing away your questions, and we'll star a few of them to hopefully bring them up so Joe and Louis can answer them. All right, so our 2 panelists for the next hour as we pass hour 4 of the live stream, the 100-hour live stream. Up first is Dr. Louis Uccellini. He was director of the National Weather Service from 2013 to 2022, director of the National Centers for Environmental Prediction from 1999 through 2013, and he was formerly a research scientist at NASA Goddard. He received his Bachelor's of Science, Master's of Science, and PhD all from the University of Wisconsin-Madison in the 1970s. And Dr. Uccellini has been recognized as a Fellow of the American Meteorological Society, was President of the American Meteorological Society during 2011, and is also an elected Fellow of the National Academy of Public Administration. He has also received a number of awards, including the Cleveland Abe Award from the American Meteorological Society, which recognizes his devotion to serving meteorology. He also is a NASA Exceptional Scientific Achievement Medal and a Distinguished Career Award for Sustained Career Excellence from the National Oceanic and Atmospheric Administration, and quote, for extraordinary dedication to preparing the public for and protecting the country against extreme weather, water, and climate events. So thank you so much for joining us, Dr. Uccellini. And we also have Dr. Joe Friday with us. He was director of the National Weather Service from 1988 through 1997. He was deputy director of the NWS before that from 1981 through 1988. And before all of that time in the National Weather Service, he served 20 years in the United States Air Force. He was selected for the rank of colonel in 1977 and had positions at the Air Force Global Weather Central and Headquarters Air Weather Service. Dr. Friday received his Bachelor's of Science, Master's of Science, and PhD all from the University of Oklahoma. I saw that your bachelor's degree was in electrical engineering. I thought that was quite interesting. And he graduated from the Air War College in 1976. Dr. Friday has been recognized as a fellow of the AMS, American Meteorological Society, and also served as a president of the organization. He has been awarded a number of medals, including the Defense Superior Service Medal, the Bronze Star, and the Air Force Commendation Medal 3 times in his military service. And he's also been awarded the Cleveland Abe Award from the AMS and received the National Weather Association's Quarter Century Award for being an outstanding member of his organization. So thank you both, Joe and Louis, for joining us today. We really appreciate it. As the former directors of the National Weather Service, we really want to know your opinions, what you guys are thinking on these cuts and how they're affecting the National Weather Service. So we'll just go ahead and dive right in. We'll just start really quickly. If you guys just want to kind of just discuss what's going on in the National Weather Service, maybe you could also talk about the letter you and 3 other former National Weather Service directors wrote. We would really be interested in that. And we could start with Dr. Uccellini.
I always start with Joe.
Okay, all right, yeah, let's start with
Joe. Go ahead, Joe.
Thank you very much, Louis. I'm just delighted to be here. I tell you, Mark, I listened to several minutes of your previous panel.
Yeah.
And my heart really goes out to the men and women of NOAA who have been subjected to this insanity that's going on, and I use that term advisedly. I think when we suddenly recognize that these sorts of things were going on, it's when the various past directors of the Weather Service decided it's time to speak out about it. We can't just stay silent about that.
Yep.
Now, I will tell you, getting 5 former directors of the National Weather Service together to agree to and sign a 2.5-page document is a miracle in itself. We don't always agree with each other. We have different philosophies about the way things should be done.
Yeah.
But this one was so critical as far as the future of the Weather Service, the future of NOAA, that this was something that we felt was absolutely essential, that we voice our concerns, that we try to focus people's attention on what was really going on. You heard from the probationary employees that were let go as a result of an automatic suspension of all probationary employees dictated by Dodge in the administration. That's insanity in its own right. You're eliminating your lifeblood into the organization. There are 2 types of probationary employees: those that are serving for their first time in the federal government, and those are really the lifeblood. Those are the future leaders. Those are the future scientists. Those are the future people that are going to make the service continue to be a viable service, providing information and service to the American public.
Yep.
But there's another kind of probationary employee too. If a person competes for a job and is accepted for that job and promoted, they're on probation for a couple of years, and to make sure that they qualify for that. Many of these people got removed as well because they were, quote, probationary. That's eliminating the best and the brightest. That's eliminating the ones that have competed. And then, of course, we had the offer and encouragement of early outs and early separations. And I can't blame people for taking those. Certainly with the uncertainties as far as the federal government is concerned right now, that would drive a lot of people to say, I don't need this uncertainty anymore. I've got to stabilize my life. And I can certainly understand that. But as a result of those actions, National Weather Service now has fewer than 4,000 people in its employment. That's the lowest it's been since I can remember. It's certainly lower than any time that I have been involved in the service. We used to have about 6,500 in the service when the modernization and restructuring began back in the late 80s and early 90s. And we made the service more efficient, and we made it better. We reduced the number of offices. We reduced the total number of staff. But that plan was a well thought out plan. A strategic plan was put together. We worked with the National Academy of Sciences to make sure that the progress moving forward on that was adequate, that we weren't doing things that were going to harm the American public. We worked with Congress. We had authorization legislation to bring that in force. We didn't just all of a sudden say, we're going to get rid of all these people without thinking about what the results would be. As a result of that non-thinking, we ended up with an organization that has holes throughout its staffing structure all over the place. I've referred to it as a piece of Swiss cheese. They're various sized and they're various locations, and a lot of them don't make any sense. We've lost a lot of senior management. Meteorologists in charge at over 30 offices are missing. The Houston office lost all 3 of its senior managers. We've lost 80 electric technicians. These are the men and women that maintain the radar and maintain the weather observing equipment and make sure that things are working for us. Now, they can make a lot more money in the private sector than they can in the federal government. They've been devoted to their jobs, and all of a sudden, many of them are let go, or been reduced in service, and others have taken advantage of the early outs. And again, I can't blame them for doing that. But this Swiss cheese structure that we have now, I'm glad I don't have Ken Graham's job, because trying to manage the structure now and to fill the holes that are there and try to take care of things coming up for this hurricane season is just incredibly difficult. And as I said, I'm just very glad I don't have that job now. But it was concern about these personnel actions, and it was concern about the impact this would have on the future. It was concern about the fact that the government has decided that they don't need all of NOAA research. And it's NOAA research that helps make the Weather Service possible to use the latest technology. It's NOAA research that has helped us develop the finest hurricane computer models going that we can use in our forecasting process. It's NOAA research that developed the Doppler radar technology that allows us to peer inside the thunderstorms to see the developing mesocyclones, which will eventually turn into tornadoes, and give us a heads up in the weather warning and forecasting process. It's NOAA research that has made all this possible. And now all of a sudden, NOAA research is not as important to the federal government by edict. Not by reason, not by any kind of structure, not by any kind of strategic thinking. There is no strategic thinking that has been involved in any of these actions.
Yeah, thank you, Joe. You brought up a lot of good points touching on probationary employees. Again, and that I feel like people don't appreciate the fact that that's also people that were just promoted to new positions, which, again, the brain drain is just absolutely insane. And the number of National Weather Service offices that don't have meteorologists in charge right now, we're losing all of that expertise that makes the National Weather Service so great. And that will definitely be a hole, as you say, in the cheese, the structure of the National Weather Service. Dr. Uccellini, do you have things to add to Joe's great open?
It is always hard. But as Joe said, 5 National Weather Service directors got together, and it boils down to our concern for the people and the ability to meet the Weather Service mission of providing observations, forecast warnings, and now impact-based decision support services that are officially in the mission and authorized by the Weather Act in 2017. And then the way it happened, especially with the probationary folks, it was cruel and it was uninformed. And it was that initial discussion amongst us that brought us together. Now, being uninformed carries the big spectrum, as Joe just laid out for us. All right. They're uninformed about what actually goes on in the Weather Service as a science-based service organization, what goes on in the rest of NOAA in support of the Weather Service mission, which ends with saving lives and property and enhancing the national economy. So NOAA being gutted out, as the Weather Service is being gutted out, is not only attack on the services that are now this collaborative effort with the emergency management community at every government level. That's where the job ends, right? Mm-hmm. It doesn't just end now with the forecast and warning. It ends with that collaboration, the provision of impact-based decision support services, the people who are on the ground saving lives and property, right? So that collaborative effort is being pulled apart. The threads that make that happen, the practice sessions, the tabletop sessions, the inability to travel even locally because the credit cards were canceled. I mean, this is just beyond belief. It's not the way you should be dealing with a science-based service organization that serves 330 plus million people from the Western Pacific all the way into the Atlantic, from north of Alaska all the way down into the Caribbean, with now 4,000 people. You talk about efficiency, right? 10 service areas from space weather to the ocean and everything in between. Yes, hurricanes, severe weather, flooding, fire weather, all right, winter weather, all of these over, what do we say now, 4,000 people, serving 330 million. So we have an efficient organization, a science-based service organization, a service organization that's recognized by the emergency management community writ large about allowing them to revolutionize their approach to these extreme weather, water, and climate events. All right, so this was obviously very disturbing to all of us, and the human factor with respect to those in the forecast offices that were let go, I got to understand the mission and the dedication to mission in the Weather Service by having Joe actually hire me in 1989 and come in from NASA, which has a pretty damn good reputation in mission itself.
Yep.
But to see the people inside the organization and what they would do to ensure that products and services got out on time every time. And if it didn't, it's all hands on deck, even if it's the middle of the night on Super Bowl Sunday, okay?
Mm-hmm.
They're there serving now 330 million people. That's what not only drew me into the Weather Service with the modernization, as Joe mentioned, but kept me there, right? And working not with those people, but for those people.
Yep.
And their dedication to mission. So really an upsetting thing to watch from the outside looking in, a full understanding of the impact. But until you listen to the people like you had on the last session, you start really seeing it and feeling it in ways that, we thought we could understand what was going on. But every time you talk to somebody who this has happened to, it really opens up a whole new dimension. So Mark, I'm really glad you're doing this and ready for your questions.
Yeah, we're glad to have you guys. All right, so I feel like you guys so first of all, if you're joining us on the live stream just now, my name is Dr. Markowski. I am a climate scientist, and today we have two former National Weather Service directors, Dr. Joe Friday and Dr. Louis Uccellini. So we'll start with some questions kind of related to what you guys were just talking about. And if the live stream, if the folks joining us on YouTube have questions, please go ahead and put that in the comments section, and we will flag those questions for later so that Joe and Louis can answer them. So go ahead and post your questions there. So Joe, we'll start with you again. Both you and Louis, you guys had a really great introduction, I think, in describing the cuts that have occurred. And I think it would be really interesting to hear how you guys think these cuts will already start affecting our weather prediction and weather forecasting in the United States in the near future, or do you think this is something that might take a year or two to kind of fully understand? And also, do you think National Weather Service workers who, the 4,000 still working for 330 million people, will they experience burnout? How are we going to take care of that situation if they're overworked?
Mark, first of all, let me assure you that we're already seeing negative impacts of the staffing shortages that are already occurring. We've had to close several offices, nighttime shifts.
That's right.
We've had to stop taking weather balloons at several locations, at least dropping one or sometimes two a day. Those weather balloons are kind of critical. They provide the type of detailed information that you cannot observe from the ground and you cannot observe from satellites. But it's the kind of detailed information that is necessary to go into our numerical models and also to go into the analysis of what the future 24, 36 hours is going to bring as far as severe weather and small-scale weather events are concerned. We've already seen numerical numbers or actual numbers showing the decrease of our forecasting computer models in the last couple of 3 weeks. You can see the numbers actually going down. And that's because of, number one, we've lost some of the weather balloons, some of the input into the data. And number two, we don't have the staffing in the National Meteorological Center, in the National Centers for Environmental Prediction. It was the old days, it was the National Meteorological Center, and I still have trouble. So we've lost some of the staff that takes care of the quality control and takes care of making sure that the models are really performing up to par. But it's not just us. The European Center, which is perhaps the best computer model in the world, is also showing a loss in accuracy over the same period because of the fact that they are being deprived of those critical data that come from the weather balloons.
Yep.
You talked about the potential for burnout.
Yep.
I have seen in my time in the National Weather Service, and I understand Louis' concern or a Louis statement in which he said that he was really working for them, not them working for him. That's the way I felt about it during the entire time that I was in either deputy director or director of the Weather Service. It was important that I represented them completely. But I would see men and women at the forecast desk making sure that the latest weather information, including severe storm warnings, went out even when their own homes were currently being threatened by a major storm event.
Yeah.
But they were staying there to make sure that information went out to the emergency managers. And that's not an unusual event. That happens time and time. If there's a bad winter storm forecast, we'll have men and women come in with sleeping bags because they want to make sure that there are people there to provide the support during the storm when otherwise they may not be able to get in. Weather is a 24-hour-a-day, 7-day-a-week mission at National Weather Service. It has some of the most dedicated people I have ever known that I've ever worked with. They are dedicated to public service. They're dedicated to the mission of the National Weather Service. But they can only be overworked so much before the stress continues to increase. Now, I've been asked in some of these interviews, how long is it going to take before we start losing lives as a result of that? I don't know. I can't say that explicitly. The men and women of the Weather Service will do everything they possibly can to make sure that we don't lose any lives. They'll come in late. They'll work late. They'll come in early, rather. They'll work late. But the fact is that overtime eventually gets to you when you're working so many extra shifts. You heard that with some of the panelists that you had on the previous panel.
Yep.
When I remember when I was in Vietnam, our duty cycle was 12 hours on, 12 hours off, as far as weather forecasting was concerned. Now, those first 8 hours were fine. The next couple of hours 9 and 10, that was getting a little rough. But boy, I tell you, hours 10, 11, and 12, I saw things on those maps that didn't really exist. You know, you're sitting there trying to concentrate, and if the weather is really severe, if you've got everything breaking loose around you, you need to be at your peak mentally. And if you have just finished working 30 hours or something of that nature, or 2 shifts in a row, you're not going to be at your peak.
Yeah.
And some days we're going to see some negative results of that.
Yeah, no, thank you. Thank you, Joe, for that response. That was, you touched on everything. And I especially liked how you mentioned the weather balloon observations affecting our numerical weather prediction models. Like that data, knowing what's going on in the atmosphere is so important to know what's going to happen in the future and improve our forecasting. So it's amazing that that's not just affecting our weather models, but also the European weather models or any other international organization that issues weather forecasts. Dr. Uccellini, do you also have a follow-up to this?
Yeah. So, you know, I've been asked the question too, when do you expect everything to fall apart? Well, first of all, I don't expect everything to fall apart with the Weather Service employees and the NOAA people who are supporting them. The dedication to mission, especially when there's an oncoming extreme event or events, plural. I'll get to that in a minute. You know, it's just absolutely amazing to be part of that. All right. And to watch it. So it's impossible to say that. But the point is that there's been a fabric established of collaboration, not just coordination, collaboration within the Weather Service, within the entire weather water enterprise. You know, the chat sessions that go on now before the official products go out with the private sector and others, and other parts of a community that's actually preparing for an evacuation. You know, that's at risk. And then you have this collaborative effort now between the weather enterprise, basically, with the Weather Service leading the way, and the emergency management community at the local, state, and federal levels. Again, I have to emphasize, they're the people saving lives. They're the ones that are preparing the community. It's this trusted relationship that's really developed now uniformly across that entire domain space. Like I said, from the Western Pacific all the way over to the Mid-Atlantic and Alaska all the way down to the Caribbean, right? That is in action now a week plus before an oncoming hurricane. You don't see it, but it's there, right? They're all part of that internal chat sessions that, really gets a collaborative effort going in the face of extended forecasts, which we all know has increasing uncertainty and lack of, the verification, decreases further up. But they got to start earlier because there are more people along the coastlines that are at risk, right? There's larger areas. There's more vulnerable people now living along the coast. So actually evacuations start 2 days in advance to get that all lined up. These folks are working together a week in advance.
Yeah.
Plus, all right. So I worry about that fabric, and at some point it's going to pull apart. People want to know, well, what's it going to be like? That we got to prepare for the hurricane season starts on June 1st, right?
Exactly.
Hurricanes are important. Believe me, hurricanes, like Joe used to say, the hurricane director works for me 6 months of the year. We all work for the hurricane director, the rest of the year, right? So the point is, yes, they're important. But at the same time, you have flooding aspects, you have severe weather aspects, and you have fire. There's no fire weather season anymore. It's the fire weather year, right?
Yep.
And some of these same offices are dealing with multiple hazards. That's a stress factor.
Yep.
And I want to emphasize that. I've actually been in offices, tried to visit each one of them. COVID got in the way of towards the end there. But I was actually watching people dealing with fire weather and severe weather within their county warning areas at the same time.
Wow.
Right. So that's what I worry about coming apart. I have to say something about balloons. I came out of Wisconsin. I did my postdoc under Vern Sumi, father of satellites, how satellites were going to replace the balloons, and people who want to end, and Joe had to deal with this in the budget, and I put an end to it with arguing with people who said, no, the balloons, we had to show them. Okay, so today, every day, over at NASA Goddard Space Flight Center, there's an evaluation of all the data that goes into numerical models, all the, like 40 different satellite instruments now. You got Argo floats for the ocean. You got a whole range. Aircraft, every 15 minutes. The balloons, those old radio sons, which are not old anymore, they're pretty remarkable instruments, with that vertical resolution of dew point, temperature, and winds, three basic state parameters, all measured independently of each other at the same time. They rank either 2 or 1 on the value listing. They're always in the top 10, but 2 or 1 more recently. It's really amazing. And they make the other observations, especially the satellites, usable within the models. They correct biases, like the warm bias we had in the aircraft data. So you don't want to lose that data set, even though you can't get it over the ocean, et cetera. It's really important. And then for severe weather, you got to have that vertical resolution. You want to deal with the nature of the pre-convective environment, you got to have that. And the radiosonde gives it to you. Now, aircraft does, from the same airports though, but you can get these. And the last thing I'll mention, coming up to the hurricane season, there's this effort to get radiosondes, supplemental radiosondes launched, because they make a difference in improving the track forecast of hurricanes. Those are the same forecast offices that have to close up the radiosonde, and we have to get the data. We don't have to, but we work collaboratively internationally, in this case with Canada and within the Caribbean, to get supplemental soundings from them too, because that westerly flow does influence the track, ultimately the track, the curvature, and et cetera. So all of this is what should make us all concerned, all right? But I got worried real fast when I started seeing that the radiosondes were the first things that were being cut because of staff shortages. So there's already an impact, as far as I'm concerned, that this country can't afford.
Yeah, no, well, hopefully something good comes from this 100-hour long live stream to Save America's Forecast, and we get the Congress to approve the budget for these weather balloons.
Mark, there's another area of the data subject that really needs to be addressed as well.
Okay.
NOAA has an organization that is really a treasure for this country and this country's economy, global economy, as a matter of fact. It's called the National Centers for Environmental Information. Used to be called NCDC in Asheville, but it is the repository of all of the data that National Weather Service has collected all the way back to Thomas Jefferson and before. It is under attack in this administration because it deals with climate. Yeah. This is kind of an Enola Gay syndrome, if you're familiar with that. Mm-hmm. The Google search came out and trying to eliminate any bad references. So the pictures of the Enola Gay, the first aircraft that dropped the first atomic bomb, has been deleted. It's been restored now, but it was deleted from the Air Force Museum because it had the word gay in it. Mm-hmm. Anything with the word climate in it is being subject to the same sort of Google destruction.
Yep.
The search for climate data is automatically assumed to be global warming, which is wrong. Mm-hmm. You and I know better than that. We're not going to argue that point. But the very fact that climate data center has been reduced by about 30% in staff threatens that resource, not just simply for people that are interested in the weather data, but those data go into every engineer that is designing a bridge, a road, a building, or something else that has to survive in this natural environment. They have to know if they're building with the right loading for snow or snow loading on the roof. They have to know what the precipitation amounts will be and so forth, what kind of temperatures they have to operate under. It is that database that makes it easy for the engineers to do their job and support the various economic needs. And I'm very concerned about the fact that is going to be not enhanced, let me put it that way, and it will probably be degraded if we have a major cut in the workforce there.
Yeah, no, I'm glad you mentioned that in CEI data sets. I mean, that stores everything we need and everything we need, especially to do research, again, to improve the weather models, the climate models that we use. And that, it's a quiet revolution, right? That weather forecasting has gotten so much better than 50 years ago. And we need the data to continue improving our models. Okay, so we have about 10 minutes remaining in our panel. So we do have some questions from the audience. We're at about 1,200 viewers on YouTube, which is awesome. Our first question actually has to do from an education perspective. Could be great to answer. How will these cuts affect education for earth sciences? I want to go to school to study earth sciences, and I'm worried how these cuts will affect my education. Would it just be better to go abroad? We could start with Lewis.
I'll take that one.
Yeah.
So one of the things that also happened during the modernization was that the Weather Service started hiring degreed meteorologists. And a lot of these probationary folks that were just let go arbitrarily, not only were bachelor degrees, but masters and even some PhDs now applying for practically every position within NOAA. So the education aspect was certainly influenced by the modernization. And the competition for positions, some of the comments that came out of the commerce, was they don't meet our changing needs. These were the best in the private. We had over 100 people apply for, in some cases, 200 people applying for individual positions, and top people coming out of the military for the technical positions and forecast positions, and people coming out of the private sector. So we spent a lot of time also serving the education community through the AMS, right? Supporting high school teachers in math and physics as they apply to meteorology, 2-week sessions out there in the Kansas City training session. We provided real-time data, not just the surface data, but real-time everything to these same teachers in high schools. We worked with unit data one of my predecessors, Bill Bonner, who's somehow had the foresight to hire me, with Joe's approval, of course, into the Weather Service without 1 day experience on a forecast floor, by the way. They brought me in, and Bill went out to help spin up Unidata. Well, why am I bringing this up? Because we workstation capabilities that were developed in the national centers, the data flow that we just talked about provided to Unidata, we're going all out to 70 different universities. The future, the same people coming out of these high schools now and universities had the same dreams that I had in terms of a meteorologist and eventually getting into the Weather Service. Didn't dream about being a director, though. Let me just say that I worry about that future, but I would encourage the people to stick with it, live the dream. This will pass. This will pass. All right. Getting that education and now in the Earth system sciences, not just the atmosphere, not just hydrology, complicated enough as it is. You got to put everything together these days: ocean, land, atmosphere, cryosphere. It's a lot of educational efforts that are being supported by NOAA, not just the Weather Service, but by NOAA, that I think will be critically important for the recovery from this and for allowing people to realize their dreams just like we did.
Yeah, no, that's so true. Joe, do you want to comment as well, or?
No, I think Lewis has done a good job on that. The education for the future is absolutely critical. What I fear about, if I were really cynical, I would think that these personnel actions that have been undertaken by the government at present have been deliberately designed to cause organizations in the federal government to fail. And it's not just Weather Service. It's the National Park Service. All the scientists in the Park Service are basically gone. The archaeologists, the geologists, the ecologists, and so forth. Services across the country, and it's staff across the country in public service. It's making the question about, do you really need to go? Do you really want to go into public service? Is it really worth the effort? Or are we going to continue to have this kind of uncertainty? That's terrifying to me. That probably bothers me more than any other aspect of what's going on right now, is the willingness for people to go ahead and go into the federal government, go into public service to provide the nation with what it needs.
Yeah, no, that's really, really good to hear. And, both of you touched on how this is affecting, early career scientists. A lot of us, don't have funding anymore. A lot of people can't maybe get postdocs, or losing their graduate student funding, no longer able to, chase the same dreams that you guys had. And that is also just a really sad aspect of this. Okay, but we'll take more questions. We have about 4. We'll take one more question, and then we'll do some closing remarks. All right, let's see. Here's a good one. How can we as citizen scientists support the NWS, like the Storm Spotter certification here in the Northeast Oklahoma office? Lewis, Joe?
Well, yeah, I would just go, spread that out a little bit.
Yeah.
Because one of the things that I've experienced with this is I teamed up with Tom Skilling out of WGN Chicago, and did a podcast and did some interactions, and watched as his, he has like 350,000 followers or something, that in the agricultural area, local towns with local mayors and emergency management community. And the feedback we got was tremendous. I'm telling you, the farmers out there, rely on the weather and climate information that NOAA provides. They also have private sector support, some the ones who can afford it, right? It's amazing to watch them. You have the voluntary observations through that climate reference network that has been established across the country. some of that data got shut down, and the folks out there were the ones who complained and got it turned back on. I mean, they're in the planting season, for crying out loud. I mean, this is not the time to be messing around with these data sets. So it is the citizen science that the Weather Service has embraced. I mean, they have observations that go back 75 to 100 years within the same family, not the same individual. It's passed down, within the families. It's really an amazing thing to watch. And again, their dedication to getting those observations in. And I was also reflecting on one of my first papers that I wrote on gravity waves. I needed hourly rainfall rates. I got it out of that voluntary network, through NCDC. I had to get the data. I had to wait a long time for it, but I'm a patient guy, as Joe knows. And this is there. It's at risk, but those citizens actually vote. Okay, the farmers vote, and I'm not saying who they're going to vote for or what, but they're agitated. I could see that in the feedback that Tom was getting through his linkages. And the mayors, in very Republican areas, have gotten to rely on that fabric again, that collaborative fabric, with their emergency managers, or whoever makes their public safety decisions. So, I think this, from a citizen's perspective and local perspective, there's definitely a buzz out there about what's happening to their data set that they pay for. Right? What is it, $4 or $5 per person per year? So I think it'll be interesting to see how that evolves.
Great. Yeah. So we have about a minute left. So we'll take just maybe closing remarks, starting with Joe. If you have anything you want to say before you leave to our streamers from across the United States and the world.
First of all, I want to thank you for doing this. I think it is vitally important. The National Weather Service really is a national treasure for this country. It benefits every man, woman, and child. It costs every man, woman, and child a Big Mac and a Coke a year to provide that service. And I just want to tell the employees of the National Weather Service that are still there, I really thank you for what you're doing. And I ask you to do the best you can. I know you will. Thank you again.
Thanks, Joe. Louis.
So Mark, again, thank you for doing this and allowing us to be on. And again, it's hard for me to add to what Joe just said, but I want to reiterate that how I know I felt, and I worked for Joe and watched him in action. It was a real inspiration. We worked, it really was. The breadth and depth of what the Weather Service does is not well understood by the people who made those decisions. But the people working for the Weather Service will come. They're not going to allow a system to come up unprepared for. That's my sense. But and thank you, Weather Service, for making sure that the people of this country will remain as best prepared as possible under these circumstances, and just keep on keeping on.
Yeah. No, well said. All right, so that concludes our panel with two former National Weather Service directors, Dr. Joe Friday and Dr. Louis Uccellini. Thank you both for joining us today. We really appreciate your time.
Okay, thank you.
Thank you.
All right, so we are done with the panel segment of our live stream. So we were joined last hour by a panel of terminated NOAA scientists. It was really interesting to hear from that group of folks about, what they do in their day-to-day, how they were laid off by the administration, and also how their work impacts every American. And we also saw that reiterated by the National Weather Service directors just now, Dr. Joe Friday and Dr. Louis Uccellini. Both of these individuals led the National Weather Service and really demonstrated how important it is that the National Weather Service National Hurricane Center, and NOAA as a whole, and the NOAA research laboratories remain fully funded. That's really what we're focusing on here on today. And so really quickly, if you're joining us on the live stream, just a brief introduction of why we're gathering here today. So this is the Weather and Climate live stream. It is a 100-hour-long live stream to save America's forecasts. It is a non-partisan event, right? The weather, whether it's a few days out or climate change, both of these things affect every American citizen, no matter what political alignment you are. And I think in the last two panels especially, we really saw how these people are passionate about what we do as weather and climate scientists, and we're really just trying to predict the atmosphere and the ocean and how it will change under climate change, so that we can better protect American lives and livelihoods. So we are approaching hour 5 here. And so we're actually going to start the next segment of our live stream, which is the beginning of our keynote segment. So every night, tonight, Thursday, Friday, and Saturday evening, during prime time, we will have an incredible list of keynote speakers who are kind of like icons in our community. And so you may not know some of them, but we are very familiar with them, talking about their papers, their research papers, or seeing them on television and things like this. And so tonight we have an incredible, as I said, list of keynote speakers. You can actually go to the Weather and Climate Livestream website to see our list for tonight. But our first keynote speaker, we're going to bring on camera on the live stream right now, Dr. Paul Markowski, who is a distinguished professor of meteorology at Penn State University, where he also serves as head of the Department of Meteorology and Atmospheric Sciences. And Dr. Markowski, I'll just start by saying I remember seeing a talk by you when I did the Penn State weather camp in high school, and that was that was maybe 15 years ago, I think. Yeah, maybe like 2010 or 2011.
Wow, that's amazing. Yeah, weather campers are everywhere.
The weather campers are everywhere. Yeah, no, I still talk to a few of the weather campers, which is great. We always stay in touch. But yeah, so we're going to also bring up Dr. Markowski's slides. And today he's going to be talking about tornado science. So Dr. Markowski, you can go ahead and take it away.
Sure thing. Thanks, Mark. Let's see here. All right, so I'm going to start with an anniversary. So this Saturday marks the 40th anniversary of one of the worst tornado outbreaks in U.S. history. It was notable not just because of its devastation, but because of where it occurred. It occurred here in my part of the country, the northeastern United States, where here in Pennsylvania, in just the span of a few hours, as many Pennsylvanians were killed by tornadoes as in the entire prior history of the state of Pennsylvania. What's also interesting about this day is that since May 31st, 1985, only 2 days have been deadlier. Both were in 2011, the Joplin, Missouri tornado in May of 2011, and then the outbreak in the southeastern US on the 27th of April, 2011. And if we look at the trend, this is hot off the presses. I just got this a couple of days ago from Harold Brooks, a colleague of mine at the National Severe Storms Laboratory in Norman, Oklahoma. What this curve shows is from 1875 until up to a week ago, the death rate from tornadoes in the U.S. The individual years are the purple dots, and then the smooth trace is what's shown in red. So there's been a heck of a decline over the decades. It was pretty flat from the beginning of the record, 1875, until roughly World War II. And then since the Second World War, a steady decline. A couple of other things to point out here that were on Harold's slide that he shared with me is that 2011 stands out as a real modern outlier. If you look at just how anomalous 2011 was, it was kind of like a typical year back when my grandparents came of age. So that's how things used to be all the time. And everybody who knows something about weather remembers 2011 as a horrendous tornado year, but that's how it used to be all the time. So we've come a long way. And that's the story I want to talk about this evening. One other thing to point out here is black dots and the unfilled squares. These are deaths in permanent homes versus manufactured homes. And you can see that we'd be doing even a lot better if we had everybody in a permanent home. So what's kind of contributed maybe to this leveling off in time is the fact that there's been a growth in manufactured homes, and those just don't fare as well in tornado wind speeds. So the reasons for this success story, you could call it, this is what I'm going to unpack over the next few tens of minutes. So there's a lot behind this data set. I guess in summary, it's a combination of better warnings, communication of those warnings, and greater public awareness. But what goes into the better warnings? Well, one aspect is technology, of course. So we now have a nationwide network of Doppler radars. These are called the WSR-88Ds. And that's been a game changer from a detection standpoint. And also data from these radars are ingested into our computer models, which are used to make predictions. So more on that in a little bit. We also, of course, have satellite technology today. This animation on the right is from just a couple of Sundays ago. These are 1-minute snapshots of the clouds. Really, compared to what was available when I was a student, this is just mind-blowing imagery. So this is also very important, especially when it comes to ingesting data into computer models to get better predictions, but also because before clouds start making rain, we can't see them on radar. So the satellite imagery is really important for monitoring the growth of clouds into what could potentially become dangerous storms. And then I've mentioned computer models a couple of times now. So these are just equation solvers. So they solve the equations that govern the atmosphere, and they require the world's fastest computers, and improvements have been steady for decades. A 7-day forecast nowadays is about as good as a 3-day forecast was when I was a student. So, and they're only getting better. And in fact, now we run simulations in real time operationally that forecasters have access to, and the public as well, I might add, that resolve individual thunderstorms, not just the larger scales, but the smaller scale stuff. So this has also been, I sometimes have to pinch myself when it comes to looking at how good these predictions are these days. I just want to take a quick side trip to talk about, to put into context just how far we've come. So the first tornado forecast that you might remember when I showed the beginning of that decline in death rate, that was roughly around World War II or so. So what's often known as the first tornado forecast, or the beginning of modern tornado forecasting, was March 25, 1948. And it turns out 5 days before that, on the 20th of March, a tornado hit Tinker Air Force Base, did a lot of damage. And 5 days later, this is you don't have to understand what all the details are in this weather map. The point is that this is a continental scale weather map. We're not zoomed in on Oklahoma. And this is the whole western 2/3 of the US. You can see the outline of Texas here and over to the West Coast. And so based on a continental scale weather map, these two Air Force forecasters, Lieutenant Colonel Fallbush and Captain Miller, were just remarking off the cuff about how it looked kind of similar to 5 days earlier. And a commanding officer overheard them and asked, you mean to tell me there's going to be another tornado today? And they basically said, yes, there's a chance of a tornado. I mean, it's in a way, looking back on this, it's almost irresponsible based on a continental scale weather map, no satellite imagery, very, by today's standards, rather primitive information. They made a tornado forecast for Tinker Air Force Base in Oklahoma City. Lo and behold, a tornado hit the base later that day, just a freak of nature. Same base gets hit twice in 5 days. And the second time around, because they had this preparation for it, they had moved some of the aircraft that had survived the 20th of March event. They'd moved those out of the way, saved some money, and to make a really long story short, Fawbush and Miller gained instant fame over this first tornado forecast. And what was key about this is that at the time, the U.S. Weather Bureau, this is what preceded the National Weather Service, you actually couldn't even forecast tornadoes. It was banned until 1950. And also the FCC forbade the mention of tornadoes on TV and radio until 1954. So it was this event that basically changed the Weather Bureau's stance and the FCC stance on this. It basically catapulted our whole field forward overnight. Again, just by dumb luck. This is a 1 in 10 million or 1 in 20 million sort of event, 2 tornadoes the same place in 5 days, and then making this crazy prediction based on continental scale data, and they nailed it. So that's where we were then. And now, we're talking about these simulations that are, run at 1 hour intervals with updates, in some cases, even every 15 minutes, and we're resolving individual storms. It's really like a pinch me sort of situation that we find ourselves in today. Even looking out for some of the high-end events 7 days in advance. These come from NOAA's Storm Prediction Center. This is admittedly one of the better cases, but there are lots of events like this where many days in advance, there are signals that forecasters skillfully can pick up on to alert the public of impending danger. And today, I mentioned some of the state-of-the-art stuff. It's every 15 minutes we're updating the simulations with the latest information. Much of that information is from radars. The term for this is the Warn-On Forecast System. It was pioneered at the National Severe Storms Laboratory, and really a heck of a team effort. The idea is basically that the weather predictions are specific enough and localized enough and skillful enough that you're almost at the point of issuing warnings before the event has even appeared on radar. Right now, the way we operate is that we kind of have a large area that we look at for threat, but then once individual storms go up, we look at the radar to see where the specific hazards are at that moment. But with the Warn-On Forecast System, we're finding that there's actually some predictive capability where we can anticipate even before the radar shows something is happening, that in fact, something's very likely to happen in the very near future. One other thing I want to point out, in addition to technology and better forecasts, is the forecaster training itself. And forecasters could be in the government, private sector, in the broadcast industry. So having humans and their insights has also contributed to this long-term decline in tornado death rate over the years. And what goes into better training? Better understanding of how things work in the atmosphere. So it would be, it's hard to get past this without saying something about advances in scientific understanding. This is where people at universities like myself come in. A lot of this is observational, either radars and field projects collecting data, UAVs, drones that is, swarms of small balloon-bearing sensors, instrumented automobiles, other devices. We've had several major initiatives over the decades from which we've learned quite a bit. Simulations, not like what the Weather Service uses, but run offline, not for operational purposes, but for the purposes of understanding the really small scale dynamics of tornadoes, essentially the nuts and bolts of how tornadoes form. Some of the stuff is just old-fashioned pencil and paper theoretical work. So this has gone on for decades. The first simulations, I mean, this is a state-of-the-art simulation by Lier. I mean, it's incredible. You're talking terabytes of information in these data sets. And this is stuff that has been going on for about half a century now, the simulation aspect of this. And the lion's share of this has been supported by the National Science Foundation. So it's publicly supported. More on that in a little bit. And then with respect to communication of warnings, of course, this is where the broadcasting industry really plays a huge role, but we've got some markets in TV now where the public is so savvy that the TV on-camera meteorologists can show Doppler velocities, not just reds where it's raining hard or maybe there's hail, but I mean, here's an example of the forecasters showing greens and reds, which are Doppler velocities, and in some parts of the country, the viewers are used to seeing this all the time. It's incredible. We have now warnings pushed to our mobile phones. Almost everybody listening has probably gotten one of these alerts for something: flash flood, severe thunderstorm warning, perhaps, or tornado warning. So that's also been a big game changer. All right, so a lot has gone into this general trend in time, and what I would say about it, to kind of wrap up this part of my presentation, is that we have, hands down, and it's really not even a close call, in the US, the #1 tornado prediction system on Earth. And it sounds hyperbolic, but in the history of the world. I mean, when you think about where we are today with cell phone warnings compared to where we were in 1948 with the first tornado forecast, it really is almost, you know, this is the equivalent of landing a person on the moon. And none of this would have been possible without sustained, long-term national investment in innovation, technology, and human capital as well. All right, so the rest of the talk, I mean, this is everybody wants to know something about what we've learned about how tornadoes form. So that's what I'll shift to now. So May 31st, 85, the types of storms that were responsible for these tornadoes were a type of storm known as supercell thunderstorms. And if I were to use as few words as possible to define one of these supercells, I would just say it's a storm with a rotating updraft. And the fancy word for this is mesocyclone. When you look at this imagery, it takes no imagination to see the rotation in the cloud. This is what the radar is seeing. The radar is usually not seeing the small scale tornado that can fall from the thunderstorm updraft, but it's the radar is typically detecting this broader scale mesocyclone rotation. But these supercell storms are the ones that produce the vast majority of headline making tornadoes. Not all tornadoes, but if it's one that is responsible for large casualties, large high-end damage, it was almost certainly a supercell. And if we look at the radar characteristics of supercells, the giveaway is this feature called a hook echo. So what we're looking at here, the fancy term is reflectivity. It's just basically power bounced off of raindrops that gets captured by the radar. We see reds where there's heavier rain or hailstones. And the hook is named because it's hook-shaped. And that's the part of the storm where rain is getting wrapped around the swirl of the mesocyclone. If we look at the Doppler velocities, this is typically colored green and red. And you have to know where the radar is. In this case, the radar is down to the south. And the reds are where winds are blowing away from the radar, and the greens are where it's really the raindrops that are moving. That's what the radar is detecting, but the raindrops are embedded in the wind. So we infer winds toward the radar where we have green. And where you have green next to red, that differential in velocity implies rotation. And so this is essentially one of these mesocyclone detection tools. And if you look at where the mesocyclone is, it matches up with the tip of the hook echo. So that's where the spiraling rain band is. If we look at other hazards from supercells, big hail is another one. So these storms have incredible updrafts. That's also what makes them a tornado threat. It's not unheard of to have updraft speeds exceeding 100 miles an hour. If you ever hear about 2-inch diameter hail or bigger, guaranteed it was a supercell storm. And in fact, right at this hour, although they might not be out today, but we have another field project going on. So this is what we do in science. When we don't understand something, we try to collect data and analyze the data. And right now, we have a National Science Foundation project taking place on the Great Plains called ICE-CHIP, which stands for In Situ Collaborative Experiment for the Collection of Hail in the Plains. It's NSF sponsored, and you can follow them along in real time. If you click on the website, you can see where they are today. I think today's a down day. I apologize, I didn't look before coming on the air. But the next day when there's a threat on the plains, I can guarantee you they'll be out collecting data, trying to learn more, gain greater insight into how big hail forms and how we can better predict it. Back to the tornado story. So how do tornadoes form in general, or how do intense vortices form in general? So I like to start with the easy part first, which for tornadoes, it's actually the end stage. It's the last stage of tornado formation. That's the easy part. And it's due to something known as conservation of angular momentum. If you've ever watched figure skating or watched water go down a drain, you're familiar with this. So it's just the principle by which if you bring in fluid to the hole in the drain, it spins faster. Or if you're a figure skater and you bring your arms inward, you spin faster. This principle we've actually known about for a really long time. It even predates our understanding of Isaac Newton's laws of motion. So this has a long history in the field of physics, and when we apply it to the atmosphere, we rely on it to explain how tornadoes form. But when it comes to applying that to the tornado problem, essentially the big questions are this: where does the angular momentum come from? In the figure skater's case, we know it's from using one of your legs to push off of the ice and spin yourself around. In the case of water going down a drain, when you get out of the bathtub, or if you maybe make a splash in the sink, your hand actually was a source of angular momentum. But in the atmosphere, it has to happen naturally. So where does it come from? And then what causes it to be drawn toward the axis of rotation? It has to, again, happen without humans pushing air toward the axis of rotation. So what's going on exactly? So that's what we'll talk about. It turns out there's some clues in the ingredients of supercells and tornadoes. So here we have a supercell storm, and if one of our tools is weather balloons. We launch a balloon outside of the storm, and from that we can assess how temperature decreases with altitude. And typically in thunderstorm environments in general, and especially in tornado producing thunderstorm environments, that temperature has to drop really fast with height. So if you force me to put numbers on this, it's about 25 degrees Celsius over the lowest 5 kilometers. So let's call it, if you like Fahrenheit and feet, 45 degrees Fahrenheit over 16 to 18,000 feet or so. And if you look at kind of what these yellow dashed lines are showing, it's just kind of mapping the cloud imagery to the locations on this chart of temperature versus altitude. And then one other trick we can employ, and this is using the laws of physics and chemistry, is we need to know the temperature inside of the cloud, because it's warmer inside of that cloud. And the fact that you can see all this bubbly motion to the cloud, that is a visual manifestation of what's called buoyancy. It's the same principle that allows a rubber ducky to float on water. It applied to a fluid, the air inside of that thunderstorm updraft is less dense than its surroundings, just like the rubber ducky is less dense than its water. If we have warm air in the thunderstorm, it's less dense and rises pretty vigorously. So you might be tempted to think, okay, well, we need to launch a balloon outside of the storm, then another balloon inside of the storm. But it turns out we don't need to launch a balloon inside of the storm. We can get the temperature on the inside of the storm from the laws of physics and chemistry, and that's what's plotted on the red curve. And it turns out the red curve here is to the right of the blue curve, which means that it's warmer inside of that cloud. And if we just shade the area between the red and the blue curve, the more area we have, the bigger the temperature differential is, the warmer it is inside of that cloud compared to its surroundings. And the fancy term for this is CAPE. It stands for convective available potential energy. This was not a word I dare use around my kids or my parents, but I heard it in popular media a few months ago, and I thought, oh, maybe it's okay to use this term now in a public talk. So I'm swinging for the fences. The public knows a lot more nowadays than 30, 40, 50 years ago, and there's too many people to name to give credit for that. But the more area you have here, the more intense the thunderstorm updraft is. And the name of the game is getting the red curve to be more to the right of the blue curve. And you do that by having a lot of humidity in the lower atmosphere. And that's why tornado days are so hot and humid near the ground. They're really uncomfortable days. And that's because those environments give rise to these profiles that have a lot of area, a lot of convective available potential energy. And then one other ingredient is, looks like my slide just froze. Just give me a second here. There we go. Large changes in wind speed or direction with altitude. So the fancy term for this is wind shear. And typically you want to have at least a 40-mile-per-hour difference over the lowest 6 kilometers or so. So roughly over 18,000 feet. And in fact, this profile that I'm showing you of both temperature and wind, this actually came from a high-end tornado environment, one of those 2011 tornado days near the Birmingham, Alabama tornado that day. So how do the ingredients make a tornado? We'll start with a look at a storm from afar. So we're kind of all armchair storm chasers right now. You can see the mesocyclone in the cloud. It looks like it's rotating. You can see the striations in it. We're looking off toward the setting sun, so roughly to the west. And there's wind shear in the environment. That's that variation of wind with height. Winds are blowing toward the storm at the ground. They're blowing out of the screen above the ground. And that variation of wind with height implies that there's spinning air. And because I'm at Penn State, everything has to include the word football at some point. So this is like football-like spin. In fluids, we call this streamwise vorticity. It's just spin that's aligned with the direction that the football is traveling. So that storm sucks in lots of samples of air. Each one's like a little football. And when you see that spinning mothership in the sky, it's essentially a manifestation of lots of individual air samples with their spin getting converted from horizontal spin into vertical spin. The problem is that this produces spin above the ground, but it doesn't really give us a tornado. So it can explain that mesocyclone, but not the tornado. So if you look at the far right of the screen here, we see rain. That's where it looks a little fuzzy, a little darker. That's rain falling out of the sky, and where it evaporates, it cools the air and the air sinks. The sinking air is turned to downdraft, and it turns out that along that downdraft trajectory, there's a horizontal temperature variation. It's warm out where we are, where we're observing the storm. We're just out in the clear air. It's a nice warm day, but in the rain, it's cool. And where you have cool up against warm, it torques the air. It's another source of horizontal spin, just like we had out in the far field on the left of the storm. But the difference between this airstream and the first one is that this airstream's headed toward the ground. So we can end up with rotation about a vertical axis very near to the ground. And at this point, we'll just zoom in, and to get a tornado, it's just the figure skater effect at this point, conservation of angular momentum. So we've explained where the angular momentum comes from. It comes from that variation of, well, there's two sources, variation of cold to warm along the edge of the rain, but then there's also angular momentum just away from the storm because of the ambient wind shear. All that comes together to give us this rotation at the ground, which can be intensified to a tornado if that air is not too cold and if there's also strong suction from above. So if it's not very cold and there's that strong suction, voila, the figure skater spins very quickly because the air, in essence, can be drawn inward to a small radius very easily. A movie's worth, well, they say a picture's worth 1,000 words. A movie, I guess, is worth 1,000 pictures. So here's a movie that shows all of this really great. You can see the rain on the right, The updraft is in the foreground where that flat cloud base is. So you can see air getting sucked out of the rain here and acquiring a lot of spin as it gets pulled upward. And in fact, this storm came very close to making a tornado right in there, right now. Very intense rotation. It didn't come quite, didn't go all the way to making a tornado, but it came about as close as you can get without carrying on to making a tornado. So why is tornado forecasting still so hard today? Well, one issue is that satellites see what's going on way up here. Radars are seeing down lower where there's raindrops. Where there's not raindrops, the radar doesn't see so much. And the width of the radar beam is often too broad to resolve the small scale structure of the tornado. It's better at detecting the broader scale mesocyclone. And of course, a lot of this stuff, the really interesting stuff is going on below where the radar is seeing things. So there's some technological limits for sure, but there's certainly some areas where scientists like myself are still trying to understand more. One is that not all supercells make tornadoes. So we're still trying to understand why some storms like this one can have a really intense mesocyclone where you see the blues and the reds or the greens near the red. That's where there's the mesocyclone, really intense. But this storm didn't make a tornado. But yet this storm here has a rather unremarkable radar signature, but yet it's producing a tornado. So this is one reason why warnings there's still room for improvement, and that's where basic science research can play a role. There are other storms that have a relatively unremarkable radar presentation like this one in my part of the country in the Northeast. Where is the tornado? I mean, I could show this to people with advanced degrees in meteorology, and I'm not sure they'd find it either. It's actually that little thing right there. If you issued a warning every time you saw that, you'd have a false alarm rate of probably 99%, but yet this also produced a tornado. So this is a real challenge for people in my line of work. Even though this was a weak tornado, if you're in a bad spot, a weak tornado can be deadly as well. There are other days when we have lots of storms on radar, and not all of them are tornadic. In fact, even on tornado outbreak days, it's virtually unheard of that all storms would make tornadoes. Most, even on the outbreak days, don't make tornadoes. And even the ones that do make tornadoes aren't making tornadoes all the time. So there's a lot to learn yet to explain those discrepancies. The technical term for this is chaos. It doesn't sound very technical. But actually, it was a term coined by a person named Ed Lorenz at MIT. And in fact, if you remember the film Jurassic Park, they were talking about chaos in this scene here, although maybe I'm dating myself. Not everybody's seen Jurassic Park. Everybody's seen Price is Right, though, and Plinko. That's the best game, right? So Plinko is a great demonstration of chaos, meaning that you move the Plinko chip just a small amount at the top of the Plinko board, and the outcome at the bottom is almost unpredictable. I mean, this guy who nails it maybe it looked like he had some predictive capability, but he just got lucky, right? Well, the same thing happens in the atmosphere. Here we have 25 of these supercell storms being simulated. All of their environments are essentially identical, but the white little lines that you see coming off of those are tornado tracks in this simulation. And all of these make tornadoes at slightly different times, slightly different durations, very different intensities, and yet the environments were all identical except for essentially infinitesimally small temperature variations. It's the game of Plinko, but applied to the atmosphere. So there are real predictability limits when it comes to predicting things that are really small scale, like a tornado. There might be some inroads we can make with artificial intelligence, but this is another thing that people in my line of work have been working on. So I'll close with these last few slides. I don't have time to talk about all the hot research areas that people are working on. I mentioned chaos is one, understanding the behavior of storms, how they're affected by terrain or the underlying vegetation service. Machine learning or artificial intelligence is revolutionizing so many fields. Tornado research and tornado prediction are going to be no different. Longer term, like seasonal predictions, effects of climate change on tornadoes, and how tornado warnings are communicated and interpreted. We're still improving those methods as well. There's some people doing really cool stuff right now down at the National Severe Storms Lab. Facets is the program where they basically, the idea is use high resolution, rapidly updating probabilistic predictions that are generated, and you pass those on to the public and emergency managers for a more nuanced risk assessment and better tailored communications. So that's pretty wild stuff. It's light years beyond what we were doing in the 1940s and 50s. We're even at the position now where we can look at how winds affect structures, loads on walls, what's called progressive structural failure. At what point does the wall fail? We can stop the tornado simulation, remove the wall, and then resume the tornado simulation to better understand it's a two-way street. The structure itself affects the tornado, but the tornado also affects the structure. I started this talk with a mention of an anniversary, the May 31st tornado outbreak anniversary, but this is another personal anniversary for myself. 30 years ago this month, I was in Oklahoma as an undergraduate meteorology student at the University of Oklahoma at their NSF-sponsored research experiences for undergraduates program. We call these REUs in my field. And I can say that this is what got me on the trajectory I ended up on. If it had not been for this REU program, nothing you've heard in the past 41 minutes would have happened. I don't know what I'd be doing, but it wouldn't be research on tornadoes. So this was a really impactful thing for me. And I would say we can draw a straight line between cutting these sorts of programs and having a drop in our country's future scientific capabilities and science talent. All right, let's end on a happier note. So this was a storm chase I just went on 2 Sundays ago in Oklahoma near Arnett. A lot of YouTube video of this tornado. Was well warned for. And I'll just close by saying that I'm thankful that there was no loss of life from this tornado. And I hope that these great tornado warnings, which today we mostly take for granted, I hope they'll continue to be as skillful as they've been over the recent decades. So thank you very much.
Thanks so much, Dr. Markowski. That was an excellent presentation on the science of tornadoes, and also some great personal anecdotes about your time. First of all, getting that weather drive, and also your experience at Oklahoma. That was really interesting to see. All right, so we're now going, we have about 5 minutes left. We're now going to open to questions from the chat. So if you guys have a question for Dr. Markowski, you can go ahead and put it in the chat. We have someone behind the scenes kind of looking at those questions and putting them up for us. So Dr. Markowski, our first question from Camille, I'm curious, does Europe use forecasting technology just as advanced in the US, or does it depend on the funding entirely? I've noticed the forecasts in the US are more accurate than when I'm in the EU.
Yes. I mean, this is an American success story. Our tornado predictions from 5, 6, potentially 7 days out, all the way up until T-minus a few hours, until it's warning time, it's go time for you to take action. There is no country on earth that rivals what you get in the United States. Europe, Asia, South America, nowhere. In Europe, it varies a lot from country to country. Some countries in Europe have pretty good radar data that you can even access on your smartphone in real time. But as far as getting warnings pushed to you or very targeted warnings, you're not going to find that anywhere on Earth like we have here in the US. We just kind of take it for granted here.
We do, I agree, yes. Okay, our next question from the audience. Let's see, how much will tornado forecasts be impacted by the cuts to our research?
Yeah, that's a good question. I don't think we know yet. They will be impacted. I don't think we know just yet what the final budget's going to look like, but a lot of the damage has already been done, even without official cuts at the National Science Foundation, for example. There haven't been as many grants being processed because of staffing issues and some other things going on. So even without cuts from the budget, there have been effectively cuts to our ability to continue pushing the envelope and understanding things. And then on the NOAA side, that you heard the Weather Service directors talking about, loss of some of the balloon launches and other aspects of just maintaining enough bodies in the office to keep operations going. Yeah, there's just no way that there will be no impact. How serious the impact is and whether it can be rebuilt at some point later on are open questions. But I think the takeaway is we can take nothing for granted.
Thank you for that. Our next question from the audience, what causes the green tornado sky?
Oh, that is a really good question. I don't know who planted that with you, but that's going to bring me to my knees. I think there's still debate on that. In science, it's okay to say, I don't know. And that's why we do science. If you know the answer to everything, then you're kind of out of business as somebody like myself. So years ago, there was speculation that hail played a role, a low sun angle combined with the path that light would take through big hailstones. I don't know that that's been entirely refuted, but I know there's some competing theories on that as well. So I'd say that the safest answer for me, and admittedly this is a bit outside of my expertise, but I'm going to say that the jury's still out on that.
Okay, great. We'll keep following the science on that. Okay, these are really good questions from the audience. Here's one from HK. Is there a difference in likelihood for tornadoes to hit rural versus urban areas? I think it's a common misconception that cities are immune, and I've read that it's just a matter of chance.
That's right. So two aspects of this. One is that objects on the ground definitely have some influence on tornadoes. So a building will influence a tornado. But we don't know the sign of the influence. In fact, so what I mean by that is some buildings potentially could enhance tornadoes just as likely as they might be to weaken a tornado. So we don't know, but they definitely have some influence. But yeah, a city is not going to stop a mature tornado. I mean, if you think about a thunderstorm, it's 50,000 feet tall roughly. So that's 10 miles tall. And let's say the horizontal dimensions are also roughly 10 miles by 10 miles. So a thunderstorm is 1,000 cubic mile entity. That's massive. When you just look down from an airplane at mountains and cities, they look so insignificant from the air. It's just not, in terms of total energy available to that 1,000 cubic mile thunderstorm, it's not going to have an obvious effect other than affecting the small scale details of the tornado in ways that, again, we just don't know. It could go either way, actually. It is true that you hear about more tornadoes not in cities than in cities, but that's just simply because the area of the United States that's not a city is a lot larger than the total area that is urban.
Yeah, no, that makes a lot of sense. Here is, actually, we'll take one more question. And this one kind of has a climate change question. I feel like we have had more tornadoes than 10 or 20 years ago. We never really had them on a yearly basis when I was little. Has climate change made tornadoes different year to year?
Yeah, so that's a tough question because we're really reliant in part on tornado reports. Tornado reports have all sorts of challenges because a lot of tornadoes occur in areas where there's no damage done, so we don't have any idea how intense the tornado was if it was just over grassland. So in terms of detecting trends in intensity, I'd say no chance, at least not using direct reports. In terms of just the count, how it's changed, same issues. There are tornadoes that are undetected or underreported. There's certainly been a trend in the total tornado count over the last half century, but I think most people in the business can explain away that trend just as better detection, fewer sparsely populated areas. The population in the U.S. is growing. We got people with smartphones, recorders. It's getting harder to have a tornado go completely undetected, although it occasionally can still happen. But with climate modeling, we don't necessarily have to resolve tornadoes directly. We can look at climate model predictions of environments that we know are tornado friendly and look at trends in those. And we can at least say, well, in the future, there'll be more days that can support tornadoes than there were in yesteryear. And there are climate models that show an increase in the number of tornado capable days, we could call them. but to get a tornado, you need a storm to develop in a tornado-capable environment. If the tornado-capable environments have other subtleties that maybe make storm formation in those environments less likely, you might have more capable, larger scale conditions, but actually fewer events. And that's where kind of the cutting edge is right now. We're still trying to sort that stuff out. One thing that we have found, this will be my last point that I make, is that there does seem to be a trend in the number of tornado days per year going down, but the number of tornadoes on the tornado days going up, so that kind of the total trend it's unclear. But that's kind of interesting. I don't know. I don't study that. I don't know if the people who do have a better explanation for that. Off the top of my head, I've got no idea why that's the case.
Mm-hmm. All right, awesome. Well, thanks so much, Dr. Markowski, and thanks to the audience also for posting those really good questions. Yeah, we really appreciate your time talking about tornado science. So thank you.
Thanks, Mark.
Nice. All right, so we're going to, before we move to our second keynote speaker of the evening, if you're just joining us on the live stream, we have over 1,300 viewers now. That's really exciting. And we will approach hour 6 during the next keynote, so hour 6 of the 100-hour-long live stream. So just a reminder that this live stream, right, it's put on by a group of meteorologists and climate scientists, and we're just featuring talks and some panels featuring climate scientists and meteorologists. And it's really an opportunity for us as scientists to show the value of our science to the American public. And it's also a reminder of the fact that as a country, we have invested in the National Weather Service, the National Hurricane Center, the rest of NOAA and all of its research laboratories for decades, since the 1940s and 50s. And so what we're doing here today is really just, these cuts that are currently experiencing, of course, are damaging to our ability to predict the weather, to do the research that allows us to improve these forecasts even further. And so that's why we're holding our live stream today. And it's also just a great opportunity to interact with the public. And you guys have been posting some really great questions that our scientists are really enjoying answering. So we really appreciate you being on today. Now, if you are feeling good, you're really enjoying your time here, you can do some action. We have a link you can press. There we go. Someone just put it up. You can go to wclivestream.com/act, and that has a pre-filled letter you can send to your representative. So again, this is a nonpartisan event. The weather, climate change impacts everyone. It doesn't matter what part of the political spectrum you are. This is just, it affects everyone. And so if you could take the time to fill that out, you don't need to. It could be a good way to continue fully funding the National Weather Service, the National Hurricane Center, NOAA, and all of these amazing scientists whose passion is understanding the atmosphere and the oceans, and also protecting American lives and livelihoods. All right, so we'll go ahead and move to our next keynote speaker. Someone backstage will bring on Dr. Ben Santer. Great, thanks so much, Ben. It's great to see you. So Ben is Dr. Ben Santer, retired from Lawrence Livermore National Laboratory in 2021, and he is also a contributor to all 6 IPCC or International Panel on Climate Change reports, and is still actively working in climate science. So we're shifting from the tornado weather side of things to more of a climate science-y talk. Ben, it's great to have you, and you can go ahead and get started.
Thank you very much, Mark, and thank you everyone who's listening today. This picture was taken by a former colleague of mine, Céline Bonfils, showing a human handprint on a dried out lake bed in Colorado. And this actually made the cover of a Nature climate change paper in which Céline and co-authors showed that there were now identifiable human fingerprints on drought, on things that we actually care about. And I'm going to talk to you a little bit today about the history of our efforts to fingerprint the climate system and to disentangle human and natural effects on climate. Well, Paul in his previous talk just used the phrase, the jury is out. And that was definitely the case in the first report of the Intergovernmental Panel on Climate Change, the IPCC, back in 1990. So just a quick informer here, the IPCC was set up in 1988. Their goal is to advise the governments of the world about the physical science of climate change, about impacts of climate change on things we care about. Think health, agriculture, energy resources, water. And they also advise the world about possible mitigation and adaptation policies for reducing the effects of climate change. The first report of the IPCC in 1990 essentially said the jury is out. They could not, at that time, formally identify human effects on global climate and said that the unequivocal detection of the enhanced greenhouse effect from observations is not likely for a decade or more. Fast forward 5 years, and the situation was very different. The bottom line finding of the second IPCC report was these 12 words, and they're forever engraved on my memory. The balance of evidence suggests a discernible human influence on global climate. It wasn't eureka, there's water in the bathtub, climate scientists understand everything, but it was the first time, I would contend, that the international scientific community said formally, we can identify a human-caused climate change signal. I was unfortunately or fortunately, depending on which way you look at it, the convening lead author of the chapter 8 of the report in which those 12 words occurred. And I spent roughly 2 years of my career defending that balance of evidence finding, the process by which it had been reached, and explaining the scientific underpinning for that conclusion. Well, the third assessment report in 2001, 6 years later, came to a much more definitive conclusion than our wimpy balance of evidence suggests finding. Importantly, the third assessment report tried to quantify how much warming was due to human activities. The fourth assessment report introduced this likelihood language in 2007. Most of the observed increase in globally average temperature since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. The fifth report in 2013 upped the likelihood language and went with extremely likely, where that phrase had a specific probabilistic meaning, greater than 95% probability that the statement was correct. And the most recent sixth IPCC assessment used this extraordinary word, unequivocal. It is now unequivocal that human influence has warmed the atmosphere, ocean, and land. So in IPCC world, this is the arc of history. And I'm going to try and explain to you some of the factors that I think enabled this history. So back in the late 1980s, we had a relatively small number of climate models, and they were reasonably simple in terms of their representation, particularly of the ocean, of sea ice. Now, in 2025, we have, in the last IPCC assessment, over 100 different climate models. These are much more complex beasts with representation of many, many different components of the full Earth system, which is why they're called Earth system models, enabling us to really probe the relationships between different components of the climate system, ocean, atmosphere, sea ice, carbon cycle, other biogeochemical cycles. And I would contend that increase in the number of models and in the faithfulness with which they represent the real world climate system has enabled some of this progress. Back in the late 1980s, most of the numerical experiments that people performed to look at human effects on climate focused on CO2. But over time, there's been this richer understanding that by burning fossil fuels and increasing levels of CO2 in the atmosphere, we do many things. We change particulate pollution, for example, these aerosol particles from biomass burning and from combustion processes. We deforest tropical rainforest, and doing that can affect climate locally and even regionally. And the model simulations over time from 1960 through to the present reflect that richer understanding, not only of human effects on climate, but also of purely natural changes in the sun and in volcanic activity. Back in 1995, at the time of the discernible human influence finding of the IPCC, satellite-based records of atmospheric temperature change were basically 17, 18 years long. Now we have records that are 45 years long that give us a much better understanding of global scale changes in dozens of different aspects of climate change: temperature, moisture, sea ice, snow cover, upper ocean temperature. These records, I would argue, have been instrumental in enabling us to evaluate climate models and figure out what their strengths and weaknesses are, but also to understand in the real world, how has climate change manifested. 30, 40 years ago, we didn't have this community-wide sharing of climate model results, if you will, crowdsourcing of climate model simulation output. Now we have that. And through things like the Earth System Grid Federation, we have computer infrastructure for very effectively sharing huge volumes of data among scientists. You can, from the comfort of your own office, interrogate many, many decades worth of climate model intercomparison programs. You can access satellite data. You can compare models with observations. All of this has been transformational. And what I'm mostly going to focus on is this final point, consilience, this coming together between basic theory, computer modeling of the climate system, satellite data, and pattern recognition methods. So consilience, a word made popular by the late E.O. Wilson, who wrote a great book of that same name, is the principle that evidence from independent sources can converge on strong conclusions. And I would argue this is what enabled this arc of history, this consilience between basic theory about the radiative properties of greenhouse gases, how they trap heat, how they interact with incoming sunlight and with outgoing heat from the Earth. The data, like the satellite data that we'll see more in this talk, the computer models of the climate system, and sophisticated pattern recognition methods that help us to separate human and natural effects on climate. Let's start with the theory and early modeling. So this very famous gentleman, Suki Manabe, known to many of us in climate science, back in 1967, published with his colleague Dick Weatherald at the NOAA Geophysical Fluid Dynamics Lab, what's been referred to as one of the most famous papers in climate history. What did Suki and Dick do? They used a very simple climate model, something called a radiative convective model that looked at things in global mean. So it looked at global mean temperature change in response, for example, to changes in levels of heat trapping CO2 in the atmosphere. And the model although I said simple, wasn't really that simple. It had water vapor, it had convection in it, it had the radiative transfer associated with greenhouse gases. And what Suki and Dick found when they increased CO2 in this model from 150 to 300 to 600 parts per million was that the lower atmosphere, the troposphere, warmed, and the upper atmosphere, the stratosphere, cooled. And this was really transformational for people like me. They elucidated the physics responsible for this warming low down and cooling up high. And it gave people like me something to look for in observations. We could then look over time in weather balloon measurements of atmospheric temperature and later in satellite data to see whether what Manabe and Weatherald had predicted in 1967 was identifiable in observations. We also had, starting in the late 1970s, these beautiful satellite measurements of global scale changes in the temperature of the atmosphere. And that's what you see here from our colleagues at Remote Sensing Systems in Santa Rosa and from Chengxi Shu's group, the STAR group, a NOAA group at the University of Maryland. These are beautiful measurements. Microwave sounders on mostly NOAA polar orbiting satellites have measured the microwave emissions from oxygen molecules. And those emissions depend on the temperature of different broad layers of the atmosphere. By measuring at different microwave frequencies, you can produce a picture like this and back out the temperature changes, in this case from the South Pole to the North Pole, and from the surface right up to 50 kilometers above the surface. And they show exactly what Manabe and Weatherald predicted back in 1967. Warming of the troposphere, with largest warming over the Arctic, where there's been a roughly 50% decrease in the extent of Arctic sea ice and snow cover, and cooling of the stratosphere, again, as predicted by Manabe and Weatherald, with the cooling becoming larger the higher up you go above the Earth's surface. The next part of consilience, so we've been through basic theory, the simple modeling of Manabe and Weatherald, the data, the satellite measurements of atmospheric temperature change. Another important component was pattern recognition methods. So this gentleman, Klaus Hasselmann, who looks a little bit like Kenny Rogers, I had the privilege of working together with him when I went to do my postdoc at the Max Planck Institute for Meteorology in Hamburg in 1987. And Hasselmann had published a paper with this title on the signal-to-noise problem in atmospheric response studies in a very obscure conference proceedings in 1979. But essentially, he provided climate scientists with a roadmap for trying to use pattern information to separate human and natural effects on climate. Back in the late 1970s, when Hasselmann published this paper, most scientists were looking at individual grid points, which is what you are seeing here. They were in a computer model dividing up the atmosphere, the ocean, the land surface into a grid, and they were looking at individual grid points at how much temperature increased, for example, at Earth's surface as CO2 increased. And they understood that the intrinsic variability of the climate system would also be present at individual grid points. And that in trying to look at how large, say, the warming due to CO2 increase was, you'd have to look at that relative to intrinsic variability. But Hasselmann's key insight was you can't do this at individual grid points. It's much more effective to separate a human-caused warming signal, which is global in scale, from the noise of natural climate variability if you look at the entire pattern, not just at individual points. And that's what my job was when I went to Hamburg in 1987 to look at fingerprints of human effects on climate. We were very lucky because we had the ultimate thought experiment. We had computer models of the climate system in which you could perform these simulations where you just change one thing at a time. You just change the sun's energy output according to our best understanding of how the sun's energy has actually changed over the 20th century. And that's what you see here. These are from simulations performed by the late Warren Washington and Jerry Meal at the National Center for Atmospheric Research in Boulder, in Colorado. And Warren and Jerry took a climate model, the parallel climate model, and ran a number of innovative thought experiments where they just changed the sun's energy output, they just changed volcanic activity, they just changed CO2 and other greenhouse gases, human-caused sulfate pollution, and human-caused changes in ozone. And in each one of these postage stamps, you're looking at the vertical fingerprint. The temperature changes from the surface right up to 30 kilometers in response to that one thing. The message from this kind of work is they're different. And this was Hasselmann's insight again, that different factors, natural and human, because the sun and volcanoes are natural factors, human-caused changes in greenhouse gases, sulfate pollution and ozone are non-natural things we've done to climate. One could use these pattern differences to disentangle the observations. And that's what my colleagues and I have tried to do really for the last 30 years or so. We published a paper a couple of years ago in which we did this fingerprinting with atmospheric temperature from close to the Earth's surface right up to 50 kilometers above the surface, where Manabe and Weatherall predicted in 1967 that we should see a very strong human-caused stratospheric cooling signal. And this was our conclusion. Extending fingerprinting to the upper stratosphere with long temperature records and improved climate models means that it's now virtually impossible for natural causes to explain satellite-measured trends in the thermal structure of the Earth's atmosphere. So what did we do? And what I'm going to show you now is a sequence of slices through the Earth's atmosphere. These are from the satellite temperature measurements, from the South Pole to the North Pole, and from the surface up to 50 kilometers. And we're going to step through these 3 years at a time. And if you're paying attention, you can see that what's happening in the satellite data over time, from 1986 through to 2024, is that the lower atmosphere, the troposphere, is warming and the upper atmosphere is cooling, just as Manabe and Weatherall predicted. We can compare this sequence of observations of the vertical structure of temperature change with model projections of how climate should have changed in response to human influence. And that's what you see here. Like the Manabe and Weatherall picture from 1967, it shows warming low down, cooling of the stratosphere, with cooling amplifying the higher up you go. And you can generate some measure of pattern similarity between that sequence over time there of the satellite data and the searched for human influence fingerprint. And that's what this time series shows you. And you can see that the time series shows a trend. That's the red line, which confirms what you can see with your eye. Over time, the data are becoming more similar to the human influence fingerprint. But how can we tell whether that red line is significant or not? Maybe it's just due to the random effects of natural internal variability in the climate system. To answer that kind of question, we repeat fingerprinting, but now with simulations where we know that there's no human influence on climate. These are so-called world without us or control run simulations. And again, we're going to step through these. They're from 9 different state-of-the-art climate models, many, many thousands of years of simulation. And we're stepping through these 300 years at a time. Again, slices through the Earth's atmosphere from the surface right up to 50 kilometers above it, from the South Pole on the left to the North Pole on the right. We can compare these world without us patterns of climate change with the searched for human influence fingerprint. And again, we calculate some simple measure of pattern similarity. I'm showing you the first 450 years of this. We can fit trends to that, just like we did with the red line in the last picture for the actual satellite data. These blue trends, just like the red trend, are 39 years long, and we can build up a distribution of the time increasing similarity between the fingerprint and natural climate variability. The kicker is that what we actually got when we compared the fingerprint with the satellite data looks nothing like this distribution of natural climate variability. Which enabled us to reach the conclusion we did in our 2023 paper, that natural causes make it virtually impossible to explain the actual time increasing agreement between the human influence fingerprint and the satellite data. And you can do this not only over the full satellite record, but you can look over 5 years, 6 years, 7 years, 8 years. If you pay close attention here, you can see there's actually a negative trend if you look from 1986 through to 1992. And that's because of the cooling effects in the troposphere and the warming effects in the stratosphere of the big Pinatubo eruption in 1991, which is the converse of the searched for human influence signal. But as you get past the Pinatubo effect, you can see that over time you're getting this increasing similarity between the satellite data and the human influence fingerprint. And this enables you to calculate, well, when could we have known? How long would we have had to measure starting in 1986 in order to be able to see a human fingerprint on climate? If we only measured over the first 5 years, from 1986 through to 1990, well, it's pretty noisy and the signal is still embedded in the noise. But if you go over 10 years, from 1986 to 1995, you already get this very clear separation between signal and noise, and see how as we increase the time scale over which we're looking for the signal, you get even greater separation between signal and the noise of natural climate variability. So why? Why is detection so clear? Basically, it's because the human influence fingerprint, in response to human-caused changes in greenhouse gases, is global in scale. It shows, as predicted by Manabe and Weatherald in 1967, this warming low down, cooling up high. That's what you see on the left panel there, with cooling getting larger the higher up you get above the Earth's surface. Patterns of natural climate variability look fundamentally different. They're much smaller in scale. They show anti-correlations, so variability that is anti-correlated between the tropics and the extratropics. That's what you see here, or between the North Pole and the South Pole. This gets back to Hasselmann and the discriminatory power of looking at patterns. They really enable you to better pick out a signal that's global in scale relative to the much smaller scale noise of natural climate variability. This just shows you the results from 9 different state-of-the-art climate models that were used in phase 6 of the Coupled Model Intercomparison Project, CMIP. These model simulations flowed into the 6th assessment report and really provided much of the scientific backbone for that report. US models are prominent in all of these model intercomparison programs. And the key point here is that all of these individual models show this canonical pattern of warming low down, cooling up high, that we also see in the satellite data in response to human-caused changes in greenhouse gases. The fingerprint is robust. So back at the time of the second assessment report in 1995, one of the criticisms of the discernible human influence finding was, you folks are just looking at temperature. Convince us if there really is a human-caused climate change signal lurking in observations. Go beyond surface temperature and atmospheric temperature. Look at the height of the tropopause, the boundary between the troposphere and the stratosphere. Look at moisture in the atmosphere. Look at ocean heat content. Look at snowpack depth in mountainous regions. Look at runoff from major river basins. Look at the properties of clouds, cloud height, cloud location, cloud optical properties. Look at sea surface temperature changes in hurricane formation regions. Look beyond decadal changes at changes in seasonality, the differences between winter and summer, and do that in the troposphere and in the ocean. Look at, getting back to the first slide, and my colleague Céline Bonfils' work, and many others who have worked on drought now, look at drought. Look at soil moisture, look at other measures of aridity, and do this fingerprinting in each case. Look at patterns of climate change. The bottom line is that people have now done that. And the power of fingerprinting is that it looks at patterns, and the changes in these and many other variables are physically related and independently monitored. They're looked at by dozens of different groups around the world using measurements at the Earth's surface, from space, weather balloons, in the ocean. And it's that consilience of the evidence from many different variables, many different measuring systems, many different groups that is so powerful. The bottom line from all of this stuff is natural causes can't explain the changes that we see. I'm going to end by giving you a brief history of climate change detection and attribution. So I would argue that in the 1980s, most of the initial work looked at global mean temperature alone, basically the surface temperature of the planet. And people tried to figure out, if you want to look for a canary in the coal mine, if you want to look for human effects on climate, where do you look at? Do you look in the tropics? Do you look in the Arctic? Do you look at temperature? Mostly people were in the phase of trying to understand where to look for human-caused climate change signals. In the 1990s, we had the jury is still out, 1990 IPCC report, the second IPCC report with its discernible human influence finding. People are starting to apply pattern-based fingerprint methods to surface and atmospheric temperature, and to better understand that human-caused changes in CO2 aren't the only gorilla in the room. We also have to look at things like human-caused particulate pollution and deforestation. In the 2000s, the 2001 IPCC report, 2007 fourth assessment, scientists did move beyond temperature only to look at regions, to look at individual extreme events like the 2003 European summer heat wave, and to really go beyond using individual models to do this fingerprinting and use multi-model archives to do fingerprinting. 2010's, the fifth IPCC assessment in 2013, people are starting to do what's called event attribution, and importantly, now have access to large initial condition ensembles where you rerun with one physical climate model a numerical experiment, say a CO2 increase experiment, but starting from different initial conditions, enabling you to generate an ensemble of simulations where some underlying human-caused warming signals, say, you have many, many different realizations of natural climate variability superimposed on that. And in the 2010s, people are starting to look at things like soil moisture and things that are more directly important for impacts on human health and societies and agriculture. 2020s, the sixth assessment report of the IPCC in 2021, this word unequivocal, human fingerprints are all over the climate system, atmosphere, ocean, land surface, and folks are beginning to do what you might call quasi-operational event attribution. So within days of extreme events, try and look at how human-caused changes in climate changed the conditions favoring that event or the event's intensity. And that's a sort of brief potted history of DNA. One final thought. As Mark mentioned before my talk, these are defining times and challenging times. We face unprecedented cuts to many of the scientific systems that have enabled what I just described, the satellite data, NOAA satellites, NASA satellites largely, the modeling capabilities at the Geophysical Fluid Dynamics Lab, a NOAA lab in Princeton, the Goddard Institute for Space Studies in New York. The work that I described today would have been far more difficult to do or even to conceive of in a world without the data, the theory, the modeling, the pattern recognition methods. All of that is imperiled. This slide is not AI generated. It's from a Japanese artist, Azuma Makoto, who launched a bonsai tree up to about 30 kilometers above the Earth's surface. And for me, it captures the fragility of this thin layer of the atmosphere that I've been showing you. We know that through our actions, we're fundamentally changing that thin shell of Earth's atmosphere. The notion that we would willfully degrade our ability to understand how and why this thin shell is changing, I think that should be of concern to all of us. Thank you very much.
Great, thank you, Ben, for that wonderful talk. Hello to all of you who are joining us now. I'm Henri Drake. I'm an oceanographer and early career climate scientist, where I work with climate models like Dr. Ben Santer just talked about in the previous talk. We've seen lots of great talks so far, and this next speaker is no exception. But before they join us, let's just remember why we're all here. Weather and climate forecasts are important. We know that they have successfully forecasted changes in climate, and that these changes are largely due to what humans have done, as we just saw using the rigorous fingerprinting methods in the last talk. And US scientists like Dr. Ben Santer have become world leaders in weather and climate prediction. They have developed the first computerized forecasts. They have developed novel statistical methods to robustly analyze them. They have developed the first computer models of climate impacts and carbon pollution, including effects like volcanoes and changes in the sun, changes in aerosols in the atmosphere, and all kinds of networks of observations to validate those models and check our answers. And this excellence is because of all of you, the investments from the public, US taxpayers, and federal funding for this science is really essential. That's what pays the bills. But right now, the funding, proposed funding cuts are affecting all areas of weather and climate science. We already have short-staffed weather stations. We have climate labs that are being shut down or are shrinking or have imminent layoffs in the future. And we need you to help save these forecasts. So we'll drop a link to 5 calls in the description where you can call your representatives and advocate for the support of this science. Okay, and with that said, it is my pleasure to introduce our next speaker, Dr. Bernadette Woods-Placky. Hello, Bernadette. Welcome.
Hello, how are you doing?
I'm good, thank you. So I'll give you a brief introduction. Bernadette Woods-Placky is the Chief Meteorologist and Climate Matters Director at Climate Central, a nonprofit research and communication organization where she helps the public understand the importance of climate change science, impacts, and solutions. Bernadette got her bachelor's in science and meteorology from the powerhouse in the field of Penn State. Before joining Climate Central in 2013, Bernadette was a broadcast meteorologist at several different stations, including in Baltimore, Maryland, where she won an Emmy for Best Weathercaster. Among other awards, she is also a fellow of the American Meteorological Society, and Bernadette is an expert on the links between weather and climate change, and hopefully she will speak to that now. So take it away, Bernadette.
Well, thank you, Henri, and everybody who's not only joining us, but really this crew who put this together. I mean, this is just super impressive, the amount of energy put into this. And I have to say, it's been so fun. I've been watching you all already and the speakers who joined us already. And to me, this is what gives me hope, is the people. It's all of you organizing this. It's all of those jumping in to give these presentations. And this is why we are going to make our way through this challenging time. So I just wanted to set that up. I'm going to talk about a few different things today. So we're going to really go into why we know that our weather is changing because of climate change. And it's because of the science, the scientists, the researchers, the data. That is what's keeping us safe and prepared from our changing climate, is going to drive how we make our decisions going forward. So a quick summary about me. You kind of already did that, so we could sort of move through this slide. But let me figure out how best to move through these slides. Did that just advance it?
I'm still seeing your first slide.
Okay, oh, I saw it. Okay. Thanks everybody for your patience. There's this really cool platform we're on, and it has all these extra fun screens. So it's not your normal Zoom. So it just takes us a moment to get used to it. So I'm going to talk about our changing weather. And our program at Climate Central is called Climate Matters. And that means a lot of different things. So we'll get into this in a few different ways today. First of all, how we know that our weather is changing, why it matters, and what we can do about it. So starting with the how we know. Many of you joining already know this, but I really want to ground us all in the fundamental science of the greenhouse effect. This goes back to the 1800s. This is not challenged by anyone, but we know that in our atmosphere, there are these greenhouse gases. They trap heat. They've been there forever, naturally occurring. It's why we have life on this planet, because without them, all of the heat that comes in from the sun would escape at night and it'd be too cold for life to sustain on this planet. So the greenhouse effect, greenhouse gases, this blanket around our atmosphere. What's happening now is we are adding more of those to our atmosphere. We can measure them and we know what that means. Now, this is where they're coming from. The main sources, and I'm going to highlight some differences here. I have the global emissions by sector and also the US emissions by sector. Because in the US, we drive a lot of big things really far. So transportation is our biggest. You see, agriculture and our land use does come into play. But when you look globally, that sort of flips a little bit here. So transportation isn't quite as big of a piece of the pie, whereas you see agriculture and land use and forestry is a much bigger one. Places like Indonesia, places like Brazil, where we're wiping out rainforests right now. So this is where our greenhouse gas emissions come from. We know that as we measure more in our atmosphere, there's a direct correlation to a hotter atmosphere, and it's trapping that heat. And how it plays out is in a whole host of different ways. We'll focus mainly on the weather aspect of it. And even with, let me go back for a moment too, I'll just give some context here. On the left, we have Celsius, and there's a little bit of Fahrenheit there. So when we talk about Celsius globally, the Paris Agreement goal was to try and limit warming globally to 2 degrees Celsius with an aspiration of 1.5. You see, we're pushing up against that 1.5 already as of last year. But people say, you know, what's a degree? What does that really even mean? Well, a little shift in this, and this is not animating because I made this a PDF, but what it shows you is a little shift pushes you over to the right and puts you in a whole new zone where you're getting a whole lot more red and a lot less blue. And that doesn't mean there isn't still heat and cold. But a little shift in that average, in that curve, really just sets things up differently. And this is how it plays out in our lives, right? So in Phoenix, days above 110 degrees, really have to fundamentally rethink your day when it's pushing up above that metric. We're getting at least 2 more weeks of that. Risky humid heat, Baton Rouge, a month more of that. In Houston, look at the tip from record highs on the top end to record lows on the bottom end. Those record highs are just outpacing record lows. Again, doesn't mean we don't get record lows. It's just consistently we're seeing more and more of those highs, and also less extreme cold. Again, still gets cold in Detroit, but the coldest of the cold days in this analysis have bumped up almost 8.5 degrees Fahrenheit. And this is another way to look at those sorts of numbers. Again, because we have this wonderful world of data and computer modeling that we can look at this. So take an average summer in Grand Rapids and the average summer temperature. Let's project it out to the end of the century. It's going to feel more like Memphis, Tennessee. That's what that means by just a couple of degrees. And you can dive deeper into this data. We have for each one of our 240 dots you see there. Those are the weather stations that we use across the United States here. And we have really driven the code with some of our amazing data analysts at Climate Central that you can look at the record highs to record low ratio for each of your communities and dive in the data, play around with it. And there's the link at the bottom. Another thing that's really a hallmark with our warming climate is that it's supercharging our water cycle here. So when you have warmer atmosphere, that blanket around us, it forces more evaporation. Where there is drought, it's really intensifying the drought. But then in that atmosphere, remembering that we're mainly a water planet, when there's a trigger, more of that precipitation is coming down in bigger buckets and heavier rainfall events. And we're seeing this across the country, even in areas that are getting drier overall. This is a beautiful graphic here from the National Climate Assessment, the last one. And it shows you the increase of those heaviest rain events across different regions of the country, even in the Southwest. Some areas are getting drier overall, but when they're getting that actual rainfall, it's coming down in bigger amounts. And that's important because it overwhelms a sewage system. It overwhelms the drains. The ground is so dry that it doesn't absorb anything. It floods the roads and it becomes a real problem. We have that information also down to these local levels. So this, I'm going to share some links at the end with you too, because I always love to give you the capacity to go explore this information and data on your own. And in our Climate Matters program, we pump out this kind of research every single week. So these are just a snapshot of 2 different cities here where we've had some rain events recently. St. Louis, higher rainfall intensity, the way we calculate 23% since 1970. Houston, 22%. We've seen visually what that's done in Houston several times over the past 15 years. Now, on the opposite side of the water cycle, right, where it's drying out, that's increasing the risk for fire weather days. Now, this doesn't mean that it necessarily leads to a fire, but the way that you look at a fire weather day is 3 things. It's the temperature, it's the amount of moisture in the air, and it's the wind. And for those fire weather days, there's a huge increase across the West. But you also see in parts of the East, we're seeing this increase. And I live in New Jersey, and many of you have seen visually, just over the past 2 years, some big fires that have broken out in New Jersey and have been an issue. But that's just the atmosphere. The vast majority of our heat is going into the oceans. When I first saw this, when I came over to Climate Central, and it was during an IPCC report, again, because of our great science and our great scientists who work globally with everyone else, this just blew my mind that over 90% of the extra heat that's getting trapped in our system is going into the oceans. And this is playing out in a whole host of ways. On the weather front, it is supercharging our tropical systems. So we're seeing more rapid intensification of the storms that form, and we're seeing those wind levels push to higher heights. It doesn't necessarily mean we will see more hurricanes, but when they form in this warmer water, they're getting more explosive. Also, when they do make landfall, they're coming with a higher storm surge because of sea level rise, which with warmer water forces those oceans to rise a little bit, and it melts more ice, which adds even more sea level rise. So the combination of the two leads to higher storm surge. And then also, we already covered this, heavier rainfall. So when these storms are making landfall, they're coming with more heavy rain. And this has been one of our biggest killers. We've seen this the past couple of years, that rainfall that is just so intense and goes so far inland now because there's so much more of it. Now, as far as sea level rise go, another thing, again, for you to explore, at Climate Central on our site, we have a really robust sea level program, and you can go in and look down to your street level and play around with different levels of water going forward for different years and different projections. And there's so many data sets of what's going to be under that water for you to really explore and learn more about this. We also are building out some additional visuals. And I'm telling you this because this is to help people understand what's happening. Because sometimes we just hear data or we just look at a number and it doesn't always process with our minds. So the visual side of things can really help people learn. And so we've been building out this flood vision. And what it does is it's mapping almost like the Google car that goes around, right? And it's getting this information of specific levels with LiDAR of our ground. And then we've been able to watch this, ready? Boom. When you look at future flooding, this is what's going to look like in certain areas. Again, now this is just one snapshot I'm showing you, but to build back to that sea level mapping I showed you, we're trying to build out this capacity so that you can really see what X number of feet is going to look like, 1, 2, 3 feet in your community, because it can help you make stronger decisions about where you live, where you buy houses, where you move. Here's another thing, and this is to build upon what Ben Santer had said. So first of all, I have to say this lineup tonight is spectacular. Really honored to be alongside it. And Ben Santer is the godfather of attribution science, and it has continued to evolve. So attribution science is now at a point where, as he said, we're getting into individual weather events or daily temperatures, and we can assess and quantify the role of climate change within that extreme event or that daily temperature. And so we've been working with World Weather Attribution on a whole host of different attribution research and science. And then Climate Central, we put this into what's called the Climate Shift Index. So again, you can go to this site, you can play around, and every single place, every day, you can look at the role of climate change within your daily temperature. And this is to offset some of the big extreme event reports, because we all understand, again, back in New Jersey, a 70-degree day in February isn't going to get a big attribution report, but you can go look and answer that question, is this normal? And this can tell you if it is or is not. And this was a snapshot from today. What we're seeing around the western part of the United States, Canada has been really lit up recently, and northern parts of Europe. We've also applied this to ocean temperatures, and I pulled this one specifically because for those who have been tracking in the Eastern Pacific, they've just named the first depression. And you see here on the little part near Mexico, down there in that orange red area, there is a climate change fingerprint on the water temperatures. So climate change is playing a role in developing that tropical depression. Here's how we applied that last year with Helene, and where we saw that absolute rapid intensification, the explosion of the storm, it moved over water. It was 300 to 500 times more likely because of climate change. So it wasn't normal. And just today, we put out our Climate Matters Hurricane Package. And within that, again, this is all stuff you can access on our website, and I'll have the link at the end. We are now putting all of this research into a tropical cyclone attribution tool. Now, I can't show you a picture because we don't have one right now. There are no Atlantic tropical cyclones. As soon as there is one with a name, it will, on our website, initiate a whole host of things that we've been building into this tool. So we do not wish to have a lot of storms, but I can't show you anything until there is one. But know that that technology is now out there. So why does this matter, right? That was a wide-ranging snapshot of the science and where we are and the value of the science to help us understand how things are changing. But this is why it matters. We are getting more lives and livelihoods being either taken or wiped out because of the increasing number of extremes. This data set in particular, the $1 billion disaster data set that the National Centers for Environmental Information ran going back to 1980, has stopped. It is not producing this data right now. This just shows you how many more we've gotten since 1980. And another way to look at this, the time in between these disasters. And think about this for people on the ground, that time to recover, for our systems, for FEMA, for the emergency managers, to help people. When something is wiped out at a level of $1 billion disaster, that is major. This used to happen on average every 80 days across the United States in 1980. It's down to less than 2 weeks. Our health is at huge risk with our changing climate. We have more mosquitoes. They're spreading farther poleward. So they're bringing new types of diseases to new areas that never had them before. With wildfires exploding more rapidly, not only is the air quality around those storms bad, but it travels. Look what happened in the Northeast just 2 years ago. The skies turned as dark as some of the wildfires out west. And it was so, for anyone in the Northeast, I mean, you could smell, it felt like there was a wildfire just down the street. It was so strong in that sense. So this is traveling. And again, we are a globe. People have already said this several times, but the weather does not stop at a boundary. It keeps going. We are also seeing longer and stronger allergy seasons. And you know what likes carbon dioxide? Poison ivy. It is exploding. When you add the extra heat, we're seeing more ground level ozone, which is harmful to breathing. And in the stagnant air masses, we're seeing that this air quality just continues to get worse. We just put out a report looking at heat risk days for maternal health when people are pregnant. And there is a climate change fingerprint on more premature deaths because of high heat around the globe. I pulled the US one, but we do have global data on this. And our kids are also at greater risk. We have a whole series looking at different aspects, but this was diving into eco-anxiety and how that's playing with our younger population, who is going to have to deal with this the most. Plus some of the things we care about most, our beverages, such as beer, coffee, wine are at risk with a warming climate. Go birds, eagles, football seasons, our sports are getting impacted by a changing climate. We're getting more power outages. It is costing more money with power demands. And climate change is sadly affecting almost everything in our lives: weather, food, water, health, economy, racial and social equity, infrastructure, buildings, roads, energy, transportation, coastal flooding, changing oceans. We're seeing shifting ecosystems and seasons, national security, migration and immigration. There is a climate change fingerprint on what we're seeing at our southern border. Tourism, sports, recreation, ways of life are all being affected by climate change. So the things that people care about in society have a climate connection. Sometimes they just don't know that. And so this sadly is making so many of these things worse. But I don't want to leave you with that, because there are things we can do. And there's a lot that we can do. I showed you our emissions. Those emissions need to come down to zero. These are some ways to do it. Weather isn't just part of the problem, it's also a solution. Wind and solar are rocking across the US. They are at risk right now with some things going on in DC, but wind and solar, I mean, this is weather. This is energy that you can't take away, that people can just gain and own, and it can be very individual and personal. And solar capacity has been exploding. Our biggest solar state, wind state is Texas, but also look at the solar in Texas. It's just been off the charts the past few years. We've also seen a lot of clean investment, especially with the IRA, and a lot of that's at risk right now. And then the bottom right here, what you're seeing is cleaner air directly because of a shift to electric vehicles. And for anyone who hasn't driven an electric vehicle, it is fun. It's a really fun thing to drive. So it's not a sacrifice to move to an electric vehicle. It actually processes energy more efficiently, and it goes pretty fast. Plus communication. And this is something, if there's anything you take from my session today, it's this. Everyone can start a climate conversation. The golden rule of communication is knowing your audience. So a quick snapshot to my dear friends, Tony Leiserowitz and his team at Yale, and also Ed Maybeck at George Mason University, have done this foundational science on people's views on climate change going back to 2008. They do this twice a year, and they've broken down public opinion across the United States into 6 different categories. You see alarmed and concerned, well over 50%. Dismissive, 11%. This is the group that has a really loud voice and is not going to change, but that chunk in the middle is open to listening about climate change. And on the left, they are very interested in driving forward climate action. So that's most of society and how that maps out, because people say, well, is it that way in my community? Well, I want to show you this. They've also downloaded and downscaled all of this data into the Yale Climate Opinion Maps. Google Yale Climate Opinion Maps. They have about 30 questions where it says select question across the top of different topics and questions related to climate change, concerns, interests, and processes forward with solutions. And you see 72% of the US thinks this is happening. And you see maybe 3 counties that are in the blue there. So to me, the biggest piece of misinformation when it comes to climate change isn't when people are challenging the facts, is that people think people don't care about it. And that is wrong. So everyone has the ability to have a conversation. And I want you to know that people actually want to hear about this. Look at this. I love this one that they did. % of adults who believe schools should teach about the causes, consequences, and solutions. What this screams is, I have questions. Something's happening and I have questions. And look at that, 75% of the US, and I don't know if I see any blue on there. But look at this. % of adults who discuss global warming at least occasionally. Every single one of us can have a climate conversation. People are interested. They have questions. And they don't think people want to talk about it because that bubble all the way that was on the right in that first slide there about public opinion has dominated the conversation. And it's just not grounded in facts. So there's another form of data and science for you all to see today. So here's how you can be a climate communicator. It's what we've learned in our program and at our organization. Know your audience. Topic, tone, timing. This is, for our program, we're not going to put out a winter report in July. Think about how to connect with people through knowing your audience, what their interests are. The second is meeting people where they are. We too often focus on what divides us, but there's so much more that unites us. And as there's already been references to, and I will put it out there too, Penn State football. I go to those games. Those people that sit with me do not necessarily think the same things I do about science. But guess what? That connects us. And we care about what happens at the game. So there are things that connect us and unite us. Personalize, localize. And all of you are joining and learning today, but not everyone has the same vocabulary when it comes to scientific topics. So simplify. And that's one of the beautiful things that meteorologists can do. They take a whole bunch of complex equations, and they break it down to rain or sun. Tell a story when and how you can. That's how we move people. That's how we open up minds. We take people on a journey. Don't be afraid. Don't overthink it. You have science and public opinion on your side. So I'm going to leave with a couple of quick slides here. This is our atmosphere. This is it. This is what gives us life on this earth. It's really tiny. And our future is our choice. Where we go from here and how much we curb our emissions really will determine life on this planet. So start your conversation today. If you need a reason to start it, June 21st is Show Your Stripes Day. For those who don't know Show Your Stripes, every line you see here is a global temperature. On the left, it's going back to the 1850s. On the right, that's today. There is a global activation day where it's really just to bring awareness to this so you can have a climate conversation in any way you want with your stripes on June 21st. I have 2 links there, showyourstripes.info. And also we're building out an interactive at Climate Central. If you come to our site, it'll have it. Or if you want to sign up to receive our regular Climate Matters, this is part of the package that we put out. It's really reporting resources, but there's a lot of benefit in there for everybody. And we put it out every single week. So if you go to this link and sign up, you will get this information too. So I just want to thank these organizers. I want to thank everyone. And I want to thank everyone who's tuning in on this, who does care about this. So thank you.
Thank you for the wonderful talk, Bernadette. That was really great, from start to finish, kind of telling us everything we need to know about climate change and how it connects to weather. I had a question about your these wonderful graphics and analytics that Climate Matters is making. So have these been taken up by the broadcast meteorology community? And how do you see broadcast meteorologists talking to the public about climate change? You know, when they're not really able to zoom out all the time and talk about statistics, they're talking about an individual weather event that week.
So yes, they have. And, you know, I didn't go into a huge detail there because I wanted to try and leave everyone with something. But for a little history on that, Climate Matters is an NSF funded project, not currently, but has been over the years, 3 different times. And initially it was with one meteorologist in Columbia, South Carolina, Jim Gandy. And what we were able to do is some testing pre and post, him bringing in timely climate information to his weathercasts in ways that mattered to his community in Columbia, South Carolina. And it showed that people were really interested when he made these connections in these scientific ways. So then our second one was to really scale this. And we are now working with nearly 1,000 TV meteorologists around the US. Plus we also do support a global community of TV weather presenters in some different ways. And yes, they are absolutely taking this up. There's some amazing, actually, they've amazed me even more than I could have imagined, because we're seeing them become climate reporters way beyond weather. The more they've gotten into the science and the data, we see them out doing stories with their community on why this matters. And then the third of those NSF grants allowed us to scale it more broadly for all of journalists. So we're working broadly with the journalism community, meteorologists and journalists, in what we call like a weekly package. It's a story package. So it has data analysis, often localized to 240 cities in the US. It has the latest science. It has methodology, so everyone can check it out. And then it has additional content to help tell the story. Plus we have experts, many are in your lineup during these 100 hours, who will volunteer to be interviewed on a topic. So we're always trying to connect with the community to help support the storytelling.
Great. We have some wonderful questions from the chat. So let me pull up one of those. Okay, so the Beast asks, is there an explanation as to why it snowed in January in New Orleans?
The Beast, I would say that's weather. We're still gonna get weather. It's just when you look at that weather over time and space. Now, the other thing that I didn't get into, and it's, again, we're with people who want to talk about science, so this is fun. It's an active area of science, is how our warming planet could be changing our jet stream. And there's some fascinating research with this right now. And some of the hypothesis behind it is, as we're warming our poles and our equator, picture a river. And when the river starts to slow down, it meanders more, right? And so when we're warming, that change in temperature isn't as great. And so everything's slowing down and sort of getting stuck in these patterns. So if you're in the big dip, the trough of the weather pattern and the jet stream, it's going to continue to really amplify on the cold side and the stormy side. Whereas when you're on one of the big ridges, it's going to lock you into a dry, hotter pattern. So we're seeing some of that, but it is a really fun area of research if you wanted to get more.
That's great answer. And I love the analogy of a river for the jet stream. I'll remember that. We have a question about communication, which was, I think, one of your last points. How do you bring up climate stuff with people who are less than open to the subject?
That is a great question. This is where knowing your audience is critical and connecting with people, right? So if you're presenting, that's different. It's you want to know who's the audience, how. But if it's a conversation somewhere in a more social setting, it's get to understand something that matters to them. It doesn't have to take a lot of time. It could be sports gear that they're wearing. It could be a place that you're traveling to. It could be whatever. And sadly, as we showed, climate change is affecting all of those things. So there's ways to start that conversation so you come to a shared space, right? And then you can bring in some of the science about, again, you have to do it depending on who your audience is, but you can do it in a what's at risk, what you've learned, something that's interesting, maybe giving them a nugget to explore a little deeper. I mean, this comes in a wide range of ways. And even, for example, traveling with work. If I'm sitting at an airport, restaurant or something, and people go, so, where are you going? What do you do? And you tell them, is that really real? The thing is, they wouldn't ask that if they didn't know. It may have come in a little gruff, may have not have been very inviting, but they wouldn't ask if they didn't want to know. So it gives you an opportunity to enter that conversation of, yeah, it is. And then you can start to build from there.
That's great. I like that. Do you have a good general way, Kayla asks, to explain when things go against the kind of expected global warming trend, like when there's a polar vortex event that brings a lot of cooling to the northern hemisphere?
Yes, Kayla, this is when I look at space and time. For example, when I showed that cold graphic, that was one that we put out with response to the polar vortex. One of the first ones when I started at Climate Central. We looked at the coldest cold temperature in each location going back to 1970. And you saw they're still cold, but slowly the cold is coming up. And again, it doesn't mean it's not cold, right? But also you can look at records. You can look at record highs to record lows. That's another way of doing this. I remember it was about 2 years ago, huge cold outbreak in Chicago, icing over, hit record lows actually, coverage all over the place. People are interviewing us. I forget the exact number of days later, but within like 3, 4, 5 days later, it hit a record high. No one was on the side of the lake talking about the record high that it hit. The reason it was big news is because it just doesn't get that cold anymore, quite to that level. And another way is attribution science. If you go to our climate shift index, that actually calculates the role of climate change within it. So there's a positive and a negative scale, because we at Climate Central really first and foremost honor the science. And you can look at, is it less likely or more likely? And sometimes with the polar vortex, we'll see less likely. But crazy enough, sometimes when people think it's super cold and we're not breaking a record low, and you look at that and it's not even showing up on the negative scale. It's just because we don't get that kind of cold the same way anymore.
Yeah, a lot of the people in the chat are talking about what they remember the climate used to be like earlier in their lives and what it is now. And I'm not that old, but having grown up in California, you feel that a sense that the climate here is getting drier and warmer. There's less snowpack in the mountains, and all of that points in the same direction. Climate change. Okay, I think maybe let's see some more questions here. Actually, I was hoping you could maybe elaborate a little bit more on this teaser about CSI tropical cyclones that you mentioned. It sounds like a really cool tool, in part because of who our next speaker is. So could you elaborate a little bit on that?
So yes, you get the pleasure of listening to Kerry next, who is a master at this stuff. And actually, he was someone we consulted when we were looking at the methodologies. And again, that's how science works, right? That's what's so fun, is people really are trying to keep advancing things. And what it is taking a paper that we had published last year, and Daniel Guilford, not me, Daniel Guilford, had published that paper, and it looked at wind speeds with tropical cyclones. Now, after he published that and had gone through a lot of reviews, he spent this past winter refining and bringing more atmospheric principles into his modeling. And so within that, we now have a tropical cyclone, CSI, that is going to be able to assess the role of climate change with wind speed on tropical cyclones. Again, I can't show you because we don't have one, which is a good thing, right? But when there is one, we're going to have all the information you need on our website.
That's just wonderful. Great. Well, thank you so much, Bernadette, for the wonderful talk and fielding questions.
Thank you. Thank you to everyone tuning in. Again, I can't thank you enough. And to these organizers, they are so amazing and they deserve so much praise for this. So thank you. And now you get Kerry, which is great.
Likewise for our speakers. Thanks again. Okay, so thanks everyone again for joining in. Hopefully you learned a lot like I did from Bernadette's talk. So if you are just tuning in now, or if you've been here for a while, I just want to take a moment to remind you why we're all here. We are almost at hour 7 of the 100-hour live stream, Weather and Climate Science live stream. And that means we have 93 hours to go. And I will be staying up late. Hopefully some of you will, and you will continue to watch these great talks and ask great questions and talk in the chat. We've already seen a lot of great talks. The next speaker is no exception. I've already teased at it a little bit, but I'll leave the full introduction for a moment because I want to talk a little bit more about why we're here. So we know that weather and climate forecasts are important, and they take a lot of work to produce and to maintain and to constantly improve. And US climate scientists and modelers and meteorologists have been at the forefront of this since the beginning of the discipline and continue to lead in this area. We've created the first weather forecasts. We then use those same tools to develop the first climate forecast to understand how carbon pollution changes the climate. We've developed an unparalleled network of observations to measure what's going on in the climate around the globe, in the atmosphere, in the ocean, on the ice sheets. And we have a constant fleet of robots now making those measurements. We have humans going out making measurements, throwing weather balloons up. And all of this is because of the support from you, the public, from the taxpayers, and from the federal government through federal grants for research, through government labs that it directly funds, and all kinds of infrastructure. But right now, funding cuts or projected cuts are threatening a lot of that weather and climate science. We already have short-staffed weather stations, shrinking and shuttering of climate labs that produce climate models. And we need your help to protect and save these forecasts. So we will drop a link to 5 calls in the chat through which you can contact your representatives and advocate for continued support from the federal government in climate science. And we really appreciate you taking the time listening to all the science we've been working on, and we're excited to share it with you as well. And with that, it is my honor to introduce our next speaker, Professor Kerry Emanuel. Professor Kerry Emanuel is Professor Emeritus of Atmospheric Science at MIT, where he did both his BS and PhD in meteorology. Kerry's research interests focus on tropical meteorology and climate, with a specialty in hurricane physics. He is perhaps most well known for his theory of hurricane intensity, which I personally like to think of as a theoretical speed limit for hurricanes, and Kerry can correct me if that's wrong. His work has also applied these concepts to complex yet critical questions such as do hurricanes get worse under climate change, or how do they change? And also, Kerry is a rare example of a theorist who successfully applies their theories towards practical solutions, such as building models that accurately estimate the hazards posed by storms. Kerry has also trained many graduate students in the field, including many other speakers in this event, and actually taught the first climate science class that I took in grad school. And I'm excited that you all get to learn from him as well. With that, I hand it over to you, Kerry.
Well, thank you, Henry, and it's a great pleasure and an honor to be with all of you tonight. What I'm going to do this evening is a little unusual, at least it's unusual for me, is I'm going to talk about the intersection between the science of weather extremes, which is very lively and I think making fairly rapid progress, the insurance industry. I think the connection between those two is pretty obvious. And I'm going to wrap that into a hypothesis, that's all it is, for why we haven't really gotten very far on climate action and how we might be able to correct that. So it's a hypothesis. You should take a shot at it, shoot it down if you can. But I just want to get people thinking in a little bit different dimension about this. Henry, I assume people can see my slides and hear my voice. Okay.
Yeah, it's all good. Thank you.
Much of the economic damage from climate change comes from extreme events, things like heat waves, wildfires, storms, floods, and so forth. And there's a reason for that that's kind of obvious, why it's dominated by extreme events. If we just think about it, societies, no matter where they are, how well they're developed, are pretty well adapted to frequent events. Just naturally, people adapt to them. It turns out frequent means about more than once in 100 years, empirically. And conversely, they're poorly adapted to rare events. Okay, no big surprise about that. And so if the climate changes faster than people can adapt, you get large cost increases when events that used to be less frequent than once in 100 years become more frequent than that. We can think of that in terms of a kind of cartoon graph, although the real graphs tend to look like this. This is just for almost any hazard. It could be an earthquake, by the way. It doesn't have to be a meteorological phenomenon. If you look at the percent of property destroyed in an incident, like an earthquake, not versus the magnitude of that, but versus the return period associated with that magnitude, generally speaking, the steepest slope is around 100 years. Why 100 years? Probably it's just a few human generations, let's say human cultural memory. So when you get events that were to the right of that vertical line and climate change shifts them to the left, or vice versa, I should say, then you get very large increases in damage. Tropical risk, cyclone risk clearly arises in the long term. If you look at accumulated damage over a long time, it's mostly coming from high intensity events. And this graph is meant to show you that. Now, I'm not telling you how this was created because that's a long story, but it's created from some physically based models of hurricane hazards run in many different places. This happens to be for the United States. And what it shows is the probability density of a storm causing a certain amount of damage, which you see on the bottom axis. And note that that damage is on a logarithmic scale. So the blue curve is for a recent climate. The red curve is for a projected climate at the end of the century under a pretty high emission scenario, just to get this illustrated, okay? So you see a shift of that probability toward more damage. There's no real surprise there. But the peak probability in recent decades has been for this particular, I should have said this is for a particular insurance company's portfolio. It's damage to that portfolio. The most likely event caught in that set in recent times is about $1 million, 10 to the $6. Remember that number. Now, we're going to graph exactly the same thing, except with a little bit different numbers. We're going to multiply the probability density by the damage itself to give you a risk probability, if you will. And the important thing to note about that is the total damage over a long period of time is proportional to the area under these curves. Now you can see that there's a near quadrupling of the actual long-term damage from that. But notice that where it's occurring in storms that cause about $100 million, 10 to the 8th thing. So if we go back to the previous slide, 10 to the 8th is in the tail of the probability distribution. And that's the point. It's the rare events that in the long run give you the most damage. And that's true for lots of phenomena. Okay, so what happens when there are trends and perils? Are there trends? Well, it's a little bit hard to see them in data so far, but as time goes on, they're becoming a little bit clearer. Henry, you mentioned potential intensity. It is, you quite correctly said, it's a speed limit for hurricanes, the wind speeds. And this is a map from ERA 5 reanalysis showing trends in that quantity, but only showing them where they're significant at the 5% level. And you can see in most of the tropical cyclone generating regions on the planet, like the Atlantic, Eastern and Western North Pacific and so forth, that they're pretty large trends. These are in meters per second per century. I hesitate to call them observed because it's a real analysis, but it's fairly close to, we hope, to what we would observe if you actually had observations of this. Notice also the Mediterranean going up very quickly. Okay. We predicted this trend way back in 1987. So just theoretically, it's actually happening. What is the consequence of that? Okay. Will actual intensities go up? Well, a fairly recent paper by Jim Cosson and his colleagues looking at very carefully processed satellite deductions of actual hurricane intensity around the world show that the proportion of storms that reach major hurricane status, category 3 through 5, has been going up in the last few decades, as we would expect, because the potential intensity is going up. So we're beginning to see a correspondence of theory and, by the way, models, which I haven't shown you, and observations. But it's not the only phenomena that we're worried about. Each year in the United States, there are about 1,200 tornadoes. They kill, on an average, 60 people and injure 1,500 and cause about $6 billion in damages. We don't hear about this often, but it's actually more damaging is hail. It causes more than twice the amount of damage to crops and property as tornadoes do. $15 billion, okay? And to put this in perspective, to touch at a point that Henry mentioned just before the talk, U.S. economic losses from severe convective storms average $35 billion. They've actually overtaken, on average, hurricanes, especially in the globe, but even in the United States, that's true. Severe convective storms are a big deal, and yet we have much less understanding of how climate influences them. To put that in perspective, the annual budget of the National Weather Service is $1.4 billion, about $4 per U.S. resident. Many of you looking at this presentation probably, if you're interested in weather, have apps on your phone that cost more than $4 or have subscriptions more than $4 per year, and yet all of them depend upon the National Weather Service. Economic teams have long ago, well, in the last 5 or 6 years, looked at the return on investment of the taxpayers' $1.4 billion. It's somewhere between a factor of 10 and 100, which means when you arbitrarily slash the NWS budget, you're costing the taxpayer between 10 and 100 times as much as it looks like you're saving. So the desiccation of the National Weather Service is not justified in economic terms. There is some evidence that there are trends in severe convective storms. This map doesn't show that. It does show trends in the kind of environmental factors that we know are conducive. So that's trends in a kind of a climate proxy of severe convective storms. The black contours show essentially the present distribution of those storms, and or the distribution some years ago, and the colors show the trends. So just about everywhere east of the Rockies, the trends are upward. Where they're stippled, they're statistically significant. This is work by Brian Tang and colleagues. But we really have to try to understand why we're seeing those trends. And that's a story for another day. It's actually a very interesting story. Okay, so the risks are increasing, but are those risks, the changing risks, being adequately communicated to people who need to know it? And that's what the rest of my talk is about. The answer is a resounding no. And let's talk about that because I think it's serious and it shows us why our work is so societally important at this point. So most current risk assessments that are used by insurance, by governments, by lots of people are based mostly, or actually I would say strictly, on historical statistics of the kind of risk you're talking about or kind of hazard you're talking about. And those records in the case of hurricanes, for example, you're lucky if you can say in the United States they go back 100 years. More like 120 years, but they get a little bit flaky as you go back. They're flawed, and you can show very easily mathematically that even if the climate were not changing, these even 100 years is way too short to get a good handle on the risk, okay? And the other problem is the last 50 to 150 years in which these statistics are based turns out in many cases, maybe most cases, to be a poor guide to the present. And that is the most important thing I'm going to say in this seminar, to the present. We're not even talking about the future. Their estimate of the current risk can be way off because of climate change that's already happened. And I can't stress enough what a fix that's put us into. Even if global warming were magically to stop, we would have this problem with us. And my view is that we scientists have to get involved in long-term risk assessments to pull it away from being based purely on historical statistics and base them on physics, on our understanding of the system and our ability to model it. We've really got to start doing that. And fortunately, the field is really beginning to rise to this challenge. There are a lot of climate and weather researchers getting involved in physical modeling of long-term weather risks. And government and reinsurance in this space have been, unfortunately, slow to embrace this approach because it's kind of baked into the way we do business. And this is a big problem. So I'm going to now show you 100-year peak winds from physics-based downscaling of 8 CMIP-6 climate models for 2 periods of time, 1984 to 2014. Well, I'm just going to show you that to begin with. And this involves about 50,000 simulated TCs. Now, what I'm not telling you, this is a choice I made, is how this was arrived at. It's a 20-year effort to produce a physics-based downscaling of GCMs. GCMs are much too coarse to resolve tropical cyclones, in spite of the fact there are a lot of papers that speak about model GCM TCs. They're really just not close to being there. So this is the 100-year wind at the centroid of each county in the United States based upon these 50,000 synthetic events. Again, there's lots and lots and lots of science behind this. If you're interested, write me, I can point you to it. And the color scale is at the right in the quaint unit of knots, and it doesn't surprise you. It's mostly coastal. South Florida is a big target, as is the Northern Gulf and so forth. Now we're going to look at the same map, but at the end of the century, and under this under CMIP-6 emissions trajectory associated with SSP 3.7.0. And the same color scale. So I'll go back and forth. You can see there's a big increase in the 100-year windstorm. And I've just got finished saying that the 100-year, in some senses, the most costly, or changes across 100 years are the most costly. And so if you were to translate that into economic damage, which we have tried to do, it's a pretty spectacular increase. Again, 8 CMIP-6 models were used to do this. Same thing. We're going back to the 20th century, well, to 1984 to 2014. But now I'm showing you the storm total rain associated with a 100-year rainstorm by county. And this was calculated literally at the centroid of the counties. Okay, and there it is. And now we go to the future. And that's an even more spectacular increase. You know, we go from 600 millimeters, say, in South Florida up to 1,400 or so. It's really big because you have two things going on. The storms are getting more intense, and there's a lot more water vapor in the air. So we're trying to take what we know and can codify about physics and use this to make real quantitative estimates of risk, including the large uncertainties, which I haven't shown you here. I'm just showing you the mean, okay? But it is absolutely imperative to quantify the uncertainties to the extent you can. Well, as I think most of you know, damages from natural disasters are increasing. These are United States billion-dollar disaster events, CPI adjusted, going back to 1980. This chart gets bandied about a lot. This is something I did myself for the whole world. This is global damage from storms, droughts, floods, and wildfires, basically meteorologically modulated events or events themselves, divided by the world domestic product of each year. So it's normalized for inflation. And again, you see a big upward trend in that. A lot of this is flooding. Flooding is really the worst globally in this terms of the amount of damage it costs. Some of these floods are from severe convective storms, by the way. But as many people have been at pains to point out, these big upward trends are not climate change. There might be climate change in there. It's mostly demographic. It's because people all over the world are moving from less risky to more risky places. And that, again, is a well-documented trend. And the collision between that trend and climate change trends is really very worrying and has so far been very destructive. So in the United States, this is a map published not long ago in the New York Times. It shows where people are migrating to in the period 2000 to 2023. So the high risk counties, this is all kinds of different risks, wildfire, storms, etc., are in red, and the places with large population booms are in blue, okay? Pretty good correspondence, not perfect, but people are moving to dangerous places. This is a map showing the number of climate hazards per county. This is all the hazards, not just storms, flood, fire, heat, drought, okay? They're all in places where the population is going up. Not all, but mostly. So why? Why are we moving to more dangerous places? You know, the demographic literature just says this is happening. It doesn't really go into why it's happening. But I'm going to make my most radical argument of the evening by saying that we're paying people to do that, okay? We're paying people to do that. Why? Well, first of all, most of the damage is from water. Even in hurricanes, that's true. In severe convective storms, a lot of it's water or hail. It's insured by the federal government through the National Flood Insurance Program. That's been true since 1968. Over the years, over the decades, political pressure from mostly coastal residents has exercised itself on the rates that are being charged in their areas, making them artificially low. And this, again, is well documented. And I'll show you the documentation of that. And then, of course, to keep the system afloat, they're too high in safe places. Private insurance, which insures things like wind damage, is in most states regulated, especially coastal states, regulated. The pricing is regulated through insurance commissioners. Most states have insurance commissioners who regulate prices. There are very, very few industries in the United States whose pricing is regulated by the government. Utilities, but utility is a government-operated monopoly. It's a little bit different. The irony is that these regulations were originally put in place to ensure solvency. You don't want your insurance company to go belly up just when you need them. But it became captive to special interests, and the regulation's actually doing the opposite now. It's making insurance companies non-solvent. So state insurance commissioners routinely regulate premiums in risky areas such as coastal regions. Now, this is a really, really startling map that comes from the First Street Foundation. It shows the ratio of federal flood insurance payouts to the premiums they get from each county in the United States. Where it's red they're getting much more from the government than they're putting in. And look at the numbers on that color scale, thousands of percent. And most of these red areas are coastal. Florida stands out. All the coastal places are getting. Palm Beach County is deep red. It's not exactly a poor county. It's getting tons of money from the federal government and not paying back much in premium. The premiums just don't reflect the risk. And that's the heart of the problem. And people who study this have known this for decades. This is not a recent phenomenon. This has been going on for a long time. All right, so this is just a chart, a time series from 1980 to 2017, showing federal flood insurance premiums in blue versus payouts. And you can see that up until Katrina or so, there was kind of a balance. And then it really went into big debt, okay? Those orange bars are much longer on average since 2005 than the premiums. So under political pressure, state insurance commissioners are regulating premiums, forcing them to lose money. So it's not just federal government, it's private insurance. This map shows from 2010 to 2023, a couple of curves, the cost of reinsurance, okay? The premiums people actually would pay if they were actuarially sound. That is, if we had a free market and insurance prices weren't regulated, they would follow that blue curve. But with the regulation, okay, we're down in the yellow and red territory. So there's this $3,000 per average property premium suppression. All right, this is what the government is doing to make sure that people don't pay for their risk. And the result is a massive exodus of insurance companies from the states that do this the most, like California, which has lost some of the biggest insurers in the company, State Farm, Allstate, Farmers, and the list goes on and on. Okay, insurance companies are getting out. Why? Because the business isn't profitable. This is just the index of a loss index, if you will. The break even is in the center. This goes from 2014 to more or less the present. Insurance companies are losing their shirts because the government is forcing them to. Now, nobody likes insurance companies, and maybe you're happy about this, but this is causing a really, really big problem because those losses in the end are being paid by taxpayers and ratepayers in less dangerous places. So we've got a big problem here. National flood insurance, again, this is not recent, has been captured by special interests in risky places holding down premiums there, with premiums too high in less risky areas. State regulation of private insurance has artificially reduced these premiums, causing insolvency in direct contradiction to the mandate, which was to ensure solvency. So this is kind of silly. We're paying people to move to and develop risk-prone regions. In places like the Carolinas and Florida, you would not be able to live there if you had to pay an insurance bill that actually reflected the risk, okay? And that's not even accounting for the thing I talked about in the beginning, which is the difference between the risk today and the risk 50 years ago. A lot of these people are getting bad information about risk. So this is driving up the damages. You remember those graphs I showed you. It's spectacular, all right? And that's the big thing driving up the damages. Climate change is what the DoD would call a large threat multiplier, and that's important. What are the consequences? Well, we've encouraged this massive migration from safer to risky places by preventing insurance from communicating risk. Relatively poor people living in inland areas that are relatively safe are paying the insurance bills of relatively wealthy people, so that's not really just, but that isn't even the worst problem there. Damages are soaring, amplified, I would argue, by climate change. And we're insulating wealthier and more politically influential people who live in these risky places from climate change. And I think that's reducing their incentive to do something about it. Okay. I do have at least some anecdotal evidence that this is going on. So despite wide publicity of climate risk and large subsidies for renewables, climate emissions just keep going up. Okay, there it is, annual carbon dioxide emissions you've seen this chart. It may have been leveling off a little bit since 2010 or so, but it's still going up. With all the discussion that we've had and all of the damages that we have seen, hasn't made a big difference in this, which is pretty depressing. And I would argue that it's because, partially at least, because we're insulating too many people from the risks. We're not paying for these risks. We're distributing it to taxpayers who really aren't in risky places. So what are the options? You could just say, well, you could do is stop subsidizing risk. So state regulators should stop regulating rates. And in 1968, when they created federal flood insurance, private companies wouldn't go near it because they didn't have actuarial data. Now they do, and maybe it's time to do that. But if you were to do this instantaneously, and I hesitate to even put it up there because someone might get the idea to do just that, doing it instantaneously would cause terrible suffering. In some places, premiums would rise more than a factor of 10. Now, you might think with people in Palm Beach County can deal with that, but not everybody, even in Palm Beach County, is wealthy. There are a lot of pretty poor people there, and their premiums would go up too, and it would be terrible. So what do we do about that? Government can ease the pain of transition through buyback programs and by temporarily subsidizing premiums for the less well-off. That's been talked about. And the most dangerous places could undertake what's called managed retreat. That is, we're literally going to move whole communities to safer places. This has happened in various parts of the world in the worst cases. But the main message I want to tell to this audience is this is a problem. It's a big problem that I think society needs to tackle. And I think it's responsible to some degree by insulating people from risk, distributing it too broadly. We're reducing incentives to try to do something about climate change. And we who work on modeling of natural hazards like wildfires, storms, and so forth are in a really good and necessary position to revolutionize the field of risk assessment, weather risk assessment. It cannot be, it's too important to leave to the statisticians, and I have nothing against statisticians, but we have got to get away from strictly historically based risk assessments because the climate's changing fast enough that it's made most of them irrelevant to today. And I'll leave you with those uplifting thoughts and happy to ask questions or answer questions. Thank you.
Excellent. Thank you for the wonderful talk, Kerry. It was a really nice tour of some of the relevant science and then some of the problems that these issues leave us with. I wanted to start, because you started your talk with the science, to ask you about some hurricane science. So one of the things that you mentioned was the warming in the Mediterranean. And you said, I think that you might come back to that, and I'm not sure if you did. So I thought maybe you were going to mention medicanes.
Yes.
Could you talk about that?
Well, it's a very interesting subject, and a big group of us are just about to publish a paper on that subject, actually. So medicanes are in their maturity tropical cyclones, except they're not in the tropics, as formally defined. And they occur when, in places where the potential intensity is climatologically insufficient, but it's temporarily increased by synoptic weather patterns. I can go into some more detail about that. So you locally in space and time create the correct thermodynamic conditions, and if everything else is right, you get what amounts to a hurricane. However, in recent years, for the first time, we have seen actual tropical cyclones in the Mediterranean. These are warm season events. Hurricane Danielle a few years ago, I think it was 2023, which went into Libya, remains the most devastating storm ever to hit the African continent in historical records. And that was a real hurricane. It was not just a medicane. So, and these phenomena, whether they're real hurricanes in the Mediterranean or actual metacanes, are affected by climate change. Although it's a complex picture. In some places the risk increases, in other places it goes down.
Great, thanks for explaining that. I also wanted to ask about hypercanes, which is a concept that I think you warned about in the past. Could you define what they are and then update us on what the risks of those are?
Well, the risk is zero and will remain zero. That's the good news, because we're very, very far from the kind of climate that could conduce to them, if in fact any climate could. So what happens in a hypercane is there are a bunch of positive feedbacks in the whole hurricane Carnot cycle. One of them is just isobaric expansion. It's heating by isobaric expansion. As air spirals into the low pressure at the center of the storm, it would like to expand adiabatically and cool, but contact with the ocean surface prevents it from cooling, and that's a heat source. It's a positive feedback because the stronger the storm, the more the isobaric heating. And the more the isobaric heating, the stronger the storm, but it's held in check by other negative feedbacks. However, if you make the ocean too warm, that feedback runs away and you can no longer balance the energy generation in the Carnot cycle strictly with surface friction. You have to start to have a lot of internal friction. And the whole storm transforms into something that's much narrower and goes all the way up into the middle stratosphere. It's fascinating, but you need about 50 degrees centigrade water for it. So no risk there for the foreseeable future.
That's good news, but theoretically fascinating anyways.
Yeah.
Okay, so I wanted to also follow up on, you mentioned very briefly that we can't directly simulate hurricanes in global climate models, like the CMIP6 models that you mentioned. And so you developed over decades these methods to downscale. So you take information from the climate models and then simulate kind of separately embedded tropical cyclones within them. So could you talk a little bit about that? And then also, what do you see as the future? Are we on the edge of being able to simulate hurricanes and tropical cyclones in global climate models? People have been making a push for these kilometer scale cloud resolving models, for example.
Well, I think we already have kilometer scale cloud resolving models that are global, but not that we can run for 100 years. And it may be a while. I mean, who knows what breakthroughs may make that possible, but on the current trend, it's going to be a long time before we're there. We know from running axisymmetric models at various different resolutions that your grid spacing has to be down in the 1 to 2 kilometer range to be even close to being numerically converged on an idealized tropical cyclone. And we're very far. I mean, when we talk about high res MIP, we're talking about 25 kilometers. So at least an order of magnitude away in grid spacing. And that's a problem. The downscaling is a way to, at least until we have these models you can run for 100 years. It's a way around that. And very, very briefly, there's sort of 4 steps. There's the genesis step, and that's accomplished in our model by literally randomly seeding the time evolving global climate state from a model or reanalysis, and randomly in space and time. And then the next step is, where are these seeds going to travel to? That's kind of the easiest one. To a good approximation, hurricanes move with the large scale flow in which they're embedded, and a little correction for something called beta drift. But the key step is to run an actual coupled ocean atmosphere model, a very fine resolution model that does the intensity of the tropical cyclone along each of these tracks. And in practice, it predicts that about 95% of them will immediately die, and those are just thrown away. So it's kind of a natural selection process. And the remainder are considered to be the survivors. And yeah, there are a lot of steps there. And the only way that we have any faith in is that it really does quite a nice job when you apply it to global reanalyses and try to reproduce those robustly measured aspects of tropical cyclones around the world. So that's how we do it, and it's easy to generate 100,000 synthetic tropical cyclones that way.
Great. Thanks for answering some of those curiosities about hurricane science. So now we'll transition more into the risk of them. So we have some great questions from the chat. So Eli Rabbit asks, at what point does it become impossible to insure against climate risk because the frequency of destruction becomes too high? At what point do extreme damage areas have to be abandoned completely?
I think the maybe flippant answer, but it's not supposed to be flippant, is that when it gets too expensive for people. I once took a little tour along the eastern coast of the Philippines, where there's not much regulation of insurance, and there is what I thought was a very well adapted coastline. Now they get hit by Cat 5s almost every year there, or very frequently anyway. And what you see is a lot of shanties. They're sort of, plywood things that are thrown up. They have very little value, and every few years they get blown away and then come back and rebuild them. That's pretty intelligent. And then there are a few real fortresses built by very wealthy people that are up on big steel pilings, and they can and do take Cat 5s. But it's actually quite nice and democratic. Everybody has a little hut on the beach, even if you don't have a lot of wealth, and it's a throwaway in a way, and it's wood, so it's not very damaging to the environment. So that's a well-adapted coastline. It's kind of ironic that the better adapted coastlines in a very poor country and the worst adapted coastlines are in the wealthiest countries. I guess that's a bit ironic.
I guess the flip side of that question is this other question, which is, to what extent should we build protections for coastal areas, so hurricane-resistant infrastructure, or is that, you think, the wrong approach?
I think the answer to that question depends very much on exactly where you're talking about. What's a right solution for New York City might be a terrible solution for Miami, and vice versa. So the answer in some places might be that it's just not worth it. It's going to cost too much to do it. In other cases, it might be very much worthwhile to build coastal defenses. So I think the more important aspect of that is the framework in which you make that decision. That is, how do you estimate how that risk will actually change? And that's where we scientists, I think, have the greatest potential to help society, is with that. Estimating sea level rise, there are lots of that's already been done, but how are these storms going to change, and wildfires in other places and so forth. And then, for engineers and economists to figure out what you might do, given the estimates of the changes in these hazards and how much it will cost. And then it should be a democratic decision whether you think it's worth it or not. And that will vary from place to place.
Yeah, so to the point of trying to create better estimates of these costs, Kerry, presumably a different Kerry, asked the question, do insurance companies employ their own climate scientists, or do they rely on work done by scientists working for the federal government? Or no scientists, I guess.
So insurance companies and many other interests rely on something called catastrophe models. And at the moment, there are only 2 or 3 firms all around the world that make these models. And the models are almost entirely statistical models. They're based on history. The meteorology that these cat modelers do, at least the ones I'm familiar with, is sort of at the level of the detail of, hurricane wind fields, how wind blows around topography and buildings, and they don't get into water. Someday they will. It's the same kind of problem. But the actual tracks of hurricanes, for example, are stochastically generated from historical storm statistics. And it's kind of locked in, and this is not because of any malicious conspiracy, but so many people use them, including the rating agencies, which rate the insurance companies. And if you don't get a good rating, you're not in business. So it's kind of, this system has become baked in, if you will. And again, no conspiracy, it's just the way it is. How we dislodge that, that's an interesting question.
Yeah. So I wanted to come back to, you mentioned at some point you showed a plot of the increase in costs due to hurricanes in the US or something. And it was, you argued that it was mostly due to development along the coasts and GDP growth, and not actually to, or not necessarily to climate change. But you also said that maybe climate change is in there as a signal. So could you update us on the state of the art of, is climate change affecting hurricanes?
Yeah, sure. One just small technical correction. That both graphs that I showed, there were two actually, they basically told the same story, were for all weather hazards, not just hurricanes. The hurricanes a big contribution to that, but there were winter storms, there were thunderstorms, tornadoes, and lots of different hazards in there. We can use these synthetic tracks, and we do all the time because we can produce so many of them, to answer the question, is the increase in damage from, say, hurricanes in the United States detectable? That is the signal that you would predict rise above the noise? And the answer is resounding no, it doesn't, because of the volatility of damage. Remember, I said the damage is not coming from all the little hurricanes. It's coming mostly from the rare big ones, all right? And there's so much statistical volatility in that, just random volatility, that it totally wipes out a signal. That is not to say that there isn't climate change or it isn't affecting damage. It is to say that that is not a good way to detect a climate signal. You really can't do it, even if you just confine yourself to hurricanes, you really can't do it in damage because of the highly weighted influence of the very rare events whose statistics are flaky on a 100-year time period.
Right. So we just had Dr. Ben Santer give a talk 2 talks ago. And so to put it in his language, I guess tropical cyclones would be a really bad fingerprint of human-caused climate change.
Absolutely, at least in terms of the damage they do. If you look at open ocean statistics like those that I showed from Jim Cosson, there you have a shot at it.
Yeah, makes sense. Okay, I think we have a time for a couple of more questions. Okay, so Kerry, I want to give you the chance, because you mentioned a few times that there was one thing you wanted people to take away. So we'll put up the question. What is the #1 takeaway you'd like people to understand? And then also, what is the one action item?
Well, the thing that I want people to understand is that our current practical estimates of weather risks all around the world are based on statistics that are A, insufficient, that is, we don't have a long enough record, and B, have been made obsolete by climate change. That's really the most important thing, okay? That we're acting on bad information, not disinformation in this case, just bad, insufficient data, if you will, and the underlying statistics have shifted. The action item would address that problem by saying we've got to get away from purely relying on historical statistics of extreme events and begin to rely on modeling them with physically based models in contrast to statistical models. We've just got to do that if we want to get a good handle on the current risk. And we can also talk about future risk, but at least we ought to do the current risk correctly.
Great, makes sense. And action item, if your action item is just to call representatives to support climate and weather science, that's fine too.
Yep, absolutely.
Great. Okay, well, for the closing question, I wanted to follow up on a little cliffhanger you left, which is that you said you maybe had some evidence in support of your theory that basically we're insulating some people who are more influential in determining the outcomes of climate from the risks of climate, and that might be an important feedback preventing more climate action. So could you talk more about that?
Yeah, my evidence is anecdotal and would never stand up in a court of law, but I'll tell you about it anyway. I mean, I'd love to see social scientists actually try to do this right, but I went through a period where I told myself I'd stop preaching to the converted and I would go and talk to very conservative groups or climate people who are very skeptical about climate. And I was invited by, remember the Tea Party? the Tea Party of Miami Beach invited me to go talk to them. And I thought, well, I have to spend a lot of time trying to convince them this is real. I didn't have to spend any time at all because they were seeing their insurance premiums go up quickly and were upset about that. And they were seeing their houses flooded quite frequently on top of that. So they were all over the climate change problem. They didn't have to be persuaded. They just wanted to know, well, how do we deal with this? What do we do about it? And I came away with an important lesson that when you are starting to be affected personally, when you feel the risk, ideology takes a backseat.
Yeah, that sounds like a insightful lesson. Great. Well, thank you so much, Dr. Kerry Emanuel, for this wonderful talk and Q&A with questions from the chat. And thanks again to everyone for listening to this wonderful presentation. Yeah, so let's all give Kerry a round of applause in the chat. And with that, we'll move on to the next segment. How's he gonna Kerry? Okay. So we are now, I don't even know what hour we're in. I'm seeing that we're almost into the 8th hour of the live stream. So thanks everyone for sticking with us. Let's take a moment to remember why we're all here. We're here to learn about science and celebrate the amazing things that weather and climate science has brought us in the US. We now rely on weather forecasts all the time. We have them on our phones. We kind of take it for granted. But maybe we shouldn't, because it takes a lot of work to improve and maintain these resources. And the US has always been a leader in this space. We invented the first weather forecasts here. We invented the first climate forecasts. We continue to lead this area and develop some of the best models and do the best science with those models. And we also make some of the most important observations of the climate, and we need those to trust our forecast, to verify them, and to learn about what's to come. And this doesn't come for free. It requires a lot of investment from you, the taxpayers, and the federal government, through grants to funding, through support for government research labs. And right now, the rug is potentially going to get pulled out from under all of that. So there are large budget cuts that are projected or proposed for weather and climate science. There are already weather stations that are short-staffed. There are observations that are not being made that should be. There are climate labs that are at risk of getting completely shut down. This morning, we were live at the NASA GISS labs last day because their lease has expired and now they have no physical space. And so we need your help to advocate for this community and for the value we bring to society. You saw the numbers in Kerry's talk. A lot of this science has a very large return on investment for society. So we'll drop a link to where you can follow to make an action. So you can call your representatives and advocate for weather and climate science, wclivestream.com/act. And we really appreciate you joining us for the live stream. We have 1,800 people almost into hour 8. And let's keep the energy going. So with that, I'd like to bring in our next speaker, Professor Andrew Dessler. Professor Andrew Dessler is a atmospheric scientist at Texas A&M University. Andrew earned his PhD. Oops, I forgot my notes. Can you fill in the gap?
Yes, I do remember I got a PhD. So I have a PhD in chemistry from Harvard. I grew up in Texas. I work at Texas A&M now.
Great. I've got the rest of your notes. Thanks.
That's for sure. I'm in the atmospheric sciences department here.
Yeah, great.
And I've played Fortnite with Henri.
Yes, we are both passionate about climate science outreach. And one way that we did that was streaming Fortnite live. So we both have some experience on live streams.
That's right.
And Andrew is also a communicator in many other ways. He wrote a textbook, Introduction to Modern Climate Change, that many people use. And just a great speaker about climate science. Has covered an impressive variety of topics in his career. So I won't be able to cover all of them, but yeah, everything from climate physics to atmospheric chemistry, climate change, and even policy. And with that, I'll leave it to you, Andrew.
Great. Well, I really appreciate the invitation to talk to everybody. And I just really want to thank the organizers for doing this. I know how much work this is. So thank you very much for standing up for science. So I'm going to talk about the history of climate science, because I think there's a lot of really important lessons that we can get from this. And to sort of inform the present situation. And so any discussion of history really has to start in the 1820s with Joseph Fourier. So anybody that's done any math has probably seen the name Fourier. You love his series and his transform, but he actually did really good climate science. And he really was one of the first people to ask the question, why is the Earth the temperature it is? It's a really fundamental, great question. And what he concluded was that the atmosphere was warming the climate. In other words, he's really the one who talked about the greenhouse effect. And at the same time that he was sort of understanding what the temperature was, there were other people like Louis Agassiz and others in Europe were walking around and they saw things like this. So this is on the banks of the Elbe in Hamburg. That's the Old Swede, is what they call that giant boulder. And if you ask the question, where the hell did that come from? You can kind of do some analysis. You find it came away from a couple 100 kilometers away, and you think, how did this get here? And one of the obvious answers is ice. It takes, ice can move rocks a long way. And if you look around Northern Europe, you see a lot of places where it looks like ice was here. And so this was really when these people understood there was a period of time when Northern Europe was covered with ice, hence the term Ice Age. And this really was revolutionary in the sense that, up to that point, nobody really thought about climate change. I mean, why would you? The climate is kind of the climate you have is the climate that your father has, the climate your grandfather has, etc. And people suddenly understood climate can change. 1856, Eunice Foote is, as far as we can tell, the first person to say carbon dioxide is warming the planet. A few years later, John Tyndall did really comprehensive experiments. He identified water vapor and carbon dioxide. So he was really the one who did the very detailed lab measurements. And then to sort of tie a bow around it, 1896, Svante Arrhenius, a Nobel Prize winning physical chemist, he really did the first calculation of global warming caused by carbon dioxide. And he said, humans are burning coal. This is going to warm the climate. Of course, he thought it would take thousands of years. He didn't understand exponential growth of the voracious appetite we had for energy. And the other thing about it is, he lived in Northern Europe, and he thought a little climate change would be good for him. So, people weren't terribly worried about climate change at that time. And then for about the first half of the 20th century, Ray Pierre Humbert calls this the Dark Ages. He gave a really good talk at the 2012 AGU meeting. I was there. It's a video on YouTube if you want to watch his Tyndall lecture, where he talks also a lot about the history of climate change. There was a couple things that did happen. Astrophysicists worked out what we call radiative convective heat transport in atmospheres and energy balance, because they were trying to think about how stars worked. And so they worked out some of the stuff that we later would use in understanding the Earth. And there were other debates. For example, people didn't know where the carbon dioxide humans emitted would go. Some people said it's all going to be absorbed by the ocean. Other people were arguing about the spectral overlap of the gases. If you know any spectroscopy, if you've taken chemistry, you might know that molecules absorb at discrete frequencies. Water vapor and carbon dioxide have a lot of overlap. And so you might think, well, they overlap so much, adding more carbon dioxide won't have an effect. So these are debates that were going on at the time. Other things that did happen that were interesting is by the 1930s, people were talking about global warming. And in 1938, a guy named Guy Callender, that was a nerd joke. Guy Callender argued that carbon dioxide induced warming was underway, because he took the work that Arrhenius had done, and he understood that we were dumping carbon dioxide in the atmosphere. And he understood the Earth was warming. He said, it's happening. Was he right? Maybe. It's hard to attribute the warming in the early 20th century. People kind of argue about that. But, you know, it was not, it was a bold prediction. 1948, Al Gore was born. I always like to put this out because, you know, people talk about climate change being this political stalking horse. And I like to say this predates any kind of political debate you'd care about. I mean, people were arguing about climate and working on climate in the 19th century before communism existed. Al Gore was born. It was, we had basically figured Arrhenius figured a lot of things out. And that was 50 years before Gore was born. So this is not a recent thing. All right, now let me take a step back because I want people to understand how science in the US works, because that's the whole point of this live stream. I want people to really think about how it works. So when World War II ended, everybody understood that technological and scientific superiority helped the US and the West win the war. Okay, the most obvious example is the atomic bomb. But other examples, radar, cryptography, napalm was invented by some Harvard chemists in 1942. Technology makes you more secure. And so based on that, in 1950, the National Science Foundation was formed. And the whole idea was this powerful innovation engine. It created the world's most powerful innovation engine through a partnership between the federal government and our universities. Let me explain how it works, because you have to understand this to understand why what's going on now is going to be so bad for US science. University researchers get money from the government, and then they use that money to do two things. They hire graduate students who do most of the work, and these graduate students who do the work, they develop breakthrough technologies. And not only that, you educate the graduate students. When the graduate students come out of grad school, they're scientists. They're the next generation. So, but when the government gives universities money, they are buying the future. They're buying the economic breakthroughs. They're the technical breakthroughs that deliver economic benefit. And they're generating the next generation of scientists. So it's a self-perpetuating system that more than pays for itself. I mean, the payoff, people have done lots of research on the economic benefits of research. And what you see is that you spend a few dollars, you get more dollars back from economic benefits. So this is an incredibly valuable thing that we do. And so when you look, so this is I pulled this paragraph out of an article that came out today, and to show you how people misunderstand this. So Harvard University's lawsuit to stop the Trump administration encapsulates a tendency among those who receive grants and other taxpayers' largesse to treat these as privileges or as entitlements, but it's a privilege. And I mean, that's the wrong way to think about it. When the government gives a university money, they're buying, it's a transaction, they're buying the future. And if the government says they don't want to pay for research, then they were saying they don't want to buy the future, because the future, the future is what research universities develop. Now, the other thing that's very important is a key component of this is our visa system. We bring in students from around the world. We are able to bring in the smartest people in the world to come to the US to do our research. And the smartest of those people we keep. And so this is this enormous benefit. If you look around the US, immigrants found enormous numbers of successful companies. A lot of them started in university labs. And this is an enormous component of our success. Look at the CEOs of NVIDIA, of Google, of Microsoft. You'll see all people who started as students here. Our research system is the envy of the world. And if we cut research funding, this system is going to shut down. I mean, nobody competent would ever say we have too many scientists. Yet that's exactly what the policies being implemented are going to do. Okay, they are going to crank down on the scientist pipeline, and we're going to have a lot fewer scientists coming out. Okay, back to climate science. So 1955, Dr. Seuss detects fossil fuel CO2 in the atmosphere. Now, I was confused for a long time because I thought Dr. Seuss was this guy, but it turns out that Dr. Seuss is this guy, Hans Seuss, who is an isotope geochemist at Scripps, and he actually detected that he was able to measure that fossil fuel CO2 from fossil fuels was entering the atmosphere. Now, just as an aside, the actual Dr. Seuss, Theodore Geisel, also lived in La Jolla, and I've heard anecdotally that they used to get each other's mail, which I think is just hilarious. So if anyone knows if that's true or not, put it in the chat, because I'd love to see Hans Seuss opening a letter and going, cat, hat, what is this? All right, so 1956, Gil Plas really solves the problem about CO2 and water vapor overlap. He does the radiative calculations and shows that adding carbon dioxide is going to have a significant effect on the radiation balance. All right, so by the end of the 1950s, we had solved a lot of these problems. We understood a lot of stuff was going on, but something else was going on. This idea, suddenly people started caring more about the environment. Several things happened. Atomic bomb arsenals grew. We suddenly realized we could kill each other. Killer smog of London. There was a great Netflix, The Crown episode about the killer smog event. 1952, lots of people died. Around the world, air pollution. People were beginning to understand that air pollution is a big problem. And again, this is humans affecting the environment. My father was an undergrad at Caltech, and when he said it was weeks before he realized there were mountains right next to the university because the air quality was so bad. 1957, International Geophysical Year started. This was a year of cooperation where all the countries of the world got together and they all started making measurements. So you'll see a lot of data sets start in 1957. And it really was sort of this peak of cooperation, scientific cooperation among the countries of the world to better understand the human influence on the system. And let me just point out the most iconic time series, the Keeling curve, started 1958. I know Ralph Keeling is talking, so I'm not going to say anything more than that. But I will say that the Keeling curve within just a few years showed that humans really were adding carbon dioxide to the atmosphere. The atmosphere was, we were affecting the radiative balance of the planet. So at the end of the decade, there's a great quote from Roger Revelle and Hans Seuss, and I like to read it because I think it's so powerful. Greenhouse effect warming may become significant during future decades if industrial fuel combustion continues to rise exponentially. Human beings are now carrying out a large-scale geophysical experiment of a kind that could not have happened in the past nor be reproduced in the future. I mean, we are running an experiment and we are in the beaker. That sounds like the definition of a bad idea. All right, let me just go quickly through a few other climate science things. 1960s, the science was advancing rapidly. Again, we had built this innovation engine between the government and U.S. universities. It was working well. 1964, a scientific report on weather modification where they were considering carbon dioxide emissions to be weather modification. They said, yes, you can modify the weather by adding carbon dioxide. 1965, the first report to a president. So this is 60 years ago. 60 years ago, the president got a report saying there was a sound basis for linking human activities to increasing carbon dioxide. And so this is not new stuff. 1967, I would like to point this out. There's a very famous Minabe and Weatherald paper in Journal of Atmospheric Sciences that really saw that in many respects, it solved the problem. I don't think we've learned anything in the 60 years past that contradicts anything in the paper. Now we're a lot more confident about it. We understand it much better. We have a lot more data. We can refine things, but it was this brilliant synthesis of information in that paper that really put everything together for the first time. All right, 1975, the birth of the term global warming. This is a paper in Science by Wally Broker, and don't read the abstract, but I do want to show you a plot. Now, this is a plot that I made. It was in an op-ed that Dan Cohan and I wrote in the Houston Chronicle probably about 6 or 7 years ago. I should update it, but I haven't gotten around to it. So the x-axis is year, and the y-axis is temperature, and the gray line is the NASA GISS temperature record. So that's the observed temperature. Now the dotted line is 1975. You'll see that the vertical dotted line. It's 1975. That's when Broca wrote his paper, and he made the red dot. The red dots are his predictions, and I want you to think about how impressive that is. So let me just cover up that part and ask, if you were going to make a prediction of the next 50 years, what would it look like? And the answer is it wouldn't look like what Broca predicted. And the fact that what he predicted was so non-obvious is proof that he understood something fundamental about the way the atmosphere works. He had a very simple model. It was what we call an energy balance model. But nonetheless, he got it spot on. And I think this really gives us some confidence that we understand what's going on, because predictions are really the gold standard of science. All right, so 1979, National Research Council has a report. They call it Charney Report. And there's a really great sentence in there, which is, we have tried, but have been unable to find any overlooked or underestimated physical effects that could reduce the currently estimated global warmings or reduce them altogether. This is the 70s. I mean, that not only do we have a theory, but they're trying to look for holes in the theory, and they really can't find any. And again, nothing's changed in the last 50 years for that. We still are looking for holes. We still can't find any holes. All right, so that kind of, in many respects, that brings us to the end of climate science. We've done a lot of work since then. We've learned a lot. Our confidence has increased, but what those guys thought is what we still think. Nothing's really, there haven't been any revolutions in our understanding of climate science since that period. So I'll skip ahead a little bit to something else, which is sort of currently the issue, and at this point now, really not even that many people, dispute climate science. Now we're really talking, most of the arguments are about the history of energy. So how did we kind of get to where we are? So we've been burning oil and gas for 150 years. And then in the 2000s, some other things started happening. So one of the sort of more important things that happened is Germany started subsidizing solar energy very heavily. And with these, what they call feed-in tariffs and other policies. And that really pushed the installation of solar energy in Germany a lot. And then in 2010s, China started subsidizing solar energy. And we understand how to innovate. So if you want to drive down the price of something, you build a gazillion of them. If you want to know how we got such cheap flat screen TVs, for example, in 20 years ago, flat screen TVs were really expensive. Now they're dirt cheap. And the reason is we built a billion of them. And as Germany's subsidies and China's subsidies pushed out the development of solar energy, the price of those things has declined enormously. So the price of solar energy has declined 90% during the 2010s. Wind has seen a similar price drop. And right now, renewable energy is now the cheapest energy that we have. In fact, solar energy is probably the cheapest energy in the history of the world. Now, I know renewable energy is intermittent, but at the same time, engineers have spent the last decade studying how to integrate them. And we have a pretty good idea now of how we integrate renewable energy into a grid. And so the good news is we're living through an energy revolution. And, this is the solution. We just have to let the revolution proceed and push back against the forces out there that are trying to stop the revolution. At least here in the US, in places like China, it's going on gangbusters. I mean, they are not going to slow down. They are installing an enormous amount of renewable energy, and they are going to have the cheap energy of the 21st century if we don't do something similar. And so the thing that gives me some level of optimism of this is that this is not a scientific or technical problem. We've understood the science since the 1970s, and we've now gotten to the point where the replacement energy is as cheap as the power that is the cheapest power. And all we have to do is get over the other problems, the political problems. There's really a political problem. And I always tell my students, sometimes students will come to me and they'll be upset about climate change. I'll say, don't be sad, be mad, and do something about it. Get involved, get involved in the politics. I think in the US, one of the things I've realized is that, because the US has traditionally been so well governed, people we don't protest very much. We don't go out and march. I think Americans have kind of forgotten about, how to work the political system, how to get involved, how to do that. And we should all be doing that to ensure our future. Anyway, I will wrap up there. I'm happy to answer questions. Thanks.
Great. Thank you for that insightful history lesson, Andrew. I just wanted to, because there's more discussion in the chat and because I interrupted, I just want to clarify that this is a live stream for weather and climate science. So we're focusing on the science and choosing to have a program that is all science talks. And so we made a choice to highlight climate science that was more physical and chemical and kind of natural sciences. So we, there's lots of people doing great work on social science of climate change, political science of climate change, and there's a time and place for that. It's just not in this live stream. So I appreciate for you for skipping through some of those slides, Andrew. And the other thing I wanted to say is that while the point of this is not a political or partisan stream, we are making a political statement, which is that there are proposed funding cuts that are undermining our community of researchers and scientists and forecasters and meteorologists. And so this is a political act in that sense, but the point is for it to be a very narrow political act, which is that we are making one very specific ask, which is to call your representatives to support weather and climate science. Okay, so with that out of the way, let's take some time for questions for Andrew. I want to start off, Andrew, which is that you didn't talk about this in your talk, but you are also moving the history of climate science forward with your own research program. So one thing that you have recently published about is how climate is affecting the energy grid in Texas. Could you talk a bit about that?
Sure. So we, this is actually work I did on my own. I did not have a student doing all the work. So in August of 2023, I remember this. I looked at our electric bill and thought, holy crap, that's a lot. August 2023 is very hot in Texas. And it occurred to me that, this is a serious problem for a lot of people. If your bill's an extra $100 or $200, where's that money going to come from? A lot of people don't have the money to do that. And so I sort of set out to try to figure out what the impact of climate change on energy costs. And what I found out was actually quite interesting. Obviously when temperature goes up, you have to run your air conditioner more. So demand goes up a few percent. But the way the ERCOT, the Electric Reliability Council of Texas, the way the grid in Texas operates, the price is set by demand. So as the demand goes up, the price also goes up because they have to bring on increasingly expensive generators onto the generator stack. And so the consumers actually get hit twice. They have to buy more energy, and each unit of energy costs more. So, it's a reasonably significant amount of money. I calculated that climate change was responsible for about $80 a person in Texas. And, that's for a middle or upper class person, it's sort of an annoyance. But for people at the bottom 20 or 30%, that's a big issue. And, they have to make a decision about, are they going to pay for electricity? Are they going to run their air conditioner? Are they going to buy food? Are they going to pay tuition? Are they going to, they have to make choices.
Great, thanks for that. So you gave a nice history of climate science and mentioned that there's this dark ages between 1900 and 2050. And I was glad that you didn't say that the last few decades have been a dark age. So clearly we've been making some advances in climate science. So could you give a highlight of over maybe the last decade? What are some of what you see as the most important advances in climate science?
You know, I know I'm going to botch this one. I mean, there have been a lot of things. There have been a lot of things going on that have really improved our understanding. You know, for example, extreme event attribution is probably 20 years old. So that's where a storm occurs, and then we go in there, the scientists go in there, and then they analyze how much did climate change contribute to that. So that's actually a very new phenomenon. And up until that, you know, the standard line was always, well, science can't tell you anything about any individual event, but we can. There's also things about, you know, the carbon budget, been advances in understanding the carbon budget, the idea that the peak temperature we experience is basically the integrated amount of carbon dioxide that gets emitted. You know, that's a big advance. I also think there are a lot of advances in things like economics. You know, if you read the 2013 IPCC report or 2007, 2001, you know, the economists were all saying, oh, the impacts of climate change won't be that severe. And the people who want to slow down action on climate change have had a field day with that. And they always talk about it's just a few percent of GDP in 2100. And I think in the last 10 years, there's been a lot of work by economists. And so very few economists say that now. In fact, I really don't know any that would come out. Maybe there's a few, but very, very few. They all understand this is a problem where we really can't estimate what the costs are. We just don't know. We don't have the tools to do that. And we're always learning about new impacts. So just one example, because we just had a talk from Kerry Emanuel, had me thinking about this. About 6 months ago, there was a paper by some researchers at, it's either Berkeley or Stanford, who talked about the number of people that are killed by hurricanes. And what they found is that while only a few people die in the immediate storm, about 10,000 people, you have about 10,000 excess deaths in the 15 years after the storm hits. And this was completely new. Nobody had understood this was happening. And so I think there really have been a lot of advances on sort of helping us understand maybe the impacts. But as far as the fundamental physics of the climate system, you know, we've done a lot of good work. You know, Ben Santer has done a lot of fantastic work on attribution studies and things like that. But you know, if you read the Charney report, you think these guys understood it, or Manabi and Weatherald. I mean, they understood what was going on.
Yeah, it really is remarkable that some of the basic numbers that we use to summarize what we know, like the number called the climate sensitivity, which is how much will a planet warm for a doubling of CO2. The average number, or the middle of the road, hasn't really changed since those times. And I've always wondered, is it just that they got really lucky, or I don't think so. I think it's that Manabe and Weatherald, they had basically all of the right climate feedbacks. They knew that there's more water vapor when the atmosphere warms up, and that amplifies the warming. And they knew that the structure of the atmosphere changes. And yeah, what do you think about that?
Yeah, I mean, when the Charney report was written, they had 2 GCMs, 2 climate models, and they had really smart people with good physical intuition. You know, I sometimes wonder if as a field, we rely too much on climate models and not enough on thinking. And, you know, when you don't have the climate models, you don't have a billion runs of them, you can't run all these different configurations, you know, it forces you to sit back and think. And, you know, there were ways they could have been wrong, you know, like they didn't have any idea really what the cloud feedback was. But it turns out that the cloud feedback is small enough that it didn't really influence their, you know, it didn't have a big impact on their analysis. So yeah, no, I mean, it's a very impressive, you know, piece of scholarship. I would also add that I think, you know, the basics of the global average climate system is not that complicated. I mean, I teach it to non-majors. You know, we do a 2-layer model, a 1-layer model, a 2-layer model. It's not that complicated. It's algebra. And so, you know, the other way to think about it is that this is really a lot less complicated than you think it is. It gets complicated when you start looking at regions and other things. But this sort of the global average climate is set by energy balance. top of atmosphere energy balance, and that's not that hard to work with.
Yeah. Could you talk about measurements a bit? So are there measurements that you think that we should be making that we're not yet, or that are at risk of being phased out, either because of funding cuts or just because they're coming to the end of the life of a mission or something?
Well, I think that, that keeping measurements going is crucially important. Measurements like top of atmosphere energy balance. So you have to measure that from a satellite. So we have satellites. What I mean by that, for people that don't live and breathe this stuff, is if you think of the planet as a system, you've got energy coming in from the sun, and then you've got heat flowing out in the form of infrared radiation to space. And for about the last 25 years, NASA's had satellites in orbit. Actually, even before that, TRIM, 1997, had a energy balance. It even goes back further than that. But for the last 25 years, we've had really good measurements of top of atmosphere energy balance. And, that's been crucial in understanding how we're affecting the climate, because, to zeroth order, climate change is a energy balance problem. And so I think that's a measurement, continuing to estimate the global average surface temperature. So whatever happens in the US, I think the good news is Europe and China are going to keep doing this. And so if the US really pulls back, I think the main effect will be that we will just have worse information than other countries about this, or we'll be relying on China and Europe to tell us things so that we'll be ready for the bigger hurricanes and more severe extreme events. So that's I think continuity of measurements is very important, and the U.S. really should be leading on that.
Yeah, agreed. So let's take a question from the chat. We have a question from Rihanna, who asks, is there a realistic way to update the energy grid in the U.S. in a reasonable time span?
Well, when people talk about sort of decarbonization and you talk about the energy transition, it's a multi-decadal problem. I mean, we're not going to shut off fossil fuel plants and replace them with renewable energy in 2025 or 2026. And so if you think about doing it in by 2050, yeah, there's plenty of time. I mean, we know how to build stuff. The problem is, and I'll say, just look at China. Look at how fast China is building out their grid. I mean, it's hundreds of, they are closing in on 1 gigawatt a day of solar installed. I mean, think about that. A gigawatt's basically like a coal-fired power plant. And they're at about 0.7 gigawatts a day last year. So, I mean, that they can build fast. In the US, we have trouble building stuff for various reasons, which I won't go into. It's hard to build stuff. You get sued. It takes forever to get approvals. There's a real permitting issue. People have been talking about that. And I do think that, we need to figure out how to get past these permitting problems in the US. Otherwise, we're going to have an energy system that's not as robust as our economic competitors. If China has better energy, cheaper energy, they're just going to kill us in the economic battle of this century.
Great. We have another question also about energy, which is, what kind of technological advancements allowed us to actually have more efficient green energy sources? And can you speak on how we developed them?
Right. So I think that person's probably asking is why did the price on solar drop so fast? And it's basically this what they call learn by doing loop. We've probably all had the experience. You want to cook a recipe. First time you cook it, it's always awkward. You don't know the timing. You don't know how to do it. And it comes out, it's a mess. But the 100th time you make it, it's like you've got it down to an art. You've got this, then this, and you do this while this is cooking and this. And building solar panels is the same. You learn how to, you build a gazillion of them, you learn how to do it. And I would also say China has invested an enormous amount of money in automation. So if you go into one of their solar panel factories, there aren't very many people. They're all robots. They're all robots and machines doing it. And that was an enormous investment. China understands that the energy of the future is renewable energy, and they have worked very hard to corner the market. So they produce most of the solar panels. I mean, their electric cars are they're going to absolutely obliterate the rest of the world's car markets. It's going to be really bad for anybody who wants to try to compete internationally. The U.S., we're a big enough domestic market. Maybe we'll have car companies that just produce cars for the U.S. market, but they won't be able to sell them anywhere else. I mean, so it's really to learn by doing.
Right. They call that, what do they call it? The learning curve or the feedback. Yeah.
Right.
Great. Well, thank you so much, Andrew, for giving the talk, taking the time. Thank you to the chat for the great questions, and Andrew for answering them. With that, we're going to move on to our next segment. Let's all thank Andrew again for that great presentation in the chat.
Well, thank you guys again for doing this.
Great. All right. Thanks, Andrew. Bye. Okay. So if you are just tuning in now, we are now at hour 8 of the live stream, 8.5 almost. And we're going to keep it going for 100 hours. So 92 more. I need to sleep soon, but there's more science to come. So I will push myself for it. So why are we here? So we're here to learn about science, and specifically all the amazing achievements of the US climate science and weather science community. We have done a lot of things in the last 100 years or so. We have developed the first weather forecasts. We have improved those weather forecasts so that they're now reliable enough that you actually look at the apps on your phone and trust the forecast that they make. We have developed models that don't just forecast a week into the future, but make projections of what climate could change like because of human emissions decades into the future. And we're continuously improving those. And along with all of that, we are making all kinds of observations. We are making observations of weather systems in real time so that we can feed that data right back into the weather models and make them accurate. And also we are making climate measurements over really long periods, continuous measurements that give us a record of not just how the climate is changing now, but also the baseline of how it had changed in the past, to give us that historical context. And all of this information is essential for our forecasts. We need to validate the models, check them against the real answer. And all that science doesn't come for free. We need you, the taxpayers, and the federal government, who makes that money available through research grants and funding for research laboratories, and all kinds of research staff who keep the weather forecast coming, keep the climate models improving, make the observations. All this requires support from the government. And so that's what we're here for. And we appreciate you taking the time to listen to our science and also to advocate on behalf of this science. So we'll leave a link in the chat. You can see the banner now. Go to wclivestream.com/act, and you can call your representatives and ask them to support weather and climate science in the US. And with that, I am very happy to introduce our next speaker, Dr. Ralph Keeling. All right, welcome Ralph to the stream.
Listen, thanks Henry so much for coordinating this. It's a real pleasure to be able to talk, and thanks to all the others behind the scenes that helped organize this. I've been listening to bits of this in the lead up here, so it's really amazing how smooth it's gone. So it's a tribute to all the hard work you guys have done. So
great. So I have a little introduction. So
yeah, okay. So okay, great. Okay.
I don't need to introduce too much because your last name has already come up several times throughout the day in multiple presentations. But I will anyway. So Dr. Ralph Keeling is a professor of geochemistry at the Scripps Institution of Oceanography at UC San Diego and the director of the Scripps CO2 program. Ralph earned his PhD in applied physics from Harvard and has maintained this iconic measurement of increasing CO2 concentrations, which I'm sure he will talk about. So I will let Ralph give more context about how he got into the field, which is a fascinating story. And also, Ralph has done so much more than just measure carbon dioxide. He has measured made all kinds of insights into the carbon cycle, atmospheric composition, and global change, as well as the human's role in it. And his work has been instrumental in not just documenting the rise of CO2, but also some of the implications of that for climate change. And so with that, we're honored to have you, Dr. Ralph Keeling, and please take it away.
Okay, thanks so much, Henry. So yeah, I'm going to spend some time now giving what starts as a kind of a personal anecdote and a family anecdote to give a little bit of the history and where we started from on this topic. So it starts with history, but then it'll include some vignettes, I guess, of what we've learned along the way to try to clarify that this is still exciting science as well as important science, and there's a lot to keep track of as we move through into this amazing and also troubling world of rising carbon dioxide, and then also to point out that some of what we do here is very much at risk now because of pending cuts or threatened cuts. And so this is a fragile enterprise, and I want to try to communicate that as well. So, I mean, what do? I mean, I've maintained records that, for the most part, were started by my father at the Scripps Institution of Oceanography at UC San Diego. And these are records on the left of carbon dioxide. I guess a question here, can you see my cursor? Is that available or not?
Yeah, we can see that.
Yeah, okay. It's pretty small anyway. So of carbon dioxide at stations, we get air samples back from stations around the world, along a transect, mostly in the Pacific. And we track carbon dioxide in the samples that come back. We also track the isotopes of carbon dioxide, the carbon-13, carbon-12 ratio, for example. And then the isotope measurements, the CO2 measurements started in the late 1950s. The isotope measurements started in the late 1970s. And then one thing I brought to the mix was measuring changes in atmospheric oxygen. And we have records of atmospheric oxygen going back to around 1990. And in every case, these are the longest records of this sort. And they provide really interesting insights into how the world is changing, and perspectives on the climate problem from that. So the story starts really with my father. And of course, he's famous for this record called the Keeling curve, which is the record of rising carbon dioxide at the Mauna Loa Observatory. The time frame here is the late 1950s. My father had been a postdoc at the California Institute of Technology, where he started making measurements of carbon dioxide in air as an aside to a project that was originally focused on river carbon. He discovered, though, that through making measurements through new techniques that he developed involving liquid nitrogen to freeze out the CO2 and providing more precise measurements, that carbon dioxide was actually less variable in the atmosphere than people previously thought. Carbon dioxide had been measured in the air going back a couple centuries, mostly as adjuncts to people doing physiology experiments. If you put a mouse in a bell jar and want to know what happens to the CO2, you have to measure the air outside ahead of before you did it. And so there were measurements of that sort, and they showed widely varying carbon dioxide levels. And so he was surprised to discover that in the afternoons, in forest settings and other settings, he almost always got the same concentration. He correctly reasoned that what was happening is that in the afternoon, the air was mixing deeply in the vertical because the ground was heated from the sun. And so he was tapping into a larger piece of the atmosphere. And what he had effectively discovered is what we now call the atmospheric background, that there's a large part of the atmosphere that has relatively constant levels of carbon dioxide. The question of the day, or one of the questions of the day, was to try to figure out whether carbon dioxide was building up in the atmosphere. It was already posed as a question going all the way back to the 19th century. And the concerns about climate were already being raised at that time, but it wasn't really clear that carbon dioxide was building up. There was speculation that maybe the emissions from fossil fuel would be fully absorbed by the ocean, and so you wouldn't see it in the air. But equipped with his knowledge of this background, he was very motivated to go to a clean site that was away from local influences like forests and urban exhaust, and tap into this background as if measuring a core property of the Earth. And the station that was available then, that was used for this, was the Mauna Loa Observatory. So the program here was a really large one. It included measurements in many, many places and airplanes and ships. But the observatory was special because they actually put an instrument out there that would track levels at a very precise level. So the instrument went in about March 1958. And of course, what did he expect to see? He expected to see a constant background. And indeed, for about the first month, he got concentrations that were varying only by about a couple parts per million, between about 316 and about 319 parts per million on a modern scale. And that pretty much was an amazing constancy that no one had seen before. Problem was that right about that point, there was a generator failed, a power outage, and it took him a while to fix that. And when the power came back on, carbon dioxide levels were dropping, and they were at a lower level. And he was thinking, oh my gosh, my instrument broke, and we're no longer getting the stable reading anymore. Something's funny. And then there was another power outage, and the instrument came back on, and now it was started at an even lower level, but was drifting upwards. So scratching his head, trying to figure out what was going on. He had no idea what to fix, but he figured something wasn't right. And then he kept the instrument on as best he could. There was a period with more stable power. And about this point in the second year, he realized, oh, it's just doing what it did the year before. It's varying with season. What's amazing is that no one ever suspected this before. So all that's happening here is that carbon dioxide is being taken out of the atmosphere in the summertime by photosynthesis throughout the northern hemisphere. Mauna Loa is in the northern hemisphere, so the air mixes around, and it's seeing the influence of the forests and the other ecosystems in the northern hemisphere. So this is just the breathing in and out of carbon dioxide, unsuspected, completely surprising discovery at the time. Now, within about a couple of years of this record, it was already clear that carbon dioxide was going up. So although people had thought you might have to do massive surveys of the atmosphere to do statistical sampling to figure out whether carbon dioxide was building up, in fact, just by doing precise measurements at a few clean sites like Mauna Loa, you could already establish that this baseline was rising. And this was published in a paper in 1960, basically showing the rise. Over the next few years, there were challenges keeping this record going. There was a funding hiatus in 1964 when the Weather Bureau that ran the Mauna Loa Observatory was tasked with restricting its scope to just focus on weather and nothing else. So there's a brief hiatus at that point. But this is a plot that he made in around 1970, showing several years or about a decade of rise. And one of the things that emerged quite quickly was that the rate of buildup in the atmosphere was not as fast as you actually would have expected from all the fossil fuel burning and the CO2 released into the atmosphere. So CO2 was building up, but it actually wasn't building up quite as fast as you might expect. And so the question at that point was, what's happening to the carbon dioxide that's not going into the atmosphere? Some of the CO2 we're releasing is going somewhere else. And I'll point out that sometimes people say, well, how do you know that the rise is due to fossil fuel burning? And there are lots of reasons we know that. But it's in fact historically the case that question was not being posed, because there was another question that was more fundamental. Where's the carbon dioxide going that's not going in the air? And the way I'd put it is, suppose you have a chicken coop and you put 10 chickens in it, and you come back the next day and there are only 5. Now, what's the question? The question is, what happened to the 5 that aren't there, right? You know that the 5 that are there, you know why they're there, because you put them there, right? So we know why carbon dioxide is building up in the air, because we're putting it there. The mystery is where the carbon dioxide is going that isn't staying in the air. And in fact, it was possible to quantify the rate of buildup quite precisely through these measurements. It's also possible to quantify quite precisely how much we're putting in the atmosphere. So you could establish the ratio we have now called the airborne fraction, the fraction that stayed in the air. In this early paper, you see him plotting the increase here. This is the year-on-year increase. That's the rate of buildup. That's the slope of this graph over here, year on year. And here's how fast it should be rising if it all stayed in the air from fossil fuel burning. And you see it's about 50%. So about half of it staying in the air. But it's also varying. It's not quite constant year on year. It's varying because of, and my father speculated early on that the same kind of processes that caused carbon dioxide to go up and down with season might be causing it to vary year to year by some other kind of natural uptake and release, not seasonally, but interannually. And we now know that that's tied to El Nino phenomenon and ecosystems, mostly at lower latitudes, tropical ecosystems that dry out or get wetter during El Nino, La Nina cycles. Now, this is important already, achievement, showing carbon dioxide's building up. This motivated a lot of other science because now you had established a factual basis for concerns about human impacts on the whole planet and on climate. So we heard earlier about Suki Manabe. I know he talked to my father and got, well, okay, well, maybe this is something worth working on because it's really building up. But from my father's standpoint, the big question was, where is this carbon dioxide going that's not ending up in the air? And here's another way to look at it. This is just now stretched until recent years, the Mauna Loa record building up. And here's how fast it would have risen if it had all stayed in the air. And you could see that about the rise rate is only about half, but it's generally following the overall shape. But it has these, if you look, some years are slightly faster than others. That's this tropical ecosystem effect. So where's that other carbon dioxide going? So one of the things, and this is really how I got into this. I mean, my career started off in applied physics. I was interested in precision measurements. I wasn't particularly sure what I wanted to do, but I was, as a young adult, already talking science with my father. And at one point he mentioned to me that, so here's my father and I, this is around 1989 when I'd already built my machine, but his insight was that what he really wanted to do that he was never able to do was measure the changes in atmospheric oxygen that accompanied the changes in atmospheric carbon dioxide. And the reason was that it could help sort out where the carbon dioxide was going that wasn't in the air. And there are really two obvious big possibilities. One is it could be absorbed by the oceans because the oceans have a big capacity for absorbing carbon dioxide. That was already clear. And they could also be taken, carbon dioxide could also be taken up by land plants and stored as tissues in the trunks of trees, or the carbon stored in trunks, or the carbon stored in soils. If that's taken out of the atmosphere, would buffer the rise in CO2. And the power of an oxygen measurement was that it helped you decide between those two possibilities. So I set to work trying to measure changes in oxygen. It was a tough challenge because really, ironically, it's hard because there's so much oxygen in air. These changes would be very, very, very small. So it required a very, very precise measurement. I developed a technique involving interferometry to do that. And this is zooming out. So now this is the records we have starting around 1990 of changes in atmospheric oxygen in this upper plot. It's also going up and down with season, something else we discovered, also because of the breathing in and out. In this case, not just of land plants, but also the oceans. And here's corresponding carbon dioxide record at these same two stations. So how does oxygen give us new insight? Well, it's pretty simple. Oxygen is going down for the same reason carbon dioxide is going up, primarily because of fossil fuel burning, which releases CO2 into the air, but takes oxygen out. To the extent that carbon dioxide is removed by the ocean, that's an inorganic chemical process that does not involve oxygen. So that will not affect the oxygen loss rate. But if CO2 were taken up by land plants, that involves photosynthesis, which does produce oxygen. And so that would buffer not only the rise in CO2, but also the fall in oxygen. By measuring these two together, we can then figure out how much CO2 is going into the ocean and how much is going into the land. The system is a little more complicated than this, because although the ocean uptake of CO2 does not really involve photosynthesis to a significant extent, there is photosynthesis in the ocean, and that can produce oxygen that gets out of the atmosphere, or other times can go back in again. The ocean circulation can vary with season and interannually, driving fluxes in and out. So this creates a bias to this approach that we have to correct for. And it's important to reduce this effect to average over about a decade and look at the fluxes over about a decade. So what we've done with these data is calculate the distribution of the carbon over time, starting on decadal averages. The first point from 1990 to 2000 is plotted here, in the midpoint 1995. I haven't shown the results yet. So the black curve here is how much, this is pretty much the same graph my father had drawn. This is the emissions of fossil fuel burning, now expressed as billions of tons of, or petagrams of carbon. So you can see that fossil fuel burning has been increasing decade by decade, and or at least increasing in decadal averages monotonically. So the highest rates of fossil fuel burning are the last decade. And then this is the amount that's appeared in the atmosphere as CO2, also rising. So one thing this shows is that we're emitting more fossil fuel burning than ever, from fossil fuel burning than ever. And we're also seeing the fastest rise rates of CO2 that we've ever seen. So not only are we at the highest concentrations, it's also building up faster than ever. Now with the oxygen measurements, we can divide out where the carbon dioxide that didn't go into the air has gone into these two major categories, either into the oceans, shown here in blue, or into the land ecosystems, shown here in green. So you can see that the oceans has been continually absorbing more carbon dioxide over time. The land certainly has grown as a sink over time, but we don't see much evidence of an increase over this several decades in the last period. I should point out that humans are also directly impacting the land surface through deforestation and the clearing of land for agriculture. That tends to release carbon dioxide into the air. What we're plotting here is the combination of that plus other offsetting processes that are causing the land to take up carbon. And we can see overall that the land is gaining biomass, taking CO2 out of the atmosphere despite the human impact on the land surface. This is the net shown here. It's the net uptake. And these measurements are not the only ways to look at this. There's lots of techniques out there that look at carbon in the water directly, or people trying to track ecosystems and carbon stocks and vegetation directly. But there are a few methods that can zoom right in and get the global number like this. And the beauty of this is that we didn't have to look in the ocean. We didn't have to look in the complicated landscape of ecosystems. We could see the signature of what's happening directly in the global atmosphere by looking precisely at how the composition of air is changing. I should make an aside here. Yes, oxygen is decreasing in the atmosphere. We can show that. There's so much in the atmosphere, however, that it's not really an environmental concern. The percent changes are too small. And we'll run out of fossil fuels, the whole reserves in the earth, long before we make a dent in the oxygen supply that's very environmentally significant. So we have a big problem with the buildup of carbon dioxide. We do not have a problem with loss of oxygen at this point. It's useful as a diagnostic, but we're not measuring it because it's a direct environmental concern. Okay, so why are ecosystems taking up CO2 despite this deforestation? Why are they doing that? It's something unnatural, because the cycle of life doesn't take up carbon dioxide. It takes it up for photosynthesis and puts it back into the atmosphere. So there's an indication here of something out of balance in the earth involving carbon uptake. We also see indications of that from other signatures of these atmospheric records. And we can see quite clearly that photosynthesis is changing at the planetary scale. So I mentioned the seasonal cycle in carbon dioxide that my father detected at the Mauna Loa record. But at other sites, you also see seasonal cycles. And in the far north, this is what used to be called Barrow, Alaska, now called Ukkivik. You see a very pronounced seasonal cycle. And this is reflecting the uptake of carbon dioxide throughout the northern hemisphere. The air mixes around. So this is, even though you're in the Arctic, you're actually mostly seeing uptake from boreal and temperate forests. And that impact on the atmosphere is reflected downwind at Barrow, Alaska. But what's really interesting, both at Mauna Loa and at Barrow, is that the depth of these swings has increased. And at Barrow, it's increased very markedly. The up and down distance here is considerably larger than here. And on this graph on the right, we've actually just calculated that difference in parts per million. And it went up from about 13 parts per million in the 1960s to around 19 parts per million today. So it's about a 50% increase. This is driven mostly by increasing photosynthesis. The cycle depends both on photosynthesis and respiration, but there's really no way to get this big increase without photosynthesis going up. Something is causing photosynthesis to increase massively at a big scale. We also see an increase in Mauna Loa, but it's smaller in percent terms. So why could this be? Why is carbon dioxide being taken out of the atmosphere by ecosystems? Why is photosynthesis going up? Well, among the reasons is that CO2 affects photosynthesis. It's not the only reason, but carbon dioxide has different effects on the planet. It affects the climate through the greenhouse effect. It affects the chemistry of seawater through what's called ocean acidification. But it also is a direct fertilizer for plants. So we're seeing probably, among other things, an impact of rising CO2 on plant growth. We also see another indication. I mentioned also that we measure isotopes. The isotopes of CO2 are trending in time. This is a pretty complicated story because there are a lot of influences. But to understand what's happening here in quantitative detail, we have to understand how carbon dioxide is cycled in and out of plants through photosynthesis. Turns out when plants take up CO2 by photosynthesis, they have a slight preference for the lighter, the less massive carbon-12 atoms over the more massive carbon-13, atoms. This is in CO2. So CO2 that has carbon-12 in it is slightly preferentially taken up by photosynthesis over carbon-13. And in order to explain this record, it has to be the case that the preference of plants for one over the other has stayed relatively constant over time. And it turns out that requires that the carbon dioxide pressure inside the leaves, where the photosynthesis is actually occurring, is rising in proportion to the levels outside. And that requires that an important measure of how efficient leaves are at using of taking in carbon for a given amount of water has increased over time. This is so-called intrinsic water use efficiency. So we can see also not only this photosynthesis is going up, the plants are becoming more efficient in some particular measure here. This is a bit nuanced and I can't quite get into it in detail. But there's evidence of change in the leaf level processes that are showing up in these global records. Okay, so I want to zoom out now and talk a little bit about how the measurements fit in the larger envelope of work in this field. The measurements at Scripps were pioneering, but by the 1970s, there were already measurements being made by our partners in the U.S. government at the National Oceanographic and Atmospheric Administration. They grew a big program to measure carbon dioxide and other greenhouse gases between the 70s and 80s and 90s, and now it includes sampling at all these different stations. There are aircraft measurements. Why do all this? Well, it turns out that if you can measure in different places and you see slightly different trends, you can use that to make inferences about where the carbon dioxide is coming from or where other greenhouse gases like methane are coming from. You can sort of zero in and figure out regional sources and sinks, which is a very powerful way to understand what's happening. The U.S. was a very early player in this field. The Scripps work was pioneering. The NOAA work was pioneering at the global scale. Other countries have moved into the space as well, but mostly they're leveraging this backbone of work that the U.S. pioneered. So the Europeans, for example, have a regional network to try to understand greenhouse gases over Europe, so-called ICOS network. But their network doesn't make sense unless it's embedded in a global observing system, which is now, because of this historical evolution, dominated by the U.S. And I'm going to give an example of some of what you can learn from these NOAA records now. So one thing you hear a lot about, maybe if you listen, is that there's a lot of carbon stored in soils in the Arctic and frozen soils, so-called permafrost. And this carbon dioxide is vulnerable to being decomposed if the permafrost melts, which of course it's doing. That's an example. There's a photo showing that here. And so these big stores of carbon could be released into the atmosphere. There's as much carbon or more carbon in permafrost than all the fossil fuel we've burnt so far. So this could be a big carbon bomb going off. There's a legitimate concern about it. But what's actually happening? Well, it turns out if you use these NOAA data to make inferences about carbon exchanges in the boreal and Arctic latitudes, what you see is that overall, carbon dioxide is coming out of the atmosphere in those systems, not going in. The photosynthesis is overwhelming slightly the other processes. And not only that, it's going in at faster rates over time. So it doesn't mean that we have to be unconcerned about this process, but what it's telling us is that the alarm bells on this problem aren't actually ringing yet. Okay, it's something to be worried about, but the alarm bells aren't ringing. So it's kind of good news, at least for the moment. Another example like this is methane data. The NOAA labs measure methane, and the methane, this is a global measure of methane they produce, increasing over time. But notice there's an interesting plateau here in the 2000s, and then it accelerated up again. Before this acceleration, people thought that the methane was coming into some kind of steady state. Maybe it stopped its rise, and then suddenly it starts surging up again. The big question is, what's caused this acceleration in recent years? Well, turns out there's a lot of methane in the Arctic soils as well. As methane hydrates, is the warming of the Arctic, which is going on, at spectacular rates. Is that triggering methane releases, driving this up? Well, it turns out you can also do the same kind of inferences about fluxes from the Arctic that you can do for CO2. And it turns out that it's pretty clear that this acceleration here is not coming mostly from the Arctic. So again, the alarm bell isn't going off yet. Another possibility you might consider is that there's one of the major sources of methane is leaks from natural gas production. Obviously, if it's leaking out as methane, you didn't use it as gas because you want to burn it as a fuel. But if it leaks out before you burn it, it can appear as methane in the atmosphere. Turns out this is also easily ruled out because there's a trend in the isotopes of methane, which I'm not showing, that suggests that it's going in a different direction. If this natural gas leakage were dominating, the isotopes would be trending anomalously recently in a different direction. So both of those can be ruled out. So the NOAA data help put a reality check on what's actually going on here. So why do we think this methane has surged up again? The evidence points to being something in the tropics, something probably expanded wetlands in the tropics because of cycles of wetness and dryness that are favoring methane production recently, or agricultural practice in the methane in the tropics that is causing methane to go up. So this is clear from these data. We can put bounds on what's going on, and the search for what's going on can now narrow. By the way, it doesn't mean these processes couldn't be important in the future. I don't mean to imply that they're not significant, but they're not explaining this recent surge. So why do we still need these kind of data? Haven't we worked it all out? Well, one of the things I hope I clarified here is that we keep learning about these systems. The quest for knowledge isn't done, and these data have allowed us to make early detection of major changes going on, and I expect they'll still be playing that role in the future. The concern, for example, about methane hydrates or carbon stored in permafrost leaking into the atmosphere. That's an example of something called a carbon climate feedback, where warming triggers more greenhouse gases in the atmosphere. These data help put a reality check on that. So far, nothing big has happened. Doesn't mean it couldn't happen, but so far nothing big has happened. So detection of carbon climate feedbacks is something we absolutely need these data to help with. I didn't talk about this, but the same methods that are used to zoom in and understand what's happening in the Arctic can be used to track specific methods for removing carbon dioxide, or to assess whether countries are meeting their pledges for carbon dioxide reductions. You don't have to trust people to report if you can also detect what's actually being emitted from the atmosphere. The atmosphere is an objective measure of emissions if you can quantify it. And you need a network like this, like the NOAA network. So let me go back to the slide showing the carbon sinks that we worked out with the oxygen data. One of the reasons we would like to keep these records going is that, what's coming next? Well, let's suppose that we managed to get to a net zero scenario by the year 2070. Net zero is a measure of where we would control warming so that it stopped increasing over time. So that's a target for mitigating climate change. In such a scenario, the future looks a lot different than the past. Fossil fuel burning has to drop. The ocean sink will increase for a while because CO2 keeps going up for a while, but then starts going down. The land sink probably continues. The point is that the patterns we've seen in the past are not going to prevail into the future by almost any scenario. So there's a lot to learn going forward about how the system is behaving. We also may be able to verify particular methods of taking CO2 out of the atmosphere, because they'll show up as though they were increased in the ocean sink or the land sink. So we can do that kind of verification. So finally, I want to talk about the challenges. So the measurements at Scripps have been continued since the 1960s. And what I'm showing here, this is the CO2 curve at Mauna Loa. This is our oxygen, one of our oxygen records. And this shows how it's been supported by funding. Each one of these blocks is a separate grant. And different agencies have moved in and out over time. So why do we have these records? Well, because my father battled to keep them going, and I worked to try to find new sources of funding, because most people don't want to keep measurements going year in and year out. So it's a definite challenge. And that was a challenge even before the recent political changes that have made this landscape even more difficult. So I want to say a little bit more before I go to I want to say a little bit more about the situation at NOAA. As I point out, NOAA is really the backbone through the program. So the Global Monitoring Lab in Boulder, Colorado, which does these measurements, is really the backbone of global carbon observing. It's augmented by the Scripps effort at the global scale by including other oxygen data and longer records. And the rest of the world is very dependent on the US. This is really basic science that is tracking what's happening. It depends on stable support over time. It's vulnerable to being disrupted. The expertise is in a small number of hands. A lot of work goes into calibration and sort of back office or tedious work. It's not for everybody. So there's a very small community working on this. Ultimately, it's not really very expensive either. These measurements don't cost a lot. You can track what's happening at a large scale at modest cost. And of course, NOAA is potentially threatened by the administration's plans for reorganization and cutting. So we're very concerned about what happens in this space. And the Scripps enterprise, as part of this, also depends on NOAA support, because we get samples from Mauna Loa, we get samples from other observatories. We also get direct support from NOAA. You can see that this orange is the support we get from NOAA. So we're kind of all dangling from one thread here, and it's a pretty vulnerable situation. And it's the whole world that depends on this, not just the US. So I think I'll stop there and happy to take questions.
Excellent. Thank you so much, Ralph. Big thank you from me, and especially from the chat, who has been very enthusiastic about your talk. So much so that you pushed our stream over 2,000 concurrent viewers, which is awesome. And you also pushed us into hour 9 of the live stream. So a great way to do it. And thanks so much for telling us all about the history of those measurements, and then some of the new oxygen and other measurements that you've been making to keep these kinds of measurements going, these Keeling-like curves. Great. So we have a lot of questions from the chat. While I get those set up, I'm just going to ask you one question, which is, so you pick Hawaii because it's far away from land and big signals from forests and whatnot. But what about volcanoes?
Right. Well, so the question of whether the observatory at Mauna Loa would be compromised because of volcanic activity was addressed very early on, because in order to set it up there in the first place, you had to worry about that. And indeed, you can see excursions in carbon dioxide in the detailed data we get from Mauna Loa from upwind fumaroles at times. And when there's volcanic activity like we had recently, you see more of these events. But local sources produce fluctuating levels, like static on a radio. And we screen the data to only select periods where it's highly stable for hours at a time. We get those conditions at night when the wind is downslope, carrying air from higher on the mountain that's basically taken out of the atmosphere and drifts down in the nocturnal cold downdrafts. That air is very stable, or can be very stable in carbon dioxide levels. And the inference has always been that that's a reflection of the background atmosphere. Recently, because we had this eruption, the observatory actually was shut down for a while, and with our NOAA colleagues, we put instrumentation on nearby Mauna Kea. And now we have a Mauna Kea record and a Mauna Loa record, and they agree really well. So, by the way, a volcano wouldn't cause the CO2 to keep building up in any case. It wouldn't produce anything like what you see. It would just be a big scattered, noisy plot. If you really, if you sample the air right in a fumarole or something. But we're far enough away from that we can capture clean air enough of the time to produce this kind of records.
Great. Okay, so I'm going to bundle some of the questions in the chat together because there's so many. So a few people asked about whether there are specific types of plants that are better at absorbing CO2 than others, for example. And then related to that is the question of carbon geoengineering or carbon dioxide removal. So, would it be possible to intentionally stimulate biological production enough to actually make a dent in the carbon budget?
Yeah, let's talk about, I'm not a plant physiologist, so I'm not the best person to ask in details, but I think a key question is, for a plant to take up carbon dioxide and keep it out of the air, it has to put it in tissues that don't decompose. So from the standpoint of buffering atmospheric CO2, you want carbon to be deposited in some long-term reservoir. That would be something like a trunk of a long-lived tree, or soil carbon, the detrital matter in soil that can last a long time. And usually those kind of pools don't build up that fast. So it's hard to get a lot of carbon into those kind of reservoirs quickly. On the other hand, you can plant more trees. You can plant them in places you didn't have them. And you can protect the forests you have already. That said, it's a little bit sobering, but if you look at the total mass of all the world's living biomass, in trees and tree trunks and roots and grass, the total amount of carbon in living systems is now less than the amount we've burnt in fossil fuel so far. So we have produced more. The total mass of carbon we've taken out of the ground and released to the atmosphere has now exceeds the total mass of the land biosphere. We are not going to grow our way out of this problem. So trees can help a little bit, and we like trees for other reasons. because they bring other benefits. But we're not going to grow our way out. So the only realistic way to get to net zero involved, that is getting to a point where we're no longer adding more CO2 to the system, is to reduce our reliance on fossil fuels. That has to be the biggest part of any kind of solution. Now, there are other ways to reduce this problem by actively taking measures to take CO2 out, like growing forests, or I mentioned alkalinity enhancement, which is one way to do that. There's certainly viable means out there. I'm personally a little more fond of methods that store carbon in deeper reservoirs, or take carbon. How to put it? So you can think of CO2 as kind of an acidic form of carbon, and if we could turn it into another form of carbon, a more basic form like carbonate, you'd actually largely reduce the problem. And one way to do that is to take minerals out of the ground that are alkaline, and they'll react with CO2 and turn it into another less reactive form of CO2. So that's also kind of a geologic solution. So I'm personally more fond of the geologic solutions because I sense they have greater permanence. I worry that if you're going to grow trees to take out CO2, you're going to have trouble being sure that those trees are going to be stable for decades out in the future. After all, anything that's living for 100 years in the same place is probably going to end up in the wrong place due to climate change at some point. So I worry about the stability of these forests, for example, as we have increasing wildfire and drought and other pest threats and so forth. So it's difficult to know how to manage a landscape so that it's going to be a long-term store of carbon at this point.
Great. So I think you've convinced everyone here about the value of long-term continuous measurements like the Keeling curve. But that only goes back as far as we can measure. So do we have a sense, one viewer asks, of how far back do we have any kind of information about CO2? For example, going back to events like the Peteet extinction.
Yeah, I could have shown graphs like that. I cut them out. But yeah, I mean, we have pretty good inferences back about 800,000 years because we can get air that's pretty well, we can get ancient air trapped in Antarctic ice that we can date pretty well, and we can measure the carbon dioxide level in. And those records are nowhere near as precise or accurate as the modern records, but they're good enough to see changes down to almost a part per million level, maybe a few parts per million. And they show that the recent levels are higher than anything there. And CO2 went up and down with the ice age, as most people have seen those graphs, I think. Going further back, it gets tough because you don't have ancient air you can analyze. You have to use proxy methods, and they're usually not much better than about 100 parts per million. And so those are give an indication that if you go back to these earlier periods like the Paleocene, Eocene thermal maximum that you mentioned, that CO2 might have been considerably higher than today, up at 1,000 parts per million or more. So it's not like we're entering CO2 concentrations that never occurred on Earth before, but you probably have to go now almost tens of millions of years into the past to get these kind of levels. And of course, we're changing carbon dioxide level at a pace that may be unprecedented in Earth history, how fast we're changing it. This is really a drastic moment in Earth history that we've brought about through this very, very rapid rise in carbon dioxide.
Yeah. On the flip side of the drastic moment in history, on this, so Chris asks, I believe the Mauna Loa site was slated as being cut by the administration. Is this true? And they have a follow-up question. What would the implications be if it was?
Yeah, here's what I know. I mean, there was a series of office closures that were brought about through a change in the, what's it called? General Services Administration leasing. They do the leases, and a bunch of buildings lost their leases. And among them was the Hilo, the town of Hilo offices of the Mauna Loa Observatory. And that can be worked around. My NOAA colleagues say they can work around that. They have to get up and move. It's nothing very efficient about having to move. I think what's concerning is that it signals an intent, perhaps, that this whole enterprise wasn't needed. But so far, my NOAA colleagues are going about doing their work and moving forward. They don't know what's going to come next. If the observatory were shuttered and all the funding was lost, I mean, it would be absolutely devastating. I don't really want to speculate about how we get around that, but those of us who are still in the business wouldn't give up trying, that's for sure. So we do have an instrument on Mauna Kea, but that still needs the same staff to support it. So, yeah.
Great, thanks for clarifying the situation. Okay, I think with that, let's all thank Ralph one last time for that wonderful, wonderful presentation. And for answering all of the viewer questions. Thanks again.
Listen, thank you so much for organizing this. You guys are really real heroes hanging in there. So, and yeah, I'm thrilled to be able to participate. So thank you.
I see as our job is we're putting on a platform where we can get heroes like you to speak. So thanks again. All right. Thanks everyone for joining in on the live stream. If you're joining us just now, we are at 2,000 viewers. We have been going for over 9 hours live, talking about climate science and all the value that it brings to society. Since the 1950s, we have delivered weather forecasts that were not that great back then, but now they are so good that you can know basically what the weather is going to look like a few days in advance. You have apps on your phone, and you can rely on those. And we also are developing climate forecasts on longer time scales. So you now can have some sense of what the climate's going to look like 10, 15, 100 years into the future. We have been leading those fields of science in the US. So it was the US that created the first weather forecasts and the first climate models. These were in large part government labs, government funded projects. And some of that is now at risk. There are projected budget cuts to many different aspects of the climate and weather science enterprise in the US that undermine our forecasts. So, things like cuts to research grant programs for federally funded climate and weather research, cuts to weather forecaster jobs. We have observations of weather systems that are not being made and that we need to improve our forecasts. Not just improve, but keep the current forecast going. We are making observations of the climate system, as we just heard from Dr. Ralph Keeling, that not just in the past, but ongoing. And so we are keeping tabs on what's happening all around the world, all kinds of aspects of the climate system. And these programs are also at risk. Yeah, so we're all here because we want to talk about the science, but also the community needs your help. So we're asking you to please act. Go to wclivestream.com/act, and we've set it up so you can press a few buttons and call your representatives and ask them to support weather and climate science in the US. Okay, with that, I am very pleased to announce our next speaker, who will also talk about the importance of measuring the climate as we go through changes. And that is Dr. Sarah Purkey. Okay, welcome to the stream, Sarah.
Great, thanks for having me.
Okay, so Professor Sarah Purkey is joining us also from the Scripps Institution of Oceanography. And sorry, let me just pull up these notes. Okay, so Sarah received her PhD in oceanography from the University of Washington. Her research focuses on the role of the ocean in global climate systems, with a particular emphasis on deep ocean circulation and heat uptake. This is also my field, and so I read a lot of Sarah Purkey's papers and use a lot of her data. Her groundbreaking work has significantly contributed to our understanding of how the deep ocean is warming and its implications for global sea level rise, and Earth's planetary energy balance. Sarah has been working in numerous oceanographic expeditions, collecting data and tracks changes in the world oceans, especially using robots, which you can see already on the slide and Sarah will talk more about. Her research has been published in various journals and earned her recognition across the field of oceanography, and we're very excited to have Professor Purkey on to share her insights into the deep ocean's role in climate change.
Great, thank you. Well, thank you for having me, and thank you to all the organizers for organizing this. It's been a great event so far. So today I'm going to talk to you a bit about how we measure the temperature of the ocean and explain to you a little bit about why that's so important. And so what this is a picture of, as you can see on the screen, we have the surface of the ocean where we can have boats and icebergs and birds and where we live, and then below the surface it's much more opaque. It's much harder to see what's going on. And so I'm going to talk to you about a program called Argo, where we have basically deployed robots throughout the global ocean, and we use this to monitor how the temperature is changing from week to week throughout the global ocean. But first, I'm going to start with something really basic, talk about the energy radiative imbalance of the Earth. You might have seen figures like this if you've been watching this for a while. This is an older one. It basically shows what energy is coming into the climate system, so at the top of the atmosphere, what's coming in, and what's going out. And I like to start with this just because it gives us a broad picture of kind of what I want to talk about today. So you can see there's incoming solar radiation that's coming from the sun. Some of that's reflected, some of that's absorbed. And then because of the temperature of the Earth, some amount of that is going to radiate back out, and that's shown in orange going out. And what's important here is that the amount of energy coming in is not equal to the amount of energy going out. And in this diagram, it's shown down here, I've circled it in red, as this 0.6 watt per meter squared. So a watt is a joule per second of energy imbalance that's staying in the climate system. And I do really like this figure quite a bit because it shows a lot of the important processes that are happening with this imbalance. But the one thing that I don't love about this figure is it shows this 0.6 watts per meter squared going into what looks like a cornfield, maybe somewhere in the middle of Kansas. And what we know from the climate system is that's not quite right. So let's talk a little bit more about this number and how we know what this imbalance is. And so this is another plot. Basically what it's showing is the energy change going back from the 1960s going forward to the present. And the black line is showing the accumulation of energy. So I'm not in watts anymore, I'm in zetajoules. This is a huge amount. This is 10 to the 21st joules that are accumulating in the climate system. And so if we start our curve back in 1960, we can see that it was flat for a little while, and then it starts to go up and up and up and up and up. And if I look at the difference in energy between that's accumulated in the system between the 1960s and present, I see that there has been 381 zetajoules going into of extra energy that we have absorbed over these few decades. And here, these red lines are showing the error bars associated. How well do we really think we understand that number, that accumulation? And now I'm going to move forward and show where that energy is going. And so again, this is the same black line. I've just changed red to these dotted lines to show the error bars. And now the colors are really showing where that energy is going in the climate system. And so starting from the top, there's 3 colors of blue here. And this is showing all of the accumulation of energy into the oceans. So the surface ocean above 300 meters, above 700 meters, and all the way down to the bottom. And then we see a small amount of energy. And if I add all that up, it's 340 zetajoules. So we're talking about over 90% of this is just going into the ocean. So again, not going into a field in Kansas, but it's mostly going into our oceans. And some amount of that is going into the land. That's this orange stripe down here. Some amount is going into melting ice. And then actually a very small amount of it, really less than 4 zetajoules, are staying in our atmosphere. And so I just want to point out why that's so significant is when we talk about global warming, when we talk about the fact that our weather and climate is changing, it's a really small amount of the total imbalance. And we get to thank our oceans for that, because over 90% of that is going into our oceans. And if there's any small perturbation in the amount that's going to the ocean, the residual is going to be left in our atmosphere. And that could have really profound effects on the rate that we're going to warm up and the kind of changes that we see. So for the remainder of the talk, I really have one goal here, which is to talk about how we know those 340 zettajoules have gone into the ocean. How well do we know that? And how have we measured that from year to year? And if we look at our globe, often we're centered around North America or Africa or some other continent, but there are many angles that we can take of our globe, and we are the blue planet, right? So this is a picture of the globe. The ocean is huge, and it's deep, and it's hard to get to. It's very remote, and so the question becomes, how do we monitor this? How do we measure the heat that's going into these remote parts of the ocean? And so before I get into that, I'm actually going to rewind in time. I'm going to go back to the 1990s and tell a little story about how we got to where we are with ocean observing, and to kind of motivate how we got these subsurface ocean measurements of temperature. I'm going to actually start with a program that was done by NASA to start monitoring sea surface altimetry. You need to go. Okay, thank you. And so in the 1990s, there was a program where we put satellites out to orbit our Earth, and as they spun around, they could actually measure small variations in the sea surface height. So here, this is showing how this is a satellite. This is Jason flying around the Earth, and underneath it, it's going to measure the sea surface height as it goes up and down. And if I look at what this can observe, is I can see that the sea surface height is going to vary on all different times and scales. And you can see some of that variation over here in the schematic. And so if I take a given point in the ocean and I look at how that sea surface is varying in time, there's huge seasonal cycles, there's other kind of variabilities, there's this long-term trend. But a lot of that variability on short to medium time scales is really driven actually by the steric changes below. And so what I mean by that is when water warms, it expands. And so this is if you have frozen ice, or if you have taken water and let it warm up and watch it expand, you can see these variations. And this happens on larger scales in the ocean. And so basically all this is to say is that if I have a column of water and it's cold, it's going to be a certain height. And then if I warm it up, it's going to expand. And how I'm going to see that is in a total change in the surface height of the ocean. And that's what the altimetry is measuring. And so while the altimetry was going out in the 1990s and we were getting all this really awesome data about the total variations in sea surface height, scientists started to think about, well, I need two things. I need to be able to verify that that's true. And to do that, I can estimate how the height's going to change very accurately if I know how the temperature is changing. And they also want to know how that change in the temperature was varying throughout the water column below. At the same time in the 1990s, there was a big push in ocean robotics and technology that was going on. And there were these things called profiling floats that were invented. And basically how they work is they capitalize on the fact that the ocean is stratified. And so what I mean by that is the surface ocean is warmer. So this is showing a section of the ocean. This is depth going across from the US across to Africa. This is a map showing here. And this is showing the various temperatures that we see in the ocean. So it's warm at the surface, it's cold in the deep ocean. And what that means is the surface water is a little less dense than the deep ocean. And when I put things in the ocean, they're going to go to where they're called neutrally buoyant. And so here, if I put something in the ocean that was the same density of this water at 4,000 meters, it's going to sink down to 4,000 meters. And so that all the water above it is lighter and all the water below it is denser. And then it stays at that depth. And so what this float technology does is it allows this robot to actually change its density. And how it does that is simply by changing its volume, because density is defined as its mass over volume. It's not going to change its mass, but it can change its volume. And so all it does is it has an internal reservoir of oil in an external bladder, and it can inflate that external bladder. And when it's inflated, its volume increases, and therefore its density decreases, and it can move to the surface. And so this is a little cartoon showing that I can move this float up and down by changing its density. I can show some pictures. These are some early versions of these Argo floats back to the 1990s when they were first getting invented. And this is a more present day Argo float shown here. And so they're quite big. They're about 4 feet big, and they weigh basically the equivalent of that volume filled with seawater. And so after these satellites were deployed in the early 1990s, by the late 1990s, a group of scientists had gotten together and had painted this vision where they were going to employ this ocean technology, this float technology, and basically have this fleet of robots going up and down in the ocean to measure the subsurface variability. At the time, this was very novel. It was a kind of a crazy idea, but they pushed forward. They got a lot of international buy-in, and they moved this forward. And they called this fleet was going to be called the Argo Array, and it was really named to couple with the satellites because the satellites were named Jason at the time. And so going back to Greek mythology, Argo, which was Jason's boat, was going to be the ocean in situ observations that we're going to couple with the satellite observations to give us a full picture of what was going on in the climate system. And so how these floats were missioned to work is we deploy them from ships. They go down to 1,000 meters. They drift for about 10 days, and then they go down all the way down to 2 kilometers. And as they come up, they have a sensor on the top that can measure the temperature and the salinity. And it's going to take a continuous profile of the temperature and salinity. And when it gets to the top, it has an antenna on it. It calls into a satellite system, and it basically just emails us its data. And so what we get is these beautiful profiles of temperature and salinity from where that float just profiled. And today, the picture that we have actually looks very similar to what was envisioned in the early 2000s. We have about 4,000 floats that are active. This is a plot as of today of the active floats, and it's colored by which country deployed it. And so here, the US contributions are shown in green. We deploy about half of the active floats, but there are over 30 countries that are contributing to this array. And you can see some of those countries listed down here. And all these countries have bought in that this is a great way to observe our oceans, and they all contribute very actively. So again, here's just some more pictures of Argo today. So when ships go out, we can put floats on them. Here's a bunch of floats loaded onto a ship in the lab. And then we go onto the deck. We can lower them over the slide, and then we can say goodbye. And they will profile for up to 10 years in the ocean, going up and down every 10 days, sending us back their data. And so the goal here was very, in the design, was very purposeful. From the satellite observations and decades of observations of the ocean, we understood something about the horizontal and vertical length scales of variability and how fast the ocean was changing. And so the design here was to have about 2 floats every 6 degrees by 6 degrees that were sampling basically 3 times a month. And with that data, we understood that we could resolve with confidence how the mean temperature of that box is changing on a weekly time scale. And so what we do is we continue to monitor. This is the plot basically showing where we think we have 100% coverage, where we have those 2 floats for every one of these boxes. Red is showing areas that we don't, and then we can say, okay, well, we need to get some more floats and we need to put them in this area as the floats die out at the end of their life. We're continuing to populate these boxes. And I do want to say something. The data system that goes along with this international program was very forward-thinking and very advanced. And so what's shown here is just a real schematic about where the data goes. So it comes to the surface, it sends the data back, and in real time, that data is put up on the web for anyone to see. So within hours, that data goes up. And then there is a delayed mode quality control where somebody actually sits, so there are people in our group that sit and look at every profile and make sure that it's climate quality, make sure it's the highest quality and ready to be used for climate science. So today, that data is used for a huge number of applications. One of the biggest applications is for weather forecasts. So the data comes up in real time, and that data is used to predict what the weather is going to be tomorrow or the next day. It's used for extreme warning systems, because it turns out the ocean plays a critical role in predicting where things like hurricanes are going to land. But it's also used for understanding what's going on around oil, drilling, and fisheries, and a whole number of applications. In addition, we use it a lot for science. This is showing the number of papers that are coming out using Argo data. And at the moment, we publish about 2 papers a day using these data. And this does a whole variety of different scientific applications. But the scientific applications that I want to focus on for the remainder of this talk is really the climate signal in that long-term warming signal. So going back to how we know that those 360 zettajoules are going to the ocean. So first, its mission was really to look at the steric signal in the ocean. This is a plot showing the total sea level change going back to the early 2000s. This is the red curve going up. This is what's measured from altimetry. Black is how much mass is being added from melting, and then the yellow is showing how much of the sea level rise is due to that warming of the ocean. And basically, this is showing if I add those two together, I get back to the blue, which is what I want to see. So it is fulfilling that mission. And then thinking about ocean heat content, I can take all of those data and I can map them, and I can look at how the ocean is changing from month to month. And so this is one product that uses all the Argo data. And what's being shown here, and I can run that again, is going back to the 90s, and you can see time marching forward, and it's showing the mean temperature change within each box. And so red is showing where it's anomalously warm, and green and blues are showing where it's anomalously cold compared to what it is normally at that box over the whole 25-year time series. And what I can do with that is then I can look at things like what is the trend in temperature at a given location. And so over here on the right, I'm showing a plot that, over here on the right, I'm showing a plot of the temperature change in watts per meter squared of the upper 2,000 meters. And everywhere that it's red, it's showing that that box has warmed, and warmed significantly above our competence limits, going up to about 6 watts per meter squared. So some places have warmed a lot more than others. Some places have cooled. So the places that are stifled means we can't tell outside of our error bars whether it's warmed or cooled, or there's some other kind of long-term variability or interannual variability that is over the size of the linear trends. We can also look at, say, how is last year, 2024, different than the climatological mean, or to say how is 2024 different than the year before, 2023. And so those are the kind of things that we can do with these data. The ocean, and then the other thing we can do is, again, look at the inventory of ocean heat content. So here, this is showing depth versus time, where blue is relatively cold over the 25-year mean versus red, which is relatively warm. And what we can see is the surface ocean is warming the most. The deep ocean is also warming. And we can see that long-term trend over here on the right, going back to the 50s. So again, all of these are different estimates based on different mapping. There's a bigger error earlier in the time series, and then it gets much more quieter once we have Argo going forward. And we can look at that down to 2,000 meters using the Argo fleet. And then below 2,000 meters, we have to do something a little bit more special. So below Argo, what we do is we use ship-based observations. So really quickly going to talk about the Ghost Ship program. The Ghost Ship program is an effort to take ships out and go along these lines. And basically along each of these lines, we take a ship, we stop, we take a big water sampling system that's shown here. Basically, each of these are called Niskin bottles, and they collect water samples. It also has electronics to measure the water properties of the ocean. We put it overboard. We send it all the way down to the bottom of the ocean. We sit inside a nice warm ship because it's usually cold outside. And we can watch it drop down to the bottom and bring it back to the surface, and then we take all those water samples. And using this, we get these beautiful transects of the ocean going down to the bottom, and we can measure everything from temperature, salinity, but also things about the carbon, tracers, and various other things. In addition to that, really recently, really over the last 5 to 10 years, we have a new variety of Argo float called the deep Argo float that works exactly the same as the core Argo float, but it can go down to 6 kilometers. And so this is showing one model of that we built here at Scripps. It works the same way. It's buoyancy driven, but it has a glass sphere underneath this plastic casing, and it can go all the way down to the ocean. And this is just really quickly, this program is still spinning up. We only have about 200 of these floats out in the ocean. So using a combination of this Argo float data and the ship-based observations, we can get an estimate of what the warming looks like below 2,000 meters. This is showing below 4,000 meters. And again, we're seeing warming all the way down to the bottom. And so we see warming mostly in the Southern Ocean, but it's propagating following kind of how water is ventilated and moves throughout the ocean going to the north. So if I pull those together, if I pull the upper 2,000 meters, mostly from Argo, and the deep ocean from a combination of Argo and ship-based observations, and add those numbers together, that is how I get these 3 blue curves, and I can add them forward in time and look at the accumulation of heat in the ocean. And so in my last kind of 4 minutes here, I'm just going to touch really quickly on where we are with Argo and kind of where we're going. So the future of Argo. So right now, we're in a really exciting time for Argo. So over the last 25 years, we've been really focused on those upper 2 kilometers temperature and salinity measurements. Like I just mentioned, we now have a version of the Argo float that can go all the way down to 6 kilometers. And we also, and I don't have time to talk about it, have a biogeochemical Argo float. So in addition to measuring things like temperature and salinity in the ocean, we have new sensors that can measure pH and oxygen and nitrogen, and understand optics of the ocean that tell us things about the chlorophyll and how much stuff is basically in the water. So something about the biology. And so over the last few years, we've been thinking about how best to sample the ocean. And the picture that we've come up with is this idea of something called one Argo, where basically a third of the floats, we still have about 4,000 floats, but a third of them go all the way down to the ocean bottom, and a third of them measure the biogeochemistry as well. And a third of them are just that core. And where we are in 2025, we've been working really hard at this over the last 5 years to spin this up. And this is shown right now where we are. So red are those core floats. The orange floats that you can see on here are where the deep floats are, and the green floats are the biogeochemical floats. And so we have about 500, 600 of the biogeochemical floats, about 200 of the deep floats, and the rest are core. And when we think about how we continue to renew this array, so again, they die out. Sometimes they have premature deaths if they get picked up by a fisherman, or they hit the bottom, or they leak for some reason, or they just run out of batteries. We need to renew and deploy, renew about 20% of the array every year. At the moment, the U.S. contributes about half of that. And so the red dots here are showing the U.S. contribution versus other countries in blue. And how we fund that is shown over here on the right. And so it is, right now, it's 85% funded by NOAA. We get some amount of funding from NSF as well, about 15%. And it's actually for the amount of data that we get and the amount of use we get, it's a very cost-effective program. So we calculate that each profile that these floats take cost about $270 per profile. And so overall, for the U.S. contribution, which again is about half, it's about $13–15 million a year that the U.S. government currently supports. And so if you're in the U.S. And you are a taxpayer, it means you are contributing about 5 cents, about a nickel a year is what you pay to keep these observations going. And I guess not going too deep into this, but in the most recent budgets that have come out that are still being debated in Congress, there's been major cuts to NOAA. And one of the major parts that have been that are proposed to be cut is part of ocean and atmosphere research, which is where these observations and many of the parts of ocean observing are currently being funded. And so that definitely has us nervous because we believe that these are a really essential part of our observing system. They play into our ability to monitor the ocean and how much extra energy is going to the climate system. But they also really lead to fundamental research and help forecast our weather forecasts. So if you like to know with better accuracy what the weather is going to look like next week, you can thank your Argo float in addition to everything else that they do. And so we would like to see this program continue. And so with that, I just want to say thank you. Thank you to the organizers. Thanks for having me, and put our website up there, argo.ucsd.edu if you're interested in learning more. I'm very happy to take some questions.
Thank you, Sarah, for the wonderful talk. That was really nice. So we have a bunch of questions from the chat. My plan is that maybe we can go through them a little bit more rapid fire so we can get through more of them. But first, I wanted to ask you, so you mentioned the cuts to OAR and NOAA, but there's also a risk of rumors of large reductions in force or rifts at NOAA labs. Would that affect Argo as well?
Yeah, 100%. So for the US component, again, that's about 50% in the array. Some of it is funded through universities, so places like Scripps. There are 3 institutions in the US that produce floats. But the other half of that is actually done in government labs. So PMEL and AOML, which are both under OAR, there are oceanographic labs. Produce floats and contribute to this, but really have a lot to do with the oversight of the program and the leadership. And they also, the whole data system right now is housed at one of those labs. And so there is a very scary possibility that if somebody is not paying attention, that the whole data system would go down. And so then we have millions of dollars of floats out in the ocean. They would just go dark. We would have no way of communicating with them. And so that is something that we're looking into and we worry quite a bit about. And so we are really a government, university, and I should say private institution partnership. Most of the floats are produced by US-based small companies that rely on these grants and contribute back to the economy through the building of these things. And so it is a really big partnership through private, through government relations, and through the university systems.
Thanks, that clarifies a lot. Okay, so let's get to these great questions from the chat. So some of them you already answered, so maybe we can go kind of quickly. So just to summarize, can you remind us what the breakdown is between the ice melting and water thermal expansion?
Yeah, so people don't realize this, but when most of the or about half, a little less than half of the sea level rise that we've experienced to date has been actually just from thermal expansion of water. So as water warms, it expands. And so we are adding mass. For the most part, that's going to distribute somewhat evenly throughout the ocean. So ice poles are melting, and that ice mass is being added and it's distributing out the ocean. But then, in addition to that, as the water warms, it's going to expand, and that is about half of the sea level rise we've seen to date. And it's very uneven in the ocean. Some places are warming a lot faster than others, which is why some places, like here off the coast of San Diego, we haven't seen much sea level rise. But if you go to some of the islands on the other side of the Pacific, they've seen sea level rise that are 3-4 times the global mean rate.
Wow. Yeah. Okay, so I want to bundle a few of these questions about the floats together. So the first one is, what's the average life of the floats? And then the second one is, are these floats at risk of being damaged by sea life, or I guess conversely damaging sea life?
Yeah, so the floats have batteries to last kind of 8 to 10 years, depending on the float model. Sometimes they do spring leaks and die before that. And our average float lifetime is about 7 years right now. So, which is great because it keeps the price and the litter of the ocean down. They can, a shark could maybe take a bite out of that. We don't see that happen very often. Sometimes a boat will run over them or something like that is more likely. The sea life that does get to them is the really, really tiny sea life that's sometimes like barnacles that can grow on them. And that's not great because it adds mass to them. And at some point, it becomes too much mass for them to overcome. We kind of get around that by having them spend most of their life down at a kilometer where there's no sunlight, and so things don't like to grow. And then are they bad for the environment? So we are very conscious about what we use to make them. They're mostly aluminum, which is not a terrible thing to add to the ocean if they do die in the ocean and fall down to the bottom. And we do environmental impact assessments. And really the worst part of these is actually the carbon that we need to take to deploy them. So we have to put them on a ship and get them out. And that does use carbon we put in the atmosphere. And that's probably the worst thing that this program is doing. So we need to figure out some way to deploying them that doesn't use any carbon.
So related to the kind of technology of the floats, some astute viewer noticed there was not many in the Arctic. So can you talk about that?
Yeah, that is a great question. The Arctic is a really hard place. So these floats, how they communicate is through a satellite system, and they need to be able to get to the surface. And so they can hold on to their data. So in the Southern Ocean, we do get sea ice, and we have a lot of floats in the Southern Ocean. And they can hold on to their data for 9-10 months while there's sea ice over the top of it. And it just holds that information as it profiles through the year. But it does need to be ice-free for about a month so the floats can surface and transmit all that data and we can get it back. The problem with the Arctic is it's much more variable. With that said, the Arctic is parts of the Arctic are becoming ice-free over the last decade quite a bit more, and we have started to deploy some. And we're still working on that technology to make sure that they're working well. So there have been some floats. Our lab, I know, just deployed 3 last year. We are looking to expand into the Arctic. But again, the ice is kind of not the best for the floats. When they run into the ice, it tends to injure them and break the antennas. So we're working on getting to the Arctic, is hopefully something we'll see in the next decade.
Great. And I guess we should also say that there are other measurements people are making in the Arctic. So there are ice-tethered profilers where you have a similar profiling robot, but it's hooked up to the, well, I don't know, they probably put it through a hole in the ice. I actually don't know.
Yeah, exactly. It goes, you have a hole in the ice and it can go down, and then it talks through basically Bluetooth to the surface expression that can talk to the satellite. So yeah, so there are other things. There's gliders, and I should really say that Argo is part of GOOS, which is the Global Ocean Observing System. It is just one part. It does great in the open ocean. We couple with gliders, we couple with moorings to look at other parts of the climate system. With the satellites, obviously, I talked a lot about that. And so it is not all of the ocean observing. We need all these other parts too. It just does a really good job in the open ocean and taking this global big picture integrated view.
Great. Okay, so this isn't, well, actually, first I want to go, so we talked about the Arctic. Let's go to the Antarctic where there, you said there were some floats. So someone asks, what is the latest about the Southern Ocean? Another viewer noticed that there was way larger deep ocean warming rates in the Southern Ocean. So can you talk about that?
Yeah, I'd love to talk about that. That's my favorite part of the signal. Yeah, so the Southern Ocean is a really special place. And I guess I had some extra slides in here, and I can just throw this up really quick. I mean, the reason why the oceans can take up so much heat is because water has a large heat capacity, but also because we have ocean ventilation and circulation. And so what I mean by that is the atmosphere is going to warm. And if just the surface ocean warms, it can only take up a small amount of heat. But if we have deep convection and we have overturning, we have mixing, then the ocean's going to be able to take up a lot more heat. And we have something called the meridional overturning circulation. And there are places in the ocean where we get water from the surface that's rapidly taken from the surface and brought into the deep ocean and into the intermediate ocean. And the Southern Ocean is one of those really special places. And so we see in the North Atlantic, it's pretty efficient at taking up heat and carbon as well, because we produce that North Atlantic deep water, which is shown over here. But around Antarctica, we produce another water mass called the Antarctic bottom water. And it takes up about half of the volume of the ocean, is kind of being produced and ventilated around there. And so this is a place where we've seen rapid changes, and those changes are communicated throughout the ocean. So it's basically a conveyor belt that allows this heat to get into the deep ocean. And so it's that, and it's also this Antarctic intermediate water, which is another mechanism that's centered around the Southern Ocean that allows for ventilation of the ocean and allows the Southern Ocean to really be a hot spot for taking up that anthropogenic heat. Oh,
I realized we had a question come up, I think, during Ralph Keeling's talk about AMOC. So there's some questions about, is the circulation slowing down? And so a related question is the warming that you're seeing in the ocean a signal of the circulation slowing down, or is it vice versa, that the warming is the thing that's causing the circulation to slow down, or do we not know yet?
Ooh, that is a really great question. So the AMOC is a complicated thing, and I like to think about it as these various pieces of these different water masses. And understanding each of them involves really understanding how those water masses are formed and what are the control mechanisms controlling it. And so I think we know more about some than others. There is a fair amount of variability in the overall strength of the AMOC. There are complicated feedbacks about how the ocean's going to be able to take up heat, about whether it's spinning up or slowing down. The part that I know the most about is thinking about that Southern Ocean and the Antarctic bottom water. And we do think we see a fair amount of evidence that that limb, at least, of the overturning circulation is slowing down. And we think that really has to do with surface forcings of buoyancy changes that are happening where those waters are being formed.
Yeah, and just to give our viewers more context, this is something that I'm personally very interested in because of Dr. Purkey's measurements. So it's providing a lot of not just information for things like forecasts, but also information for other scientists to use to answer scientific questions.
Yeah, I mean, I think this is a great question. I think a lot of scientists are working on this, and just want to emphasize that we need people to continue working on this. We need great minds and data to kind of support it and the models to go along. And so it's the only way we're going to continue to monitor and get ahead of any big changes that could affect our climate very rapidly.
Yeah, okay, so maybe a couple more questions. So one is, from Kayla, where would you want more floats to be deployed?
Yeah, that's so I am really interested in the deep program. I think the deep ocean it's vastly undersampled. It is, people talk about it's easier to get to the moon than it is the deep ocean. It is a fascinating place of kind of basic exploration is still needed. And when we send the floats down there, we're getting back information about things that are so basic of our understanding of this part of the climate system. And so I would love to see an expansion of the Deep Argo program so we could actually get global coverage for at least a couple decades to kind of look at what is the deep circulation look like? What does the temperature variations look like? What is driving the dynamics down there? How can we use that to better constrain our models, which will have a big implication on how well we can predict the future? And so I guess I would say that the deep ocean really below 2,000 kilometers or 2 kilometers of Argo would be a great place to put it. And then beyond that, I think the poles are fascinating. The Southern Ocean is still undersampled. The Arctic, it would be really exciting to get some floats up there.
Great. So this is not exactly a question, but someone floated the idea of adopt a buoy in the chat. And I'm wondering if you could actually talk about some of the outreach that Argo does, because isn't this a thing that you do, that you go to classrooms and they get to effectively adopt a buoy?
Yep, if you go to the UCSD, argo.ucsd.edu website, which is the Argo page, you can look at some of the outreach efforts that are going on there. And there are a few different programs called Adopt a Float, where classrooms anywhere from K through 12th grade can adopt floats. And it's free. A classroom can sponsor a float and say, I'm going to adopt this float. And what you get is you can send you get to name the float, you get to put your school logo on the float. And then you get to follow along on its journey as it's deployed and collects data. And it's a really fun program. And so, yeah, I do encourage people to look on the website. And if you have elementary through high school age, or if there's anyone out there that is interested in getting involved, you can reach out to me. You can reach out to any of those avenues and get involved. It's really fun to adopt a float.
That's hilarious. I forgot that the actual name of the program was Adopt a Float. I just knew that something vaguely like it existed.
And I have to say, I love like the designs and names that have gone onto these floats, and it makes actually deploying the floats super fun when they're all decorated up and ready to go, and each one gets its own name, and it's very individualized.
Okay, well, let's all thank Professor Sarah Purkey one more time for a wonderful talk and for answering some questions and pushing us into hour 10 of the live stream. We are now 1/10 of the way there, still holding on to 2,000 viewers. So thank you everyone for staying up into the night. And yeah, thank you again so much, Sarah.
Thank you.
All right. Okay, so with that, I am arriving at the end of my shift. So I will now welcome on the next host, Mary McGraw, who is an atmospheric scientist at a NOAA Cooperative Institute. Welcome to the stream, Mary.
Thanks, Henri. Great job holding down the fort for 4 hours. I think before we get started on our next talk, we have to reset the stream. So I think everyone should hold tight for a second, right?
Yeah, so I think that what will happen is this stream or the live feed might go down, but if you just go back to either the YouTube page or WC Livestream/watch, you'll be able to get the new stream there. So YouTube is not meant to stream for 100 hours straight, and we're doing it the hard way.
Awesome. So yeah, I think everyone just head back to the YouTube or the live stream site. Make sure you get on the